Hello and welcome to another tutorial. In this tutorial I'm going to discuss sequences and series. These are important concepts in math and analysis, and I'll discuss how to implement them in Java. Now, a brief introduction to sequences. A sequence is basically a function of integer numbers. So if we have a continuous function f of x, so it's called a continuous function because x is a continuous variable that can span all the way across the real numbers. And then f has a dense relation. The plot of f is basically dense, so it's a dense plot. But then when you look at the discretization of this function over only the integer numbers, you see only dots. So this plot is not a dense. It's not dense. It's a discrete points along the integer numbers. Okay, so this is called a sequence of integer numbers, and it could very well span from negative numbers to positive numbers. And we typically don't use the sequences with f of n. We typically show them as f sub n or a sub n. So we use a subscription we use a subscript index for the sequence instead of writing them as f of the x or f of the n. So an is value of an can be real or complex. So the sequence could be a sequence of integer numbers, which are always real, but then it can map them to real or complex numbers. Okay, so the output of the sequence can be real or complex. Here we just consider real numbers, so the output of the sequence is also a real number. And it can be defined over positive or negative numbers, from negative infinity to positive infinity. But the typical case is that we typically start from 0 index, because if you have negative, you can just shift the index, right? The convention is to use from 0, then go to positive numbers. Sometimes we just start from 1 and go to positive numbers. I guess it's really a matter of choice. And then one example is 1 over n squared, and n starts from 1, 2, 3 to infinity. And then there are two important types of functions. So if you look at this sequence or the representative function, you see that as you increase n, the function increases monotonically. So this is called a monotonically increasing function. So for all n, at each given n, if the next term of the sequence is larger than the current term, it's a monotonically increasing. If the next term could be greater than or equal to the current term, then it's just called an increasing function. It's not monotonic. So monotonic here is a keyword. Similarly, for the decreasing functions or decreasing sequences, if for all n, at each given n, the next term is less than the current term, then it's a monotonically decreasing function or sequence, and the next term could be less than or equal, then it's just a decreasing function. Okay, now one important concept for sequences is the limit, or what happens when the n goes very large, n goes to infinity. Okay, and it's called the limit of the sequence, which is the value of the sequence or the proximity of the sequence to a given number when n is very large. And as n gets larger and larger, the terms of the sequence get closer and closer to that number, which is called the limit of an, limit of the sequence. And here are some examples. 1 over n squared, when n goes to infinity or n gets very large, so the denominator gets very large. So 1 over a very large number is approaching 0. That's why we say that the limit of 1 over n squared is basically the limit of n squared is basically 0. Now the other case is the natural number, or the Neper number, natural number, and it can be actually defined as a sequence 1 plus 1 over n to the power of n. And basically what this happens is that as you increase the n, inside the parentheses or the base goes approaches 1, but it's always greater than 1, but then the power approaches infinity. So something greater than 1 to an infinite, if it was exactly 1, no matter what the power was, we always get 1. But the difference here is that the base is not exactly 1, it's approaching 1, but it's always greater than 1. And we know that if we have a number greater than 1 and we raise it to a very large number, it gets bigger and bigger. So there are two things here that are competing against each other. One is as the base is getting closer to 1, which potentially decreases the value of the whole sequence. But then the power is also increasing more and more. And because the base is always kept at higher than 1, the value of the sequence should increase and increase. So these two eventually cancel each other out perfectly, and the resolution or the final result is a number, natural number, which is 2.7 something. Now, in order to implement the sequence, it's very easy to implement it in Java. What I'm going to do, I'm going to use a functional interface. So basically an interface with just one method that returns the value of the sequence. So let's head to Eclipse. I'm going to create a new Java project called demo sequence. And here I'm going to create an interface and call it sequence. And I'm going to annotate it with functional interface, functional interface, okay. And then what I'm going to do, I'm going to add a method which is basically returns the value. So going to have a double, so the return type is double because our sequence is from integer numbers mapping to double numbers or real numbers. Double evaluate, and the input is some integer k. Okay, so the main difference between a function and a sequence is that the input is an integer number here, not a double number. Okay. And then if I want to test this, so let's create a class test sequence, and I want to have a main method. So let's finish this. So here I'm going to create a sequence. So sequence, so the approach 1 for creating the sequence is to just have a sequence like S1 equals sequence 1 equals new sequence. And basically what I'm doing here, I'm using so this is the approach 1 is anonymous class, so we're implementing as an anonymous class, and just we're overriding the evaluate method, so we're going to return 1 over k squared, k times k, for example. All right, and then I can do a sysout, system.out print line sequence evaluate at some point 2. And we get 0. The reason we get 0 because we're dividing an integer by integer, so I have to turn this to double. 0.25, which is 1 over 4, correct. I can remove this, just k times k, and then we get 4, 2 times 2. All right, so this is the first approach. What is the second approach? Is to create a new class or implement sequence interface. So maybe we have some other, so I can create a concrete class, sequence example. So maybe we are implementing a particular sequence that has additional properties, because in the sequence interface we are just evaluating or returning the value of the or defining the function. This is just defining the function of the sequence or the expression. But here, for example, we can have a class here, implement sequence, okay, and then we are forced to implement the interface method, and we have to override it k times k. But we can do other things here, for example, such as overriding the toString method. So we go to source, override implement. We are going to override the toString method, and here I'm just going to return k2 or something like ak equals k squared. All right, so here now instead of using anonymous class, remember that we could also override the toString method when we're creating the anonymous class, but it's not recommended to have a lot of overridden methods, because it just doesn't make the text look nice, right? It makes the text of the code look ugly. But the good thing is that we can always refer a class when implement a sequence by its object type sequence, by its interface name. So sequence sec2 equals new sec example, for example, and then we do a sysout here, and sec2 evaluate at 2. So if I put double, it complains because Java doesn't do automated casting or downcasting, because there is a potential for error here. So I have to return 4, yes. But what I can do, I can also do a sysout on my sequence, and this invokes the toString method k squared. Okay, so this is just expression for the sequence. So for sequences that you may usually use you can implement them as a concrete class, but keep the signature or the footprint of the class as a sequence by just implementing our functional interface. All right. But then the third approach that I personally use the most is lambda expression, or basically it's a way of functional programming. And what I mean by that is I can define a sequence, say integer k goes to k times k. All right. So because it's a functional interface, which means it can only have one method, and then or one abstract method. It can have concrete methods, default methods, or static methods. So k times k, so you understand that the input is k and the output is k times k. And then I do a sysout on sec3 evaluate at 2, 4. Okay, so these are 3 ways, but this one is recommended because when we are passing this to another class, we can just simply use this. Wherever we need to pass a sequence, we can write this kind of expression and invoke the function directly. So this is a good advantage. And so this is the main concept of sequences. And another thing is recursive sequences. This also happens a lot in engineering or physics applications. In the recursive sequences, there is a factor of recursion, and by that we mean that each term of sequence is depending or is defined by the previous terms, or maybe the next terms, basically other terms. So an, for example, a Fibonacci sequence, in each term depends on the last two terms. In a geometric sequence, each term is the last term times a constant number. So R here is a constant number. R is a constant number. Okay? For factorial sequence, each term is the last term times the index of the current term. So here n is not a constant number. N is not a constant number. So this is the main difference between a geometric sequence and a factorial growth or a factorial sequence. Here the coefficient here is not a constant number. Now obviously, in order to find these, we can go back recursively. So we have an equals an minus 1 plus an minus 2, and then we can write an minus 1 equals an minus 2 plus an minus 3. So we backtrack all these to some initial condition or initial point. So all these recursive sequences need some initial points or initial conditions, and it depends on how many terms are appearing in the definition of the sequence. So for example, for Fibonacci, I have two terms that are defining the next term. So I need two initial conditions, and the initial conditions are typically a1 equals 1 and a2 equals 1. For geometric sequence, I have one term that is defining the next term. So obviously I need to set the value of r, but besides that, I only need one initial condition, and we typically say the a1 is some number, okay, the first term. For factorial, the same thing. So we only have one term that is defining the next term. So we typically use a0 equals 1, and actually we cannot do this, because if I put n0 here, we can do this, because if we start from a0, then the next term is a1. a1 is 1 times a0. So a1 and a0 are potentially equal. So for factorial, it doesn't matter, because a0 is equal to a1 by definition. Okay? So that's one of the reasons we can say that 0 factorial is also 1 factorial. And 1 factorial is 1, and therefore we can define 0 factorial as 1, 2. But I mean, obviously the best definition is to start from index 1. So recursive sequences can in fact have closed form solutions. In fact, this Fibonacci has closed form solution, geometric sequence has closed form solution, and actually for geometric is very simple. an is just a1 times r to the n minus 1 power, and you can easily verify that. And there are actually mathematical ways to calculate the closed form solution, if it's possible to calculate the closed form solution for recursive sequences. So if you're writing a Java code for recursive sequences, if it has closed form solution, it's better to implement those, because it just saves time. Typically recursive evaluation is costs time and memory, But if we have closed form solution, it's just substituting numbers into the equation and finding the value, and that's the fastest way, right? But if the closed form solution is hard to find, then we can directly implement recursion in Java. And I'm going to head back to Eclipse and show it to you. So let's create a new class, recursive sequence. Okay, and we're going to have a let's call it Fibonacci, for example. So let's go refactor, rename Fibonacci. Okay, and in the Fibonacci we can have private basically double. I mean, in terms of Fibonacci, all terms end up being integer. So private int, let's call it f0 and f1. These are the two terms, and we're going to initialize f0 to 1 and private int f1 equals 1. All right, so the first two terms are equal, are set to the respective initial conditions, and then let's implement our functional interface, the signature of sequence, because we so implement sequence, and then we need to add the unimplemented method or override it, which evaluates at some point k. So when we do the idea is that when we implement recursion, basically we have to start with the initial conditions, which are these are stop conditions for the recursion. Okay, so initial condition is that if k equals 0, so if k equals 0, then we can return f0. Okay, else if k equals 1, we still return f1. All right, so these are initial conditions. And finally, we actually don't need to have an else here, because it first checks these two and it has a return, so the method ends up terminating or going back. But I'm going to put the else here anyways. So if k is not 0 and not 1, I need to implement recursion. And the way we're going to implement recursion is just calling the function again, evaluate at k minus 1 plus evaluate at k minus 2. All right, this is how we implement the recursion. Okay, so this is the Fibonacci, and it implements our sequence. So let's head here, approach 3, approach 4, and note that I could actually so because Fibonacci has a identity, has a fixed definition, so we could implement everything in a static way. So we call the class and the static methods instead of trying to instantiate. So in this way, first let's call this a recursive sequence. So I can use the signature sequence, the interface fib, and then it's a Fibonacci sequence and empty constructor. Okay, implement sequence. Well, let me see why it's complaining. Okay, so I was forgetting to write new. Okay, and then the signature, and we only want to evaluate this, so sysout or system out print line fib dot evaluate at 1, and then we can write a for loop for int I equals 0, I less than 20, I plus plus. We want to evaluate at index I. So now you see how the recursion happens. So we start with 1, the first term, the second term 1. As soon as it goes here in the evaluate method, basically it checks these two initial conditions. When these are returned, it returns the value, and then it goes inside another loop inside the evaluate. So it goes all the way down, and as you can see, if the number is large, going down in the evaluation function and then coming back pretty much takes a long time. So it's always recommended to implement, if we have a closed form solution for the sequence, it's better to implement a closed form solution. So here for the Fibonacci we have 1, 1, and then 2, 3, 5, 8, 13, 21. Now other sequences such as geometric, we can also implement that, but the question is, do I really need to create a class? Can I use a lambda? So lambda for recursive sequences. So let's say I create a sequence geom, and I want to go from k to something. So in order to do that, I'm going to go from k to some expressions here, and if k equals 0, I'm going to return or k equals 1. Let's start from the first term, is called 2, and then I'm just going to return, or let's just write an else, return what we want to do. We want to create a recursive. So 2 is the first term, and we know that at each k we have to multiply by the number. Let's say our the constant number is 3. This times evaluate, so we cannot call evaluate. Let's see if we can call evaluate function. We cannot. I call the k on this. So what did we do here? We created a lambda expression, but this lambda has a problem right now. So what we want to do with this lambda is be able to do a recursion right in the lambda expression. So in the lambda expression, we create a sequence object, and here we want to override the evaluate method. And in the evaluate method, what we can do is we want to have an initial condition and then some constant number times the evaluate method at some other point. Now the question is it possible to do that? And it should be possible, but I'm not sure if I recall how to do it. But for now, you can just instantiate a constant or create a concrete class, and basically just use the recursion in this fashion. Whenever you call the evaluate method, you check the initial conditions and then go inside the call the other evaluate method on the other terms. Okay, but if you have a, instead of recursion, if you have a definition or the definite expression for the sequence, you can definitely use lambda expressions. All right, so this concludes this discussion on sequences. Next we will have a look at series and what is the definition of a series and what are the, look at a few important series such as Fourier series, Taylor series. Thank you for watching. I'll see you in the next video. Hello and welcome to another tutorial. In this tutorial I'm going to continue our discussion on sequences and series, and in the last video we discussed what sequences are. They're just a simple representation of functions over the integer numbers, and then we discussed also a particular type of sequences which are recursive sequences, and now we're going to look at another type of sequences which is called a series. So series is basically a sequence that is defined as the sum over another sequence. So if AI or AN is my sequence, I can create a sum from index I equals k to n and call this S of n. So with this definition saying that my series has index n, it means that I'm fixing the initial index, which is k, and just I'm varying the final index n. Okay, so this sum basically means that I'm summing Sn is equal to ak plus 1 all the way to an. And if you're wondering how many terms are in this sum, it's last index minus the initial index plus 1. And the plus 1 is because both the last index and the initial index are included. If one of the end indices is not included, we have n minus k terms. If both indices are included, we have n minus k plus 1 term. Okay, and remember that I is the summation index. So when we use the sigma notation, it just we use some summation index which is I, and it runs from k to n, and the series S is defined over the last index n. Okay, so a series is a sum over the terms of a sequence. So if a sequence is given, then we can sum over its terms, right, from some number to some number. And typically k, the initial index, is 0 or 1, and n runs over the positive numbers 1, 2, 3, etc. So the sequence usually starts from 0 or 1 or 2, something like that. Now in order to evaluate Sn, obviously we have to calculate a first, all the terms that we need from the initial index to the last index, and then sum them up. Okay, now what you can see that there's an element of repetition. What do I mean by that? What I mean is that if I calculate S5 for example, and the initial index is 1, I have to calculate A1, A2, A3, A4, A5, right? Now let's say I want to calculate S6, then I have to calculate A1, A2 all the way to A6. But A1 to A5 were in fact calculated when I evaluated S5. So I do not need to actually recalculate them each time that I'm trying to calculate some S at some index, right? So what we can do, we can use some concept called caching, and which means that when for the first time I evaluate Sn, I'll try to save ak plus 1 all the way to an. All right, and then if I want to evaluate S at some other index, let's say Sn plus 2, when I start to look into the a terms, ak all the way to an plus 2, I try to see whether or not these terms, each individual term, has been calculated before or not. So caching means that the first time when A is calculated, just calculate and save it into some hash map or something else, a data structure, okay? And then next time I want to calculate the sequence, I'll try to see if any of those terms, A terms, have been calculated before or not. So if they have been calculated and saved, I just retrieve the values. I don't calculate them again. So this can in fact save a lot of performance, and this shows itself especially when we look at the Fourier series or series of functions, because then if I want to evaluate a function at say 1000 points, I do not need to calculate all the coefficients 1000 times. All right, now as just like sequence, there is a limit concept of Sn, a series. So when n goes to infinity, if the value of the sum approaches some number, we say that that number is the limit of the series. All right, and mathematically this means that when at some point n, for some large index n, the difference between each two terms becomes less than some arbitrary number epsilon, we say that the series is converging, and we can find the limit. If this doesn't happen, we always end up with some number, then we say that the series is diverging, okay? So, and then for example, one case is that if an is monotonically increasing, then series always diverges, right? And in fact, there is a lemma, or there is a theorem that says that the necessary condition for a series to converge is that the sequence approaches zero when n gets larger and larger. That's the necessary condition, not enough. Okay? And so there are other conditions that need to be satisfied. But if the limit of the sequence is not zero, we are sure that the series does not converge, okay? And if we want to calculate, so we can define the series as the sum, as a sequence, but then if we want to calculate the infinite sum or the value of the series or the limit, we can define plus infinity and negative infinity. And we can just use a enum type for such a thing. And the other thing is that obviously we cannot sum infinite number of terms, so we have to cut the series at some point, and for that we need to have a convergence test, or what is the tolerance or the error. Convergence test is basically defining the error of the evaluation. And we can have an absolute error or a relative error. Relative error is when the next term becomes less than 1% of the previous term, we can cut the series and consider it a convergence. Absolute error is when the difference between the two terms of the sequence of the series is less than the error, then we call it a convergence. All right? Let's head to Eclipse, and I am going to define an enum type. I call it limits, and here I'll have the infinity, like plus infinity, minus infinity, or positive infinity, negative infinity, positive infinity, and negative infinity, something like that. And I'm going to create a class called series. All right, and in this series what we are going to do is we are going to have a method called public double evaluate, or get value, for example. And here we're going to pass a sequence, and then we're going to have initial int. We have an integer for the initial index, and then int for the last index or the final index. All right, so final is a keyword, so let's call it last index. And then you can probably guess what we're going to do. We create a double value result, and then eventually we need to return the result. And in the simplest form, we just write a for loop. For int k equals initial, and then k less than last plus 1. Remember, we want to go all the way and include the last index, and k plus plus result plus equals sequence dot evaluate at k. All right, this is how we calculate the series, a finite series. So this is for finite series. And then let's go and test this. So I'm going to create a new class called test series, and I want to have a main method. And here I'm going to create a series. So the first approach is create a sequence and pass it to series. So sequence sec equals, let's call it sec1, equals new sequence, use the anonymous class, and then we need to implement the evaluate, and here I'm going to say k, or I don't know, 2k, and then we create a series object, series series 1, new series, and in the constructor we don't pass anything, right? And then double val1 equals series 1 get value. I pass my sequence and the initial, let's say from 0 to 5, and then run a system out.println val1. All right, let's see what happened here. So we created a sequence and we used the anonymous class approach. Remember that sequence is an interface and you cannot instantiate interface, but anonymous class allows you to do that if you implicit or explicitly override the value, the method evaluate, which is an abstract method. Remember, evaluate is abstract method in the interface, in the sequence interface. All right, and then we create our series class, and the series class takes care of evaluating the sum over some sequence from the initial term to the end term. Remember that both the initial, both ends of both ends of the sum or indices are included. Remember that, because in some languages such as Python, there are predefined functions. When you say create a distribution of integers from 0 to 5, the convention is to include the first index but exclude the last index. But here my convention is that I'm going to include both of them, because that's closer to the way we write the sigma on a paper, right? When you write from 0 to 5, you actually mean that the first term and the last term are included in the sum. So if I put here just k, and then we end up with half of it, 15, that is correct. And then if I put -1, it also works, because actually it doesn't work, because the for loop only goes from increasing, right? So if we want to be able to sum over the sum over in each direction. Basically, when we say 0, -1, we also calculate from 0 and then -1, -2. We can modify it here. So this is the sum evaluation. This is the check for proper limits or proper index values. By that I mean that we check that if initial is greater than last, then what we are going to do is we can probably define local variable init lst. If initial is greater than last, what we're going to do, say that init is actually lst. Init is the last one and the lst is init, right? We're swapping the otherwise we're going to say init is initial and the last is lst, and then here we put init, or basically lst is last and lst. All right, let's see this works. Yes, now if I say from 0 to -5, it should return -15. Okay, or if I say -5 to 0, it should return. Now what happens if the two indices are the same? Does it return -5? Yes. So 2, 2, 2. And the reason for that is we included both the initial and the last index. That's why we have last plus 1. So k runs over from the initial to last. Okay, but now the important thing here is that caching. So as you can see here, each time we evaluate the term, we can run into the problem of the fact that we have to evaluate all the terms of the sequence all the time, right? But this is not recommended. So what we're going to do, we're going to change this to static, because here this function doesn't have anything to do with class, right? We define the sequence, we define the initial and the last, and then obviously we get a warning here because we're accessing the series by an instance, but get value is a static method, and you have to access the static method via class, not the instance. So we have to use the series class. All right, in fact we don't even need this. I'm going to highlight it, and this still works, right? Get value sequence from here to here, and this still works, but this is not efficient. So what we're going to do is we're going to create a constructor here. So basically create an instance sequence, all right, and obviously it gets initialized to null, or we can specifically or explicitly set it to null. And then I'm going to have a constructor, and here I'm going to pass a sequence, and because I'm using the same name, I have to use the this reference to make sure that no shadowing. So no shadowing of global variables, because I'm using the this term. Okay, now I have this. What I'm going to do, I'm going to basically create a map or hash map from Java util, and it's an integer. And remember, you cannot use primitives in hash map. Cannot use primitives in hash map. Have to use use wrapper classes. So this map is basically takes track of which terms in this sequence have been evaluated. So it should be integer, which is the index, versus double, which is the value. So I call it cache. All right. And obviously, when I create the object, I'm going to also initialize it, and we actually didn't need to have a specific map, a specific hash map. We can just use the map interface, and I need to import it from Java util. Okay. All right. So what happened? We have the sequence. We have the cache, and now when we create something like this, and this is not static anymore, but here we don't specify the sequence because it's been given there in the sequence. All right. And I'm going to assume that it's not going to always, the initial is always less than index, initial and last. But what I'm going to do here, instead of doing this, what I'm going to do is put a if here. So here where caching happens, here is where caching happens. And what do I mean by that? We're going to say that if our cache contains key, and the key is an integer k, all right, if it has, then result plus equals cache dot get k. All right. So if the index k for the sequence has already been evaluated and it's in the map in the cache, then we just retrieve it from cache, and this is a hash map, so retrieval is very fast. Else, what I'm going to do else is now obviously I need to evaluate this, but then basically what I'm going to do is I'm going to evaluate the sequence. I get the sequence evaluate at k and put it in the map. Let's call it x, some local variable. We calculate it. All right. We put it in the map. We also add it to the result. Now what happens here? You can see what happens. So we do the caching. So if term or ak is has been evaluated before, then we just retrieve it. If this is the if first time, ak evaluated, put it in the map. All right. Let's see. We use the static version. Now let's actually uncomment this, create series 1, and in the series what I'm going to do, I'm going to create a lambda expression. So k times let's say k. So what happens here is that this is a lambda expression or functional. So we're passing the sequence to this, and now we want to see first of all this works. So sysout series 1 dot evaluate get value from 2 to 5. Yes, works, right? Both of these are working, right? But now let's make a comparison. Of caching versus not caching. So what I'm going to do, I'm going to write a for loop, I equals 0, I less than integer dot max value, I plus plus, and basically I'm going to time it, right? For the benchmarking, I'm going to time it, and in my mathlib library, my library on GitHub, in the utils, I have a timer. Okay, so you can just use this class, and in order to do that, I'm going to go to the build path of my project, and in the project I'm going to add a dependency on the mathlib. All right, and what I'm going to do, I'm going to create timer. I'm going to import it from mathlib. Timer1 equals new timer. All right, and then timer1 dot start, and each time I'm going to evaluate basically from 1 to, or from 0 to I. So we're going to sum this. All right, and then timer1 dot stop and sysout timer1. Let's run this to make sure it works. It is still evaluating. So 5,958 milliseconds. So it took about 6 seconds. All right. Now I'm going to basically copy this, and this time I'm going to create another timer, timer2 start. But now instead of doing this, I'm going to create use the series that we created, right? So in the here I'm going to say series 1 get value from 0 to I. Now let's see what happens here, and here we're going to have timer 2. Let's save it. So the first for loop is taking time, about 6 seconds. The second for loop is taking time. Apparently it's taking more time than. Alright, I'm going to maybe reduce the limit. So let's say 1,000, 10,000. (47 milliseconds), 803 milliseconds. So the overhead that we're paying here is that in this case, evaluating the series is actually much more efficient than caching and then uncaching, which means you're putting in the map, in the cache, and then retrieve them, because the sequence here is very simple. But if the sequence was defined in terms of something that takes time, let's say an integral function, and we will look at that when we look at the Fourier series. But if the evaluation of the interval takes time, then we want to use caching. But if the evaluation of the sequence doesn't take time, then better not to cache the sequence. So I'm going to write it here. So implement caching only if the evaluation of the sequence takes time, or basically it's a costly operation. And that's actually the case for Fourier series. So what I'm going to do here, I'm going to set a boolean here, boolean do cache, and I'm going to set it to false, and then we have a setter here, public void set caching flag, for example, boolean caching, do caching. This dot do caching, do cache equals do caching. All right. So, and therefore, what we're going to do, we're going to say if do cache, we're going to implement the caching thing, the caching algorithm here. Else, we're just going to basically get the result So if you're not doing caching, then we can just evaluate the sequence. And if I run this again, hopefully the result is yes, it's the same, because now we're not doing the caching. But we will see a case in the next lecture that when we do the caching, we actually need to we actually get enhancement in the evaluation of the function. All right. So I'm going to put a comment here. So the first timer for access via a static method without caching. The second is a second timer access via instance method, and here caching can be enabled. So right now caching is disabled and we get the same performance. But if we say that series 1 do set caching flag is true, so we add a flag here for caching, then this is going to take a long time, because putting to the map and then retrieving is not the efficient way here. Okay, it's actually less efficient than directly evaluating the sequence. All right, but for the cases when calculating the terms of the sequence is less efficient than reading and writing and reading from a cache, a map, it's better to do the caching. So in general, our series class is better to have this capability to be able to, so that we can turn the caching on and off. All right, and thank you for listening. In the next video, we will look at two specific series. One is Fourier series and the other one is Taylor series. I'll see you in the next video. Hello and welcome to another tutorial. In this tutorial, I'm going to continue the discussion on sequences and series. And to recap, we discussed about sequences, and we said that if you consider a dense function f of x, which with x being a real valued function and f being a continuous function, we get a dense plot of the function. Now if we evaluate f only at integer, or the integer numbers could be positive or negative, we end up with a discrete sequence of numbers or values for f. And we said that we call this a sequence. And the convention is that instead of using f of n, we use f sub n or a sub n. Okay, so n here can only be an integer number, and we said that the sequence can be increasing or decreasing, or monotonically increasing and monotonically decreasing. And then we said that one important property of the sequences is the limit of the sequence as n tends to grow larger and larger. If the sequence approaches a specific number, we call that the limit of the number, and we can actually have a mathematical way of defining whether or not a sequence has a limit, but that's not the point here. And these are just two examples. 1 over n squared if n goes to infinity approaches 0, and 1 plus 1 over n to the power of n when n goes to infinity equals e, the Neper number. And we said that we can implement a sequence as a functional interface, as we did previously. And next we talked about one important class of sequences, which is recursive sequences. And we said that in a recursive sequence, each term is defined as a function of the previous terms. And for example, Fibonacci, each term is the previous term plus the second previous term, an minus 1 plus an minus 2. And this is an example of linear constant coefficients recursion, and these type of recursions have indeed closed form solutions. We can find them. Geometric sequence, each term is some constant number times the previous term. Factorial, each term is the index at that term times the previous term. So here n is not a constant number, this coefficient. So this is a nonlinear recursion, okay? And then we said that initial conditions are required to uniquely determine the sequence at each given index. For example, for Fibonacci, and the initial conditions depend on how many terms, how many of the previous terms appear in the definition of the sequence. For example, in Fibonacci we have 2 of the previous terms, so we need 2 initial conditions, A1 and A2. Geometric sequence, 1 term only appears, so we only need 1 initial condition. Same as factorial, only 1 previous term appears, so 1 initial condition. And we said that it's easy to directly implement recursion in Java, okay? We just implement the recursion in calling the method that evaluates but then we need to also take care of the initial condition, the check for the initial condition or when the recursion ends. Now we said that recursive implementation in Java is typically expensive and costly. So if we can't find a closed form solution for the sequence, it's better to implement it via the closed form solution. And then we discussed the other important concept, which is a series. And series is by itself is a sequence, but that's a sequence that is constructed over the summation of another sequence, A. So A is also sometimes called the generating sequence, and S is called the series, okay? And typically the initial index of the summation is fixed, and then the final end index is where the series is defined over, right? And we typically start from the initial index is either 0 or 1. That's the typical case. And then we said that in cases where evaluating the series, evaluating the generating sequence A is costly, is expensive in terms of computation, we can do caching, okay? But if it's easy to evaluate the generating sequence, caching doesn't offer any improvement and may even worsen the performance, as we saw in the last in the previous video. But in general, when we if we deal with cases that we need to calculate these coefficients many times, then it's better to do the caching and save the coefficients. Because if I calculate S3, I need to calculate all the AIs from the initial index to 3, and then S4 from initial index to 4. But if I have already calculated the initial index to 3, I can just use them again. I don't need to recalculate them, unless recalculating is easier than caching. And the simple way to do caching is using a hash map. All right, a hash map pair of integer and double value. Integer is the index and double value is the result or the value of the sequence A. And then we said that series can also converge because this is a sequence, so we can also define a limit for this series. And if after some large n, the distance between the two terms of the sequence is less than a small value, we say that the series converges, and there is a convergence, and then the value of the limit is basically the value of the series, infinite sum. And then we said that if the generating sequence is monotonically increasing, this could in fact lead to a divergence. And the necessary condition was that for the generating sequence, the limit of the generating sequence must be 0 in order for the series to be able to converge. Doesn't guarantee convergence, but that's the necessary. So if the series converges, the limit of the generating sequence an must be 0. So that's one test to see if the series converges. We can find the limit of the generating sequence. And then we can implement a convergence test when one of the indices, here let's assume the upper index, the end index, goes to infinity, okay? And then the convergence test is basically how to decide when to terminate the sequence, the sum, and whether or not the sequence of the sums converges or not. So in terms of testing for convergence, the question is what criterion should we use for convergence test, right? And the problem here is that we don't know the exact value of the limit. So exact here is the keyword, right? We don't know what the limit is. So if I know what the limit is, then I can decide how far the value of the sequence is from that limit. And that gives me a sense of the error that I have if just I terminate the sequence at some given index, all right? So because we don't know the exact value of the limit, then we have to define the error without this value. So, and if we have the exact value of the limit, the absolute error of the sequence when we terminate at some index is the estimate at index n. Let's say n is where we terminated, minus the exact value. But if we don't have the exact value, what we can do as an alternative is to define an error sequence, okay? An error sequence is basically the current estimate where we want to truncate it minus the next estimate. So if these two are very close enough to each other, then we can confirm or assume that the sequence converges, okay? So, and this gives us a sequence for the absolute error of the sequence, each term relative to the next term, okay? Now similarly, the problem here is that maybe the limit is very large and these terms are also very large. Let's say the limit is 10,000 and this is 10,020 and this is 10,022, okay? So the problem is that the difference is still 2, and 2 could be a relatively large number. So when we're dealing with absolute error, we don't know what is the tolerance. Let's say eventually we want to truncate the series based on saying that, okay, the absolute error is less than something. But how do we come up with that something? That also depends on the magnitude of these estimates, right? 2, for example, 2 could be a large number, and let's say we want to have absolute error less than I don't know, 10 to the negative 4 or 5 or something. So a better case is relative error, and the relative error, again, if we have the exact limit, we define it as the exact absolute error divided by the exact value, which is the limit. Now obviously if the limit is 0, then we are in trouble, all right? So another way is to define a sequence of relative errors, which is the absolute error at position n, at index n, divided by the estimate at n. So this basically tells us how relative to the current estimate, how much the next estimate changes, right? So if it's 1%, it means the next estimate only changes less than 1%. And that could be a good condition for terminating the sequence and assuming that the series convergence, okay? Now, if a sequence convergence, or better to say, if the series convergence, the absolute error must go to 0. These two are and the relative error goes to 0. The relative error goes to 0 because the absolute error goes to 0, because that's the definition of the limit, right? The limit is when the estimate minus the exact value is less than some number, some small number. But again, we can prove that if the series convergence, the sequence of absolute errors must go to 0, and the sequence of the relative errors also goes to 0, okay? Now the problem here, one problem that we always have when we're dealing with numerical sequence is the speed of convergence. All right, this is a key here because that determines how fast we can get a good estimate, a reliable estimate of the limit. And there are numerical ways to accelerate the convergence of the sequence, but we're not going to talk about it here. All right, let's head to Eclipse and try to implement the convergence of series. So to recap, we implemented the sequence as a functional interface with only one function that evaluates the interface at a given integer. Here I changed the integer to long because long is 64-bit while integer is 32-bit. So we can go to larger integer numbers with long, okay? And then we create a series class, has a generating sequence, all right? We implemented the cache, which is a hash map of integer double. And we set a flag, do cache. And if it's false which is by default it is false, then we don't do caching, we just evaluate the sequence. And then here I added the double convergence tolerance. This is the tolerance we use for relative error. And then the max iteration, when we're doing a sum over infinite number of sequence, infinite number of indices, we should have a max iterations, right? Because eventually, even if this is not met after some time, some number of summations, it's better to just terminate it. So I put it by default 10,000, but we can change it. So the series class is defined by taking a generating sequence, and then if we want to sum over in the finite number of indices, we have a get value method that takes the initial index and the final index. But then here I implemented another method for only with initial index, with implies infinite sum, right? We're summing from the initial index to infinity, okay? So here I set the result to 0 initially and define temporary variable, and this temp is going to hold the value of the error, absolute error, which is basically the difference between Sn and Sn minus 1 is just the value of the sequence at that index, right? And k is the initial index, and I put it in a while loop while k is less than max iteration. So this is the first termination criterion. So we want to only sum over finite number of indices. We don't want to solely rely on a tolerance for convergence, okay? And in engineering, most of the sequences that we have, especially in physical problems, they usually converge relatively fast, so we don't end up with summing 10,000 terms, and that's a good thing. But so one thing here is to have the is to have the a stop condition based on the maximum times that we want to do the summation. And then at each sum, we evaluate the sequence, put it in our temporary, and then add it to the result, which was initially 0. So the result is accumulating the sequence. Accumulating Sn. Temp is basically just the value of An, right? A sub n and S sub. So result. And then next we check whether or not the sequence has converged. And if it not, then we increase the index and go back to the beginning of the while loop and try to add more terms, okay? And then, so what is this converge? Converge takes the error, which is the value of the sequence. Basically, if you recall, An is Sn minus Sn minus 1. Okay. So we take An and we take also Sn. And then we say that, okay, let's print the absolute error, which is the magnitude of temp, and let's say that the tolerance for the absolute error is 1 10 to the negative 8. And then the relative error, which is the temp, which is the absolute error divided by the current value of Sn, the result. And tolerance is the convergence tolerance, which we set it to 10 to the negative 10, okay? And then absolute error again is the magnitude of temp, the relative error is, and we can even put these in the beginning. And then here we just put absolute error and we put relative error, okay? And then we have to check for both the relative error and absolute error. So we said that sometimes relative error is better, but sometimes, especially if the terms of the sequence are small, it's better to have the check for the absolute error too. And if you also recall, I said that the necessary condition for the convergence of the Sn, the series, is that the limit of An, the generating sequence, which is our temporary or the absolute error, should go to 0. So we want to also make sure that this sequence goes to 0, An. Otherwise, the series doesn't converge, right? So checking for the absolute error is also necessary. So here I'm setting it to 10 to negative 8, and the tolerance for the relative error 10 to negative 10. All right? So this is how we can test for the convergence. Now let's head back and create a class to test this. Test convergence. And I'm going to have a main method. And let's create a static method. Public static void test1, and in the main method I just run test1. Alright, so in the test1 I'm going to create a series S equals new series, and the generating sequence I'm going to use a lambda expression, and I'm going to have k times k, 1 over k squared. So the series here, our sequence is a sub n is 1 over n squared, okay? And we know that this series converges, and this converges mathematically and converges, and the value for the convergence or the limit is pi squared over 6. We know that, we can mathematically prove it. So let's create the double value lim equals s dot get value, and I'm going to invoke the method with only one integer value or the long value, and from here I just put 1. So when you sum from 1 to infinity, so the series, series converges, and this sequence, the limit of the sequence is also 0, okay? So what we are going to do is system.out.println and limit equals plus lim, and also a sysout exact equals plus math.py times math.py over 6. All right, so let's run this. So we have max iteration reached, so the relative error never reaches 10 to the 10. All right, but the limit is 1.6448 and the exact value is 1.6449. So up to 3 digits, decimal point digits, we are good. So that's a good convergence. So that's why I actually have this also. So at the end of checking for convergence, we can see if the k has reached the max iterations or not. If it has, then we say that okay, max iterations reached. Now we have to make a decision on the convergence or divergence, and then here I'm going to say that if the absolute value of 10, so basically I'm looking at the limit of the sequence, which is the absolute error. If it's more than 10, so remember this sequence an must approach 0. If it's more than 10 after all these iterations, 10,000 iterations, I'm going to call it divergence. And then if I'm going to just math.abs is less than 1e minus 5, I'm going to call it convergence. So maybe let's put this here and I'm just add an else. Or else if let's say if this is greater than 10, we're going to call it divergence. And if something else, we're going to just say undetermined status for the series. All right. So we have convergence because even if the max iterations reached, we're calling it a convergence because the absolute error is very small. So we can confidently assume that it's a convergence. Now if I put, for example, k times k, so obviously this sequence diverges, and it's a divergence because max iterations reached. And note that the absolute error at the end is 10 to the 8, but the relative error is small, only 10 to the 4th. That's why the relative error may not be the best thing or the unique thing that determines convergence, unless we use a very large, very small relative error. That's why we should both test for the convergence of the absolute error. It has to converge to 0. If it converges to something else, the series doesn't converge. Okay. And so this is how we can determine. So we can use other tests. For example, let's test 2. And in test 2, I'm going to use another sequence. Let's say 1 plus 1 over n to the power of n. And we are going to check whether or not it converges. So we know that this series converges to, this sequence converges to E, right? And therefore, the series that uses an as its generating sequence must diverge. because the limit of an is not 0, it's e, the Neper number, which is 2.7. All right, so let's see. The sequence is math.power 1 plus 1 over k to the power of k. All right, and we're going to sum from 1, and we see what happens if we get a convergence or divergence. Now it says, okay, so we have to run test 2. Says that undetermined status of series. So we summed up to 27168, and the reason is that the absolute error is still small. So we see that the sequence is converging to E. So let's also print E. Limit of an math.e. All right. 2.718, 2.7181459. So the sequence is converging because the absolute error is converging to the value of the sequence. But then the relative error is 1e to the negative 4. So max iteration is reached, and then in the series, what we said that, okay, we said that if the absolute error is less than this, we say that the series converges. We call it a convergence because at least we know that the limit of the an is 0, it's close to 0. But then if this is greater than 10, we call it a divergence. So 10 obviously is a large number. We can say 1e negative 2, for example, or something like that. And then we end up with a divergence. So it depends on how you implement this, and depends on the sequences. And based on that, you can write your own criteria for convergence and divergence, right? Okay, thank you for listening. I'll see you in the next video. Hello and welcome to another tutorial. In this tutorial, I'm going to discuss the concept of Taylor series and how we can construct them. So we discussed sequences and series, we discussed the convergence of series, and now assume that we have a smooth function of one variable x. So we have f of x, and this is a smooth function, which means its derivatives all exist. First derivative, second derivative, it doesn't have a weird discontinuity or something at some point, okay? It doesn't have a sharp edge, so its first derivative is available, is defined, and also we assume that higher order derivatives are also known. So in general, it's a smooth function. Now we can find a polynomial at the proximity of a given value for x. Let's call it x0 at the proximity of a point of interest. So x0 is the point of our point of interest. Let's call it point of interest. Okay. We can approximate the function with a polynomial. Okay. So polynomial expansion at a given point, and it's based on the derivatives of the function, first order, second order, third order. All right. So this is a polynomial. These coefficients are constants, and these terms x minus x0, x minus x0 squared, these are the terms that depend on the x, and this is only valid in a proximity of x0, in a neighborhood. Okay. And this obviously we have to truncate it at some point. So it's not an infinite polynomial of the infinite degree, right? We have to truncate it because we can't just numerically do infinite series, all right? And so therefore this locally approximates the function. And one example is the exponential function at x equals 0. E of e to the x is from 0 to infinity, n factorial, x of n, x to the nth power divided by n factorial, 1x, x2, x3 over 6, etc. And then there are different ways of implementing this. One is we're going to define the function using our symbolic math library that we developed in the past, and then call the diff function on each function, and then call the diff function multiple times basically. So here call diff multiple times, this diff function multiple times. Another way is to numerically evaluate higher order derivatives at each point. We will get back to it, and there are different methods like accelerated ways of calculating derivatives, which is called Richardson extrapolation. We will get back to this when we look more into the calculus, but for now we're going to use our symbolic class. Okay, so how are we going to do this? So we already are familiar with the concept of the sequence and the series, right? So this is a series, and the sequence is x minus x0 to some power, and then the order of the derivative is that power. And then we're going to use the polynomial class because we know that the result is going to be polynomial. So let's head to Eclipse and create a Taylor expansion, for example. And what I'm going to do, I'm going to say that we have a function f or func, and then in the Taylor expansion for the constructor takes a function f or func, and then I'm going to assign it this dot func equals func. All right. Now at the moment it doesn't recognize the function, right? It assumes, so in order to tell it where if you recall, we had a project in the workspace, symbolic math, and we implemented some basic mathematics or some basic elementary functions, right? So in order to tell the Java to be able to find this function, I'm going to give this project a dependency. So we go to the build path, configure build path, and in the projects I'm going to add a symbolic math. Okay, and after this, now we are able to import this function from symbolic math. Okay, now maybe to recap, I'm going to recap on the function, I'm going to create a main method. And if you recall, we said that what we can do is we can use the function space, and we defined elementary variable x, and then we implemented the methods that represent the composition of elementary functions. So let's do the import static function space, everything, and here let's say function f1 equals x or sine of x, and then if we do the sysout f1, it's sine of x, we calculate the value, with the get value method at math.py, or just pi if you recall. We duplicated the pi in the function space, but it's as a constant function, right? So we can't use it here. We have to pass a double math.py over 2, and this one returns 1. If it's pi over 4, 1 over a square root of 2, it should be 0.707, right? And we had another function, the diff, that we're going to use, right? The diff method. So sysout f1.diff, and this returns a function that is the diff derivative of the original one, which should return a cosine, 1 times cosine. That's correct. And then we did the operator overloading. So if I do function f2, 2x plus f1, and do a sysout on f2, I should get 2x plus sine of x. 2x plus sine of x, okay? So this works. And then finally, let's check the differentiation. Also works on the operator overloading, f2.diff. So we get the derivative of 2x is 2, the derivative of sine is cosine, and there's a factor of 1 here. Alright, so this was the recap. Now in the Taylor expansion, the other thing that we need is polynomial, right? So in order to do to find the polynomial, if you recall, in the other project demo polynom, we developed the polynomial, okay? And the polynomial takes an array of doubles to construct the polynomial. So what we're going to do here, we are going to calculate all the derivatives from the 0th order, which is the value of the function, all the way to the nth derivative, and then create a polynomial. So in order to do that, I'm going to also give a dependency, go to the build path, give a dependency on the demo polynom. I'm going to remove the dependency on the mathlib. We're not going to use it. And this is going to complain because we use the timer class here, and the timer class is from the mathlib. Alright, so we have the polynomial, we have our functions here, some elementary functions with operator overloading, so we can create more complex functions. So in the Taylor expansion, what we are going to do is we are going to set a method public polynomial get series and int n, for example. So the order is n. So what we are going to do, so it doesn't recognize polynomial, we have to import it from the demo polynom project, and this is just finding Taylor series from up to degree n. Okay, so the degree is n, so we're going to create a polynomial, which is our result, new polynom, and we're going to pass a null. Remember, this creates a 0 polynomial, but we also have to define a coefs, which is an array of doubles, and it's going to be, so the degree of the polynomial is n, so we have to have n plus 1 for, and then we write a for loop for int I equals 0, I less than coefs dot, or I less than coefs dot length I plus plus. What we are going to do, if I equals 0, coefs I equals func dot get value at I. Alright, else we need to differentiate n times. So differentiate n times, and eventually we're going to return this result. What one thing that we need to be careful is, if you recall, we define the coefficients for the polynomial from the 0th term to the highest degree. So the last term, last index of the coef is the coefficient of the highest degree, and that's basically consistent with our definition here. So the 0th coefficient is the constant term, the first coefficient is x minus x0, the second is x minus x0 squared. So what we need to also specify the point, right? So we are going to give it a double x0 and an int n, all right? And then we have the coefficient, so let's do this. Now, I mean, because of this initial point, calculating the coefficients is not easy, because this is not exactly the coefficient of the polynomial, right? Because we have these other terms. For example, x minus x0 squared creates 2x times x0, right? And that adds to the previous term. So let's just, instead of doing the coefs, let's start with the 0 polynomial, new polynomial, null. All right, so this is just this is p of x equals 0, and then we're going to, from 0 to n plus 1, from 0 to n, right? I from 0 to n. If I is 0, we do the result equals result plus func value, we add the constant to the polynomial. Otherwise, we're going to differentiate n times and then add to the result, and what we're going to add to the result is actually x minus x0 to some power I, right? So what we are going to do is we're going to, let's remove this and then remove this recap. What I'm going to do, I'm going to from the polynomial import the static one. Now if you recall, in the polynomial we had this x, our base polynomial, right? And note that the operator operators have been overloaded for polynomials, right? So differentiate n times to find the, for k equals 0, differentiate basically I times. For k equals 0, k less than I, k plus plus, we're going to, so let's define a double coef is 1, and then coef times equals func dot diff, basically func we take the different derivative, and obviously we need to first make a copy. So because this just destroys the, okay, function func copy equals func, and this is these two are currently pointing to the same object, the object references, but we destroy the func copy and differentiate it n time. So we differentiate it n time, put it back in the copy n time. All right, so okay. Now after we differentiate n times, we're going to what we're going to do is we're going to create a polynomial. So we're going to add it to the result. The result equals result plus fun copy get value at point x0, right, times x. If you recall, x is coming from polynomial x minus x0 to some power, so that's the other thing. So we're going to create also a polynomial here, p equals new polynomial one. This is just p of x equals 1, and each time that we do the diff, we also p equals p times x minus x0. We also accumulate these multiplications, and then eventually we add the result, something like this. Okay, so let's recap what we did. So we're defining a method get series, and we're giving the initial so basically this is the initial or the point. This is point of interest. This is the degree of Taylor series, degree of our polynomial, and it returns returns the Taylor series of the function. All right. So we defined a zero polynomial, and then if the degree is n, we have to go from 0 to index n. That's why this is n plus 1. If it's 0, we don't need to do any differentiation. It's just the value of the function. And then we copied this function into a new one. And then we also created a one function because we want to construct when to differentiate the function n times. That's why we have this inner loop. And then we also need to create x minus x0 to the power of I, right? I times. That's why we have this one polynomial and then multiplied by itself, all right? And then eventually we add the result, add to the result, right? So we calculate the ith derivative at x0, and we calculate x minus x0 to the I, and then add it to the result. Okay. All right, now let's test it. So class test Taylor series or Taylor expansion, and we want to have a main method here. I'm going to create a public static void test1, and we're going to run test1. All right. In the test1, I'm going to create a function f1 or f, let's say, equals let's import static function space everything, and then let's import the function. Let's say sine of x. Or first of all, just x, right? Let's just see what happens when I do x. And I'm going to create a Taylor expansion, TE, new Taylor expansion of f, and then polynomial p or Taylor is TE dot get series. Let's say we want to add 0, and we want to go to third term, and then sys out Taylor. All right, let's see what we get. we get 0x cubed, 0x2, 1x plus 0, right? So we are getting the Taylor series. Taylor series, or P of x, is just x, which is correct. Okay? So let's do another test. Test 2. This time let's go plus 2. And we're going up to the third term. So we have 0x cubed, 0x2, 1x plus 0. Okay? And maybe let's also do a sys out on the f itself. We have x. Oh, that's because we're doing a test. Okay, test 2. Let's run. We have x plus 2 and we get 0x cubed, 0x2, 1x plus 2. Perfect. And then let's do test 3. Here I'm going to do, let's say, sine of x and up to the third term. So it should be x minus x cubed over 6. There is no x2, right? So let's see what happens. Minus x cubed plus 0x2 plus 1x plus 0. Now the question is, why is the coefficient is not 6? What happened? What went wrong here? And we are calculating the in order to do that, let's go back to test 2, but let's add a coefficient 3x plus 2, 3x plus 2. So that works. We have sine of x, which returns sine of x, and in the sine of x, if it's diff, we return cosine. Otherwise, we implement the chain rule and return a cosine. So the differentiation is correct. For test 3, minus x cubed plus 0x2 plus x plus, so we're okay, so that's because I forgot. So there is something that I forgot here. There is a 1 over n factorial also missing here. So the coefficients are f of x 1 over 1 factorial here, and then 1 over 2 factorial here, and 1 over 3 factorial here, and etc. So the coefficients are missing. So not only we have to implement the function n times the polynomial, and we also have to have the double factorial or coeffactorial. Let's just call it factorial. Okay, and it's going to be 1, and factorial times equals so it goes from 0 to, so we have to multiply it by k plus 1. So basically this means that this multiplies 1, 2, 3 all the way to I, right? Which is I factorial. And then what we are going to do is 1 over factorial times func All right, so this is the correct way. So we have 1 over factorial and then the value of the nth derivative or ith derivative times the polynomial. All right, that's correct. 1.1667 x cubed plus x plus 1. Let's make sure that the other tests are also correct. We have test 1, which is x. Okay, and maybe let's make it a little bit more fancy. F of x equals plus f Taylor of x equals plus Taylor. And again, the beauty of this here is that we already have a good class for polynomials. We already developed a relatively nice symbolic math, which is relatively fast, so no problem there. And we're just taking advantage of both of these two projects and then creating a Taylor expansion. And so let's run this again. X is just 1x plus 0. Okay, so in the test 4 I'm going to do cosine. So for cosine we know that it's 1 minus x over 2 plus x to the 4 over 4 factorial and minus etc. Okay, so up to the third term we should get 1 minus x squared over 2. Let's run test 4. Let's update these and also update this. Cosine is minus x cubed, so no x cubed, minus 0.5 x squared, which is correct, plus 0x plus 1, which is correct. Now if I continue to the 5th power, I should get 1 over 24 x cubed, x to the 4. So x fifth is 0, x to 5, x4 is 1 over 24, x cubed is 0, minus 1 over 2x2 plus 1. Okay, and then now the Taylor series also add up. So test 5, we're going to do a third of to the third term, sine of x plus cosine of x. So sine only has x minus x cubed over 6. Cosine has 1 and x squared over 2. So we should get basically 1 plus x minus x squared over 2 plus minus 1 minus x squared, 1 plus x minus x cubed over 6. So if we run test 5, so the function is sine of x plus cosine of x. So minus 1 over 6 x cubed minus 1 over 2 x 2 plus x plus 1. So this is correct. Correct. Now the other thing that I'm going to show here is I'm going to plot these functions and try to see how close they are to their so let's plot and compare f of x and Taylor expansion. So this function, this is Taylor, we have the Taylors, and in order to plot I'm going to use a class that is basically a wrapper for the J-free chart for plotting in Java, and we will get to the plotting in more details, but for now I'm just going to use the class which is called MATLAB chart. It's in the plot package in the mathlib on my GitHub. So MATLAB chart, fig, new MATLAB chart. Okay, At the moment it doesn't recognize it, so we have to give it a dependency, give the build path a dependency on the mathlib. Okay, and then we have to import it from mathlib. And I'm going to create an array of values x and use math utils in the util package in the mathlib, math utils, and call the lean space function. This is exactly the function you use in NumPy in Python or MATLAB. So the start is from, let's say, minus math.py. I'm going to use 10,000 points, 1,000 points. Double func. These are the f values, f vals, or func values. Func vals is I'm going to use another class, array func dot apply, and it takes a interface, a functional interface, and an array, which is x. Now array func is in the func package. It's just basically a for loop. So you give it an interface, a functional interface, which defines a real function and just runs the for loop and returns it. So in order to create this functional interface, I'm going to say that, okay, t goes to basically f.getValue at t. So I'm creating a lambda expression based on the function that I have, all right, sine plus cosine. And eventually I want to say that fig.plot x and func vals with color B, for example, and then I'm gonna render the plot and I want to run it with a flag true, boolean true. Okay, so this is the value, and I want to do a Taylor vals. Array func apply. Here t goes to the polynomial, which is Taylor dot evaluate at point t and over the array of x. And similarly I'm going to plot Taylor vals with red. Alright, so let's run this, and it doesn't show because I mentioned this in one of my videos. You have to go to the run configuration when you are on Mac. In order to run a swing component, you have to make sure that you remove the check for this flag. Okay, now if you recall, we are expanding at let's also give it some label. So fig.x label is x, and fig.y label is f of x, Taylor of x, or we have to put this after rendering the plot. Okay, so we are expanding at around 0. Okay, and you see that the Taylor expansion to the 5th term is to the 3rd term is relatively close to the value of the function, but as we get away, you see that the values are not exactly the same. They get away from each other. So this blue curve is the actual function, and the red curve is the Taylor expansion to the 3rd term, right? Now if I increase the order, so this is the 3rd term, let's go to the 6th term. Now as you can see, it's very interesting that now it converges or approximate the function to a much wider range of x values around 0. Okay, so the more you increase the function, the more you increase the order of the Taylor, the number of terms in the Taylor series, basically the wider the range is that the series convergence or approximates the value of the function. See, the error is very small, so sixth order term, sixth degree polynomial is definitely a good approximation for sine of x plus cosine of x around 0, and it covers from -2 to 2, for example, which is a wide range, and the error is still very small. All right. Okay, this is the topic of the Taylor expansion. Thank you for watching, and I'll see you in the next video. Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on sequences and series, and let's just do a quick recap of what we have talked about so far. So in terms of sequences, we said that sequences are essentially functions, and but they are on a discrete axis, so their variable is a discrete integer. And in terms of Java, the integer could be int variable or long variable. Okay, and then so it's basically a function, but we usually don't denote a discrete function f of some discrete variable with f of n. We typically denoted by some a, b, or anything, some symbol or a variable with a subscript of n. Okay, and again, the an, the value of this function, can be real or complex. Here I'm going to focus on the real number, so the function is real, and the index can be negative, 0, or positive. We typically look into the cases where the index starts from 0 and is positive, or it starts from 1. These are two mostly used cases. All right. So one example is 1 over n squared. This is a sequence, and then we said that there are typically two families of sequences that have a unique behavior. One is monotonically increasing, which means increasing the n will result in a strictly increasing behavior for the sequence, and just increasing means the next term can be greater than or equal, and monotonically decreasing means that the inverse of this statement. So each term, as we increase n, each term gets strictly smaller and smaller, and just decreasing means it can be equal or less than the previous terms. All right. And then we said that for the limit of a sequence, the definition is that what happens to the sequence as n goes to infinity, and we just calculate this using the rules of the limits. It has a formal mathematical definition, but here, for example, 1 over n squared, when n goes to infinity, obviously goes to 0. And then the limit of 1 plus 1 over n to the power of n, when n goes to infinity, the base goes to 1, but the power goes to, but it always stays above 1. So anything slightly above 1, when you raise it to infinite power, it should give you infinity. But because the base is approaching 1, these two kind of cancel each other out, and the key here is that they cancel each other out at the same rate. Therefore, this limit exists, and it's just the Neper number or the natural number E. All right, or sometimes this is also called Euler's number. So Euler's number. And we said that in terms of sequence, the best way to implement it in Java is using a functional interface, because then we can pass it as lambda expressions, and it's a very convenient way to do it. And then we said that we can do recursion for sequences. A lot of times we define a sequence based on a recursion, and it could be a simple or linear recursion, which means that all the coefficients are constant numbers. For example, Fibonacci, an equals an minus 1 plus an minus 2. Geometric sequence, an is some constant number times the previous one. But there are some non-linear recursions where the coefficients actually depend on the index. For example, factorial an is n times n minus 1. So this coefficient is changing each time we calculate a term. And then we said that for recursion, obviously we need the initial conditions so that we can start from the initial terms and then evaluate the next terms. And based on how many recursive terms we have, we need those many initial conditions. For example, Fibonacci has 2 recursive terms, so it requires 2 initial conditions. Geometric sequence has 1 recursive term, so we only need 1 initial condition. And these recursive sequences can in fact have closed form solutions, and it's always best to calculate the sequence based on their closed form solutions. It's much easier to program it using recursion, but recursion is always not the best case, because in Java you have the method stack, and then going into the stack deeper and deeper and then have to coming back, it just adds a lot of overhead in terms of computation. All right, but there are ways to mitigate that. One of them is memoization, and you can just look it up. Memoization is a great way of increasing the performance of the recursive calculations. For example, one famous example is just Fibonacci. So if you just look it up, you can see how memoization works for recursive sequences. And then we said that most of the times engineers and physicists deal with a particular type of sequence, which is basically the sum of the terms of another sequence, and we call that a series. So a series is basically, or the partial sum of a series is when you sum another sequence from some fixed index, which is typically 0 or 1, to some n, and this n is the variable. Okay, so let's say k is 0 here or 1. I from 0 to n of ai is sn. All right, so we sum over this sequence a and get another sequence, and in fact this is some sort of sequence transformation. And what happens is that you take a sequence, do some operation, algebraic operation on it, and then you create another sequence. That's called the sequence transformation. And series is one way of sequence transformation. And we said that caching or memoization helps with increasing the performance of calculating. And what it means is that let's say I calculate S0, S1, S2. If I want to calculate S3, instead of calculating all the terms of A, I can save S2 and just add term 3, and then calculate A at 3 and then add it to the previous term. I don't need to, if I want to calculate S1000, if I have already calculated S999, then I can just use that value and add it to 8000. All right, this is again memoization or caching. And then we said that okay, this partial sum is another sequence, so we can ask what is its limit, and the limit of this partial sum is called a series. So series is the limit of a sequence which is generated by summing another sequence over some finite number of terms. All right, and then the limit exists if the difference between two consecutive terms gets smaller and smaller as n gets bigger and bigger. And then the necessary condition is that in order for the series to converge, or in order for the limit of this partial sum to exist, this sequence A must have a limit of 0. If it has a limit anything other than 0, the series doesn't converge. So that's a necessary condition. And then we said that numerically we can try to implement some convergence tests, because we cannot sum over infinite numbers of terms. Okay, so test for convergence, we discussed this. We can define the convergence in terms of an absolute error or absolute error for the sequence, because most of the time, or almost all the time, you don't know the exact value of the limit. So you have to you have to define your error based on the behavior of the sequence, right? This is what you have. And then you can also define a relative error. and then look at the speed of convergence. All right. One of the very famous series that we talked about was Taylor series, and we implemented that in Java, and we said that Taylor series requires the calculation of the derivative of f some many times. Each term n of the sequence requires the nth derivative, and then we discuss how to do that. But then here's the new topic, which is called convergence acceleration. And the idea for convergence acceleration is that most of the time, if you have a series and you just want to, if you have a sequence and you want to find its limit, the sequence has a very slow convergence, which means if you want to get a good approximation for the limit of the sequence, you have to evaluate the sequence at a very large number, and that sometimes is not a good idea, especially when you're dealing with series, because if this series has a very slow convergence, I have to let's say evaluate it at n equals 1 million. That means I have to add 1 million terms of this sequence together, which is not a good idea. All right, so somehow we want to increase the rate of convergence of this sequence, which means we want to get the same accuracy but adding summing less and less numbers of the terms of this sequence. And typically the way we do it is we define a sequence transformation, and by that, first we have to define what is the accelerated convergence. So consider that we have a series an that converges to A, and then consider that we apply transformation to this an series and create another actually this has to be a sequence an that converges to A, and then we construct from this initial sequence an a new sequence bn that also converges to A, but has the property that the limit of bn minus A divided by an minus A, n goes to infinity, is 0. Okay, if this condition is met, then we say that bn has a faster convergence rate than an. If this is any number but 0, then we say that bn and an have the same convergence rate. If the limit is defined such that bn minus A divided by an minus A to some power, let's say power of 2, is 0, we say that the convergence of B is quadratic when compared to A. All right, so if this number is not 0, bn and an have the same convergence rate, and that transformation that we used doesn't do anything better. But if this limit becomes 0, this sequence bn converges to the same limit as A but with a faster convergence rate. Now let's look at one example. So let's say bn, one example is bn equals, for example, half times an plus 1. Let's just format this correctly. All right, so this is one example. And in this example, what you see is that basically if A converges to capital A, then the limit of this is half times A plus A, which is A. So Bn also converges to A. So if An converges to A, Bn also guaranteed to converge to the same number. But if we calculate this limit, Bn minus A divided by An minus A, we see that what happens here is that this number is because when n goes to infinity, an plus 1 and an are pretty much the same, right? Because n is very large, or n is much larger than 1. So bn becomes just half times an plus an, which is an. And this limit becomes 1, right? This number becomes 1. That means that this transformation of sequence of an into bn has a linear or has the same convergence rate. So it's not useful to do this transformation. It just has the same convergence rate as A. So it doesn't help at all, right? Now, most of the time we do the transformation on a sequence because we are calculating a series of that sequence. So here, this is from Wikipedia, and it's the series acceleration. And it says, in mathematics, series acceleration is one of a collection of sequence transformations. So we take the sequence and then transform it for improving the rate. So basically, this sequence is the partial sum sequence. So to remind you again, it's this Sn, right? We want to calculate the limit of this sequence, which is the series over this A sequence, right? We start with this, we create a new sequence, and then we want to calculate the limit. But most of the time, this sequence has a very slow convergence rate. So we are trying to find transformation to apply to this Sn, which is the partial sum of the series, to accelerate the convergence, which means we want to calculate at a very smaller index for n and to get a good accuracy. All right, so it's a sequence transformation for improving the rate of convergence of a series. So take note of these keywords. Techniques for series accelerations are often applied in numerical analysis, where they are used to improve the speed of numerical integration. So that's one use case, because when we calculate numerically calculate an integral, we divide it into some sub-intervals, we create a series, and then let the n goes to infinity, right? So numerical integration is an example of a series, and we want to calculate the limit. Series acceleration techniques may also be used, for example, to obtain a variety of identities on special functions. Thus, the Euler transform applied to the hypergeometric series gives some of the classic well-known hypergeometric series identities. So Euler transform is one of the examples of the sequence transformations. Now here I have listed some of the famous or most commonly used transformations. And before looking at them, let's define two things. One is the difference of a sequence. We said that a sequence is a discrete version of a continuous function, right? And for continuous functions, we have something called derivative or differentiation. For sequences, we have a discrete analogy to that, and it's called a difference. Difference, let's use the symbol delta, and so the difference of an is an plus 1 minus an. So immediately you can see that this is some sort of transformation, because we can define another sequence bn, which is delta an. All right, and we can calculate that sequence at any n, right? So this gives rise to another sequence, which means that this delta is just a very simple transformation of the sequence. And most commonly, this difference is defined for a forward case, where delta an is an plus 1 minus an. But we can similarly define it for a reverse case or reverse difference. So the first one is called forward difference, the second one is called reverse difference, and let's show it by delta bar, which is an minus 1, okay? Now, having that in mind, the binomial transformation takes a sequence an and creates a partial sum sequence Sn, which is defined from index 0 to n minus 1 to the k, the combination of k from n times ak. So remember, we're transforming an sequence into Sn sequence. All right? Euler transform takes an alternatively changing sign of a sequence that has also a factor of minus 1 to the n. So its sign changes alternatively and transforms into another sequence, minus 1 to the n Sn. All right? And the definition is this: if we are calculating the series over this minus 1 to the n an, we transform this sequence into minus 1 to the n delta na over 2 to the power of n plus 1. And this delta na, as I mentioned, this is another sequence. So we are calculating it at 0th, or the first term of the sequence, all right? and divided by 2 to the n plus 1. So you differentiate or calculate the difference of a n times and find its basically first term, zeroth term, or you can say that I calculate the difference of a0 n times. That's another way of looking at it. So this is another way, and these two are basically have the same limit, but this Euler transform version has a faster convergence rate. All right, and there are two famous nonlinear transformations which are very famous. The first one is Aitken transform, which is also called delta squared process. So for Aitken transform, just note that these Aitken and Shanks, these are nonlinear transformations. And the Aitken's delta squared process is something like this. Let's denote the sequence of xn by capital A. And then ax is the transformation of this sequence, which is another sequence. Let's call each term ax sub n. So ax sub n is xn plus 2 minus the difference, or the first difference of xn plus 1 squared, divided by delta squared of xn. Now, what is the continuous version of this? For a continuous function, it's like f of x minus f prime squared over f double prime, something like that. All right. So the first difference squared divided by delta squared, and delta squared means, as I mentioned again, delta an is the first difference, which is another sequence, right? Delta an. So you apply a delta over this new sequence, delta an. It becomes delta an. All right. And then this can simply written as this. The axn is xn plus 2 minus xn plus 2 minus xn plus 1. So this is the first difference for xn plus 1 squared, divided by xn plus 2 minus 2 xn plus 1 plus xn. What I want you to notice here is that calculating the Aitken transform of x at index n requires the knowledge, or requires the calculation of xn, xn plus 1, or xn plus 2. Okay. Now the next one is Shanks transform, and the idea here is that if I want to calculate a series from, let's say, 0 to infinity or 1 to infinity or any index to infinity of am, so small a is given, and let's say this series converges. So we already know that it's a convergent series, and let's say it converges to capital A. So we create a partial sum sequence from A. So basically this is our first transformation, going from am to capital An, right? We take this sequence and transform it into capital N using this partial sum. And now in order to so this sequence capital An has, let's say, has a slow convergence rate. So we can define the Shanks transform on An, and it's pretty much Aitken transform applied to An minus 1. That's the same thing. So San is just An plus 1 minus An plus 1 minus An, which is the first difference of An squared, An plus 1 minus 2An plus An minus 1. This basically is the Aitken transform applied to xn minus 1 or An minus 1. All right. So in order to calculate the Shanks sequence, Shanks transform at index n, we need to know or calculate the A at n minus 1 and n plus 1. All right. So basically there's not much difference. But then the idea here is that once we are going to calculate the series of the small a using the partial sum sequence, we can apply Shanks transform as many times as we want. So we can apply Shanks to An, it gives us another sequence, and then we can apply Shanks to this new sequence. So it's typically denoted by Shanks squared or s squared, which is s Shanks of An, and s cubed is Shanks of Shanks. All right. So this is how. But then the question is, how do we implement this in Java? And the first approach, I think, is the best approach, and because we already defined a sequence as a functional interface. All right. So instead of defining a class to implement this transformation on this sequence, because remember, when we apply a transformation, one of these transformation to a sequence, the results should be also a sequence, right? For even a simple difference, when you apply it to the sequence, it's another sequence and you calculate it at any given n, right? So we take our functional interface sequence object and we want to keep it as a functional interface, but we want to apply new methods to calculate this transformation. And the way that Java allows that, to evolve an interface but keeping it again as a functional interface, because remember, functional interface must only have one abstract method, which is where we evaluate our sequence. So we use default methods. All right, default methods allows us to add more methods, more capability to a sequence, basically evolving that interface without breaking the contract of the sequence being a functional interface. All right, so let's head to Eclipse and I'll show you how I've implemented this. So in our sequence project, we had a sequence object, which is a functional interface. All right, and then a series class, which basically takes a sequence and then sums over some index that we provide from the initial index to the last index. And here I've changed the int types to line types because it just takes more memory, but it's better to have it as line, right? Just to be safe. And then so this was the main idea, but we also implement something called caching. So we calculate the sequence at each point and put them in a map and then retrieve them at another time. All right, so let's not worry about caching at this point, but these are our two main classes. Now in order to evolve this interface, we already have this functional interface. So this is our public abstract method, which is called evaluate, and takes a long variable k and basically calculates ak. So k goes to ak. All right, and again, we want to only have one public abstract method to be able to use it as a functional interface and use it as lambda expressions. So what I've done here, I've added a default method here called, and the return type is a sequence, because when I apply the difference, the difference is like a sequence transformation, right? The forward difference, and it has to return a new sequence, right? And the good thing here is that having this only this single public abstract method allows me to just write it as in a very convenient way using lambda expression. So when I calculate the difference, it creates a new sequence, and basically n goes to, I call the evaluate function at n plus 1 minus evaluate at n, right? Again, this is a lambda expression, which means the return type is automatically a sequence interface. Now what I could do, I could also call the this over this method, the evaluate method, but it's not necessary. So this is how I transform a sequence using the difference. So difference is defined as a sequence transformer and it returns a sequence. For 8can, the same thing. So I add a new default method called 8can, and the return type is a sequence. All right, and again I use a lambda expression. So n, it takes the nth term of this current sequence and calculates it at n plus 2 minus, this is the first difference, n plus 2 minus n plus 1 squared divided by n plus 2. So this is delta squared, n plus 2 minus 2n plus 1 plus n. And I'm just calling the evaluate method, all right? And then for the Shanks transformation, I could just call the 8can, and basically I could write something like this. So I could say return n goes to 8can, or basically call the method 8can at because remember the return type is a sequence, so I can call the evaluate method on this and calculate at n minus 1. I could do this, but here I'm just adding it, just writing it down. So basically copy and paste this and just replace n by n minus 1. So n plus 2 becomes n plus 1 minus n plus 1 minus n squared divided by n plus 1 minus 2 n plus n minus 1. All right, this is our Shanks, and we can add more methods for the binomial transformation, Euler's transformation, etc. But these are transformation. How do we use this actually? So let's go back to the PowerPoint here. I have an example here, and it's just from Wikipedia. So I'm going to use a Shanks transform to calculate this series from 0 to infinity, 4 times minus 1 to the k over times 1 over 2k plus 1. And this sequence, this series turns out to have an exact solution, which is pi. So this is basically one approximation of pi. And this table again is in Wikipedia. You can look it up. But I'm going to plot the sequence. So I define a partial sum, basically from 0 to some n, and call it capital AN. And plot AN as a function of n, the index, and also the first Shank, and then apply the Shank again to the Shanks, and then apply the Shanks 3 times. All right? And then I'm going to plot the absolute error. So the absolute error for each n is the value minus the exact value, which is pi. So in this case, we already have the pi, the exact value, so we can just do a comparison of how applying Shanks multiple times actually accelerates the convergence, right? And by that we means that, for example, at after 6 terms, so if I sum 6 terms of this sequence, I get 3.2837, which is far from 3.1415, which is pi. But after transforming using Shanks 3 times and then evaluating it at n equals 6, we already at 3.141592, which is very close to pi, right? 5-6 digits of accuracy. So here I have created a test class, test sequence transform. All right, so what I'm doing here in this method, I create the sequence sec, which is k goes to 4 times 1 over 2k plus 1 times minus 1 to the k. So instead of using the power method, I implement this like this. So minus k is equivalent to saying that basically if k is even, this becomes 1. If k is odd, then this becomes minus 1, right? So I have these ternary operations. I calculate the k mod 2, compare it with 0. If it's 0, k is even, so I return 1, and if k is odd, I return minus 1. So this is a much more efficient way. Instead of calculating like math.pov minus 1 to the k, don't do that. Don't calculate minus 1 to the k using that approach. Just call the mod operation. So this is my basic sequence, and what I need, I also define the exact value, which is math.pi, and then I'm going to define my initial partial sum, which is capital AN, and takes n, creates a series class. And remember, series just sums over the terms of this sequence, passing the sequence, and I want to sum from 0 to n, right? So n is the variable, and this basically a lambda expression, and it returns a sequence. All right, so this partial sum is also a sequence. And remember, we want to apply the Shanks on this partial sum, not the original sequence. So we create the partial sum, and we want to find the limit of this. But what we find out is that this has a very slow convergence rate, so we have to evaluate it at a very large n, let's say 1000, 2000, or whatever. But now we apply a Shanks, so sequence Shanks 1. I take the partial sum and call the Shanks method, which was a default method. And this is the beauty of the default method, having to add it directly to the sequence interface, because I create the sequence and Shanks it, it's another sequence. And then I can call the Shanks again on this sequence. I call it Shanks 2, twice Shanks, and then I take Shanks 2, apply the Shanks again, I create Shanks 3, and all of these are sequences. So I can evaluate it at any n, right? Now I create an array of indices, 20 indices. So I want to evaluate the partial sum at n 0, 1, 2, 3 all the way to, let's say, 19. And then I calculate also the Shanks 1, Shanks 2, and Shanks 3. All right. So my indices actually start from 1. So index 0 is 1. So from 0 to 1, A1, A2, and then Shanks 1, Shanks 2, Shanks 3. And here I'm calculating the absolute error. So evaluate at I minus the exact. Okay. And then what I'm going to do here, and then I create a chart and then plot the index and the partial sum. This is my original slow converging sequence. Color B, Shanks 1, Shanks 2, Shanks 3, and then render plot, marker on, and then X and Y axes are both logarithmic because probably the error gets very small, so we want to see on a logarithmic axis, and then I just run. Okay, so one thing here is that there isn't, so if we are plotting on a logarithmic axis, we cannot have 0 as index, so that's why I'm adding index 0 to 1, and then we probably want to also evaluate these at the value of the index, right? So index 0 is 1. All right, so let's run this. All right, that's the result. And let me just add some labels. X label is index number, and then fig dot y label is the Shanks. Shanks 0, 1, 2, and 3. So Shanks 0 is basically the original sequence. All right, and let's see if we can increase the font size. Yes, let's increase the size a little bit more. So we are, as we can see, the blue one is the original sequence, and after 20 terms the error is still pretty big, right? It's between 0.1 and 0.01. So we have to, and it has a very slow converging rate. And then the first Shank suddenly reduces the error by more than 1 order of magnitude. After 20 terms, the error is already has like 3 digits accuracy instead of not even 1 decimal accuracy, right? And then the second Shank increases again, takes this first Shanks and then Shanks it again. So here the error, now the sequence after 20 terms, it has a accuracy of more than 6 decimal places. And then the third Shanks basically kills them all. So it has more than 3, 4, 5, 6, 7, 8, 9 to 10 digits decimal places of accuracy. All right, so that's how Shanks help to accelerate the sequence. So I'm going to put this here, maybe make it a little bit bigger, and so I hope you enjoyed this video. This is how the acceleration works, and we can use this idea to accelerate any numerical integration method or any type of problem that eventually deals with a series, the calculation of a series. All right, thank you very much. I hope you enjoyed this video, and I'll see you in the next one. Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue the discussion on convergence of the series and how to accelerate them. And in the last video, we talked about how to use sequence transformers, some transformation on the sequence, so that we get a better or a faster convergence. And the idea was that we start with the sequence an and create a new sequence bn from the terms of an, such that the limit of bn minus an minus a when n goes to infinity is 0. Now the assumption is that the sequence b also converges to the same number as a. That's the prerequisite. And then if this limit is 0, this means that bn, the series b, the sequence b, has a faster convergence than a. And we discussed multiple transformations, and the two famous ones were Aitken transform or delta squared process, and then the Shanks transform, which is basically the same as Aitken, all right? And Aitken takes the sequence and then calculates the first difference and the second difference, so delta of xn plus 1 and delta of n. And the difference, which is typically the forward difference, is an plus 1 minus an, all right? And then we said that we can, when we do this, the sequence becomes a new sequence. Here S is Shanks, so we said that we can transform that sequence, and typically we use these transforms to calculate series, which are the partial sums of a sequence. So we said that if we start with an, then we define a partial sum sequence, which is summing over the small a sequence. And then now we can transform this partial sum because we want to find if this series converges, we want to find the value of the series or the limit of this sequence, the partial sum sequence. And we said that we can transform using Shanks or Aitken. And then we can also apply Shanks or Aitken multiple times, because once we transform the sequence, it gives us a new sequence, and that new sequence also converges to the same limit, to the same value as the original sequence. And if I Shanks it again or Aitken it again, the new sequence, again, it should converge to the original value, but in a faster rate, all right? And we look at one particular example, which we already knew the exact solution. So the series was 4 times minus 1 to the k, 1 over 2k plus 1, and we summed it from 0 to infinity. And we plotted the error, basically the error of a partial sum with the exact value pi. And we summed up to 20 terms. And we saw that if we just sum this sequence by itself, the convergence is very, very slow. After 20 terms, summing over 20 terms, the error doesn't even have 1 decimal accuracy. And then as soon as we Shanks it, after 20 terms, we get 3 to 4 digits of accuracy. If we Shanks it again, the error even becomes better. And if we Shanks it 3 times, after 20 summations, the error is very, very good. So the convergence becomes faster and faster, all right? And we also discussed how we implement that in Java. And the idea was that, okay, our sequence was defined as a functional interface. So in order to keep that definition, the functional interface definition, we need to add a default method to evolve the interface. And the default method should return a new sequence object, because then we can easily just apply these transforms as many times as we want, because when we transform the sequence, the result is a new sequence, so we can transform it again. And but another thing is that sometimes when we're trying to apply Shanks or Aitken, they are not effective. And the general idea is that the Shanks and Aitken are good when the sequence is oscillating. Basically, it has a minus 1 to the n terms. So the terms of the sequence are oscillating between negative and positive. And basically, this sequence that we already looked at has this behavior. It has a minus 1 to the k term. So the terms are oscillating back and forth between positive and negative. And Shanks and Aitken are pretty good for this type of sequences. But if the sequence is not oscillating, let's say all the terms are positive or negative, then typically Shanks and Aitken, they don't work well. They don't give you a very fast convergence. And in those cases, we typically use Richardson transformation. So the Richardson transform is a better way for non-oscillatory sequences, all right? And let's say we have this A sequence and we're trying to sum it up. So Sn is representing the partial sum from 0 to n. And the value of, and let's say we know that this series converges. So the value of the series, let's denote it by S, and we're looking for that. And the way we want to find it is just accelerate the convergence of this, all right? So the first Richardson transformation is take the Sn and Sn plus 1 and multiply Sn plus 1 by n plus 1, and then multiply Sn by n and subtract it from n plus 1 times Sn plus 1, all right? And here's the basic Java code. This is a default method in our sequence interface, which returns a new sequence object, and n goes to n plus 1 times the evaluate method at n plus 1 minus n times evaluate at n, all right? And then we can continue this with like the second order Richardson, which works on Sn, Sn plus 1, Sn plus 2. We can work with the third order Richardson, which works on Sn, Sn plus 1, Sn plus 2, Sn plus 3. And we can work on the fourth order Richardson, which is Sn, Sn plus 1, Sn plus 2, Sn plus 3, and Sn plus 4. And basically increasing the order of Richardson increases the rate of convergence. And as a general rule, I want you to remember this, really understand this. If you are given a sequence, straight up summing the terms of a sequence is always a bad idea, because most of the sequences that we deal with, especially in the engineering problems or physics problems, have a very slow convergence rate. So we just don't want to sum it up. I mean, the information is in the series, right? So, but the problem is that if we just sum up the terms of the sequence, we typically don't get good amount of information out of it. We have to sum a lot of terms. But because the information is still there, is already in the sequence, these transforms, Shanks, Aitken, and Richardson, they try to basically tickle the sequence so that you extract the information from the sequence faster and faster, all right? So if we go to Eclipse, to our sequence project, and in the sequence interface, I have already implemented the Richardson. So this is the first order Richardson, n plus 1 times an plus 1 minus n times an. The second order Richardson is like half times n plus 2 squared an plus 2 minus n plus 1 squared n plus 1 times half n squared an. And then the fourth order, and then the cubic, this third order Richardson, and the fourth order Richardson, all right? And if you recall, we had all these methods: add, subtract, multiply, and divide, and negate, to add the capability of operator overloading for our sequence. So now if we use the plus operator on two sequence, the result is another sequence, all right? So that makes some of the calculations in terms of writing the code easier for us, all right? Now back to the PowerPoint. So let's look at this example, 1 over k squared and k from 1 to infinity. We already know that this sequence converges, because if you look at the error is summing from some n to infinity of 1 over k squared. And you can make it equivalent to an integral of 1 over x squared from n to infinity. That gives you a behavior of 1 over n. So we know that the error goes to 0. So this series should converge. And the good thing is that we already know the exact value for the series, which is pi squared over 6. This is a very famous series, okay? And the behavior of the error is the limit plus a1 over n plus a2 over n squared, etc. And all these a1, a2 are most likely positive. a1 is definitely positive, right? We already said that if you estimate the error by approximately an integral of 1 over x squared, you get 1 over n. All right. Now this series is not oscillating, is not alternating sign between -1 and 1, so it doesn't have a -1 to the n sign, -1 to the k term, which means most likely if we apply Aitken or Shanks, we don't get a good convergence or a good acceleration. So let's try to actually see this in the code. So in the test, I'm going to create a new class called test Richardson. All right. And in the main method, I'm going to invoke test1, and test1 is going to basically be applying the Shanks or Aitken to this sequence. Public static void test1, and we're going to apply Shanks. So in order to do that, I'll go back to our basic code that we had before, and let's copy maybe this one, this code here. Let's change the sequence to 1 over k times k. All right, so we're looking at 1 over k squared sequence, and the exact result is math.pi times math.pi over 6. All right, and then if you recall, the way we calculate the partial sum is so it's going to be a sequence object. N goes to, this is a lambda expression, n goes to, we call the series class and called its static sum method. We pass in the sequence, so this sum method basically takes the sequence initial and last. Okay, from we're summing from 1, not 0, to n. All right, and this gives us the partial sum, and then we're going to Aitken it, Aitken, so let's call it A, and then let's just rename this, refactor, rename Aitken 1, and this is going to be Aitken, maybe also refactor, rename it, refactor, rename Aitken 2, and this one is going to be Aitken 3, Aitken 3. All right, so Aitken, 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 and as we discussed, Aitken and Shanks are, so I'm going to call this AN to make it more readable. Aitken, Aitken, Aitken. Okay, so we create our partial sum, we Aitken it, it returns a new sequence, and Aitken it again, new sequence, and then Aitken again, and then Shanks 1 sum, let's also refactor, rename it. This is going to be Aitken 1 sum, and then this one is going to be refactor, rename. This is going to be Aitken 2, Aitken 2, and this is going to be Aitken 3 sum. All right, so everything is there, and then we're looking at the log. We're plotting in log scale because we want to look at the decimal places of the error, and again Aitken 0, 1, 2, 3. Okay, so everything is set, and let's run this to see what happens. Yes, now because I'm running this for the first time and I am using a Mac machine, I have to go to the arguments here and uncheck this flag so that it can create a let's run it again. Yeah, okay, so we here let's see what happens. This is our original sequence, and the convergence is not good, right? After the 30, I'm summing over 50 terms, and Actually, let's so index 0 is 1. Okay, we're summing from 1, so that was fine. So this is the original sequence, or 8can 0. We're not doing any 8can transform, and the convergence is very poor. We're not even getting a 1 decimal place of accuracy. And then the first 8can, second 8can, and the third 8can, they basically don't do any good, right? The only thing here is that after 3 8cans and 50 term summation, we end up between 1 and 2 decimal places of accuracy, which is very bad. It's like terrible, okay? And now let's try to do the same thing here. So I'm going to copy this, and let's call this test 2. And instead of 8can, we're going to do Richardson. Okay? And then so we're going to take R and then Richardson it. And instead of Richardsoning the new one, the new Richardson, what I'm going to do is I'm going to apply a second order Richardson to the original. So let's call this R2. So what I'm going to do is taking the partial sum and then Richardson second. So this is second order Richardson. Let's rename it. So this is Richardson 1. And this is going to be Richardson 2. And finally, instead of Richardsoning the previous ones, I'm going to apply a Richardson 3 to the original sequence. So what we're going to do here, we're going to take the partial sum and Richardson 3. All right, and let's call this Richardson 3. So we have our partial sum, Richardson 1, which is a first order Richardson, Richardson 2, which is a second order Richardson, and Richardson 3, which is a third order Richardson. And let's rename these to Richardson 1 sum, this one to Richardson 2 sum, Richardson 2 sum, and this one to Richardson 3 sum, Richardson 3. All right, so everything is set. We're still looking at the log scale, and let's run test 2. So remember, test 1 was doing 8can transform, and test 2 is doing a Richardson transform. Wow, look at that. Here is the original sequence, which gives us about 1 decimal place of accuracy. The first Richardson, or the first order Richardson, gives us at least 2 decimal places of accuracy. The second order Richardson gives us 4 to 5 decimal places of accuracy. And then the third order Richardson basically obliterates the previous ones and gives us 3, 4, 5, 6, 7, 8, more than 8 decimal places of accuracy. Now, as you can see, this sequence was a monotonically increasing sequence, right? The partial sum. And the Aitken or Shanks, they don't work because they're typically very good for alternating sequences. So let's do a side-by-side comparison here. Let's give this a title. So this is Aitken, and this is Richardson. In the I have changed the Y label to Richardson. Okay, now let's copy this and go back to PowerPoint. So we have this one, which is Aitken, and the other one, which is Richardson. and just a side-by-side comparison shows that how good Richardson is in terms of accelerating this non-oscillatory sequence to a very good convergence. Okay, so this is one of the very interesting things about these kind of transformations. Similarly, if you go back and look at the Euler transform also works on the oscillatory sequences. Now you might ask, why is it that we are so interested in oscillatory sequences? That's because most of the time in engineering problems or physics, when you try to approximate a function with a series, or the solution of a differential equation with a series, you most of the time end up with an oscillatory sequence. That's why a lot of thought has gone into developing these accelerations for oscillatory. Now you might ask, how do we come up with this transformation? Where is the root or basis of this Shanks or Aitken or Richardson transformation? How do we know why these transformations are in fact accelerating the convergence of the sequence? And this is the topic of the next video, so please stay tuned and subscribe. Thank you very much, and I'll see you in the next one. Hello and welcome to another Java tutorial. In this tutorial I'm going to continue the discussion on sequences and series in Java, and in the last video we discussed how different transformations such as Aitken, Shanks, and then Richardson help accelerating different types of sequences. And the key point was that if we are summing over an alternating sequence, a sequence that has alternating signs in its terms, it's definitely better to use Shanks or Aitken transformation. But then if the sequence is not alternating in sign and we're trying to sum the terms of the sequence to find the series, it's better to use Richardson transformation. And we said that Richardson, it could be first order Richardson, second order Richardson, third order Richardson, or fourth order Richardson, and etc. And this was this slide shows the comparison that we did for the 1 over k squared sequence, and we're summing from 1 to infinity. This sequence definitely converges. How do I know? Because the error goes to 0. How do I know? Because I can approximate the error. So how do we approximate the error? The error of a partial sum is summing from n to infinity of 1 over k squared, which I can approximate with the integral of 1 over x squared from n to infinity, which is 1 over n, right? So this series behaves as the limit plus a1 over n plus a2 over n squared, etc. And it's a monotonic series. It's very obvious that this is a monotonic series, and the partial sum converges to the limit because the error goes to 0 as n goes to infinity, and the limit approaches L, this partial sum approaches the limit from below because all the terms are positive. So as we add up more and more terms, the sequence gets larger and larger. So Sn is always less than L, right? So all these terms, A1, A2 coefficients are positive in some sense, all right? And we showed that if we look at the comparison of the Aitken and Richardson, this is the plot for Aitken, and we saw that Aitken doesn't really, even if we apply Aitken even 3 times, it doesn't give us a good acceleration. The original sequence is the blue curve, and it has like 1 decimal place of accuracy, and after 3 Aitkens we get like 2 decimal places of accuracy, which is not good. On the other hand, if you use Richardson transformation on this sequence, we see that when I say on this sequence, it means we apply the Richardson on the partial sum sequence, okay, not on 1 over k squared. We create a partial sum sequence Sn, which is summing from 0 or 1 to n an, which is 1 over n squared or k squared, and then that's the partial sum. That's the sequence that we're trying to accelerate for convergence. We saw that the first order Richardson immediately gives us about 3 decimal places of accuracy. The second order Richardson gives us 5 to 6 decimal places of accuracy, and the third order Richardson gives us more than 8 to 9 places of decimal places of accuracy. So for this type of sequence, 1 over k squared Richardson is definitely much better than the Aitken, right? Aitken or Shanks are hopeless, but Richardson is much better. And the question is, how do I know if you give me a sequence, a series, right? 1 over k squared or any type of AK sequence. How do I know which one to use, Shanks, Aitken, or Richardson? So the key here is understanding the behavior of the error, right? And before looking at general case of how the Shanks, Aitken, or transform come to be, these type of accelerators, let's try to look at another example. In this example, I take the 1 over k squared, but now I add an alternating term, right? Minus 1 to the k plus 1. So it's like 1 minus 1 over 2 squared plus 1 over 1 over 3 squared minus etc. Okay? So now I take the 1 over k squared sequence and then add an alternating sign term to it. This is an oscillatory convergence, right? Because if you look at the sequence of the partial sums, they oscillate around the limit. And however, this series exists, which means the partial sum sequence must converge. How do I know that? Because again, regardless of whether or not we have this alternating sign term, minus 1 to the k plus 1, I can estimate the error by integrating 1 over x squared. So the behavior of the error is still 1 over n, right? But the coefficient could be positive or negative. And we are going to do exactly the same thing here. We're going to take this and run Aitken and Richardson and see which one provides a better case, a better convergence. So let's head to Eclipse, and I have this test Richardson, which was 1 over k squared. So let's copy it and create a new class. Let's call this Richardson 2. And in the Richardson 2, what I'm going to do, I'm going to create basically minus 1 to the k plus 1 power. So basically what I want is if k is even, I want to get if k is even, I want to get minus 1. K is odd, I want to get plus 1. Because I'm summing from the k equals 1, so I want the first term to be positive. So what we are going to do here is that k mod 2 equals 0. We're going to compare it. And if k is even, I want to have minus 1. Otherwise, I want to have plus 1. Okay? And remember, just note this one important thing, that I'm returning double values, not integer, because I'm dividing by k is long. So if I return 1 as an integer and then k is long, k times k is also long, and 1 divided by k squared is always 0, which is incorrect, right? So we should either return a double, minus 1 plus 1, or convert k to double before calculating this rational number. Okay? And we don't know the exact value, so I'm going to just look at the absolute value of the sequence. Basically, I set the exact value to 0, which means I'm just looking the absolute value or the magnitude of the terms of the partial sum or the Richardson. Okay? And we know that this sequence converges, and so the exact value is 0. Everything else is the same. I'm just going to, because I'm not looking at the error, I'm just going to remove the log. I just comment them. I just want to, on a linear scale, I want to look at how the Richardson and the Aitken are accelerating the convergence here. Okay? So test 1 is Aitken transform. We're applying Aitken transform twice to the or 3 times to the partial sum. So let's see, test 1 is 8can. Okay, okay, I need to remove the log scale from the 8can too. And maybe let's increase the font to 15, the font size. All right, so obviously the blue is the original sequence, and we definitely see the oscillatory behavior, but that's a convergence behavior, right? The terms are oscillating around the limit, the terms of the partial sum. And as you can see, the first 8can is the red one, and we see that it has a much better behavior, almost converging after just a few steps, 8, 9 terms, okay? And even the higher order 8cans, the green one is the second order or the second 8can transform on the first 8can, and then the black one is pretty much converges. So you see that after 3 8cans on the original sequence, the black one, you pretty much after 2 terms you're there, right? The error is very small. So let's zoom in as much as we could, as much as we can. The red is the second 8can, the green is the red is the first 8can, the green is the second 8can, and the black is the third 8can. So the limit is about 8.22467. Okay? So 0.822467. So I can write it here. 8.22467. Okay? As the exact value. We can zoom in and okay? And now I can look at the error. So the black one, so as we can see, the sequence has a very slow convergence rate, and then the red one is getting better. So the first 8can is better. The green and the black pretty much converge after 20 to 30 terms. Okay, let's put this back, just look at the terms. 0. So this is 8can, and we see that the 8can is definitely helping a lot in terms of the convergence of the sequence. Let me just zoom in. Alright, so we're going to copy this, put it in our slides. So this was 8can. Now let's see what Richardson does. So for Richardson, I'm going to run test 2. And it's very interesting that not only so the blue is the original sequence, right? Just summing up the partial sum. And the red is the first Richardson, first order Richardson. It actually gets worse and worse. The green is the second order Richardson, and the black is the third order, which is definitely diverging. So not only Richardson doesn't help, it actually causes the sequence to diverge. So Richardson is definitely not a good option in this case. Definitely we don't get a good not only we don't get any convergence or any benefits in terms of faster convergence, but in fact it diverges. Remember, the blue here is the original partial sum sequence, and then the red is the first Richardson, the green is the second Richardson, and the black is the third Richardson, which pretty much diverges. Okay? So just be careful when you're trying to sum the sequences. Just try to get a feeling for the behavior of the error, and if it's alternating in signs, If it's oscillatory, definitely, by oscillatory I mean the sequence that is generating the partial sum, this AK, okay? If this is oscillatory, we know that the partial sum is also oscillating around the limit, and then we should use Aitken or Shanks. If it's a monotonic, then we should use Richardson, okay? So then the next question is, where are these accelerators come from? What's the reasoning behind this? And in order to do that, I'm going to present this discussion. So the question is, where do the ideas of Aitken, Shanks, or Richardson acceleration come from? And these are based on modeling the asymptotic behavior of the error. So this is very important, modeling the asymptotic behavior of the error. And it's not an exact modeling, it's just based on intuition, how the sequence would behave, right? If we have an alternating convergence, what happens is that we know that we have to use Aitken or Shanks, right? Aitken or Shanks. But why? Because typically in physics or in engineering problems, this type of sequences, the way their error, if you try to estimate the behavior of the error, so we have a sequence that is alternating around the limit. We know that it converges, and the terms of the sequence as we increase n, they are alternating between the limit, but they are getting closer and closer. So this is like an oscillatory behavior, and typically in physics or engineering problems, you can model the behavior of the error with something like this: some constant times minus b, another constant, to the power of n. So the error behaves like some power of n, right? Some constant to the power of n. And obviously, in order for the error to go to 0, this b coefficient should be less than 1, right? And this a coefficient could be positive or negative. We don't really care that much. But then if this is in fact the behavior of the error, what we can do, we can say, okay, an is asymptotic to the limit plus a minus b to the n. And now I can write the same thing for an plus 1 is asymptotic to l plus a minus b to the n plus 1, all right? Now if I bring L to the other side, an minus L, an plus 1 minus L, okay, and then divide these two, I get minus B equal to an plus 1 minus L divided by an minus L. And I can do the same thing for n terms, the nth term and n minus 1 term, right? Again, bring the L on the left side, an minus L divided by an minus 1 minus L, and it gives you minus B, all right? So that basically means that now if we set these two equal to each other, then we have eliminated A and B and have come up with a relation between the L, the limit, an plus 1 and an minus 1. And now I can actually solve for L, and L is an squared minus an plus 1 an minus 1 divided by 2 an minus an plus 1 minus an minus 1, which is exactly the Shanks, right? If we go back and look at the definition for Shanks, Shanks is if you write Shanks is an plus 1 an minus 1 minus an squared divided by n plus 1 plus an minus 1 minus 2 an, okay? So that's basically the same thing. I just reversed the signs of the numerator and denominator. So n plus 1 times an minus 1 minus an squared, and then an plus 1 plus an minus 1 minus 2an. This is Shanks. And then it turns out that now the error of this, if you look at this sequence and just substitute this term, this approximation, the original approximation, L plus a times minus b to the n. Now consider this as a new sequence and substitute this model into this. What you will see is that this becomes asymptotic to L, plus some constant, now b to the n plus 1 power. So that means you actually reduce the order of error, and now the convergence becomes faster and faster, right? Because instead of b to the n, remember b is less than 1, instead of b to the n, we end up with b to the n plus 1. And that's very important, because now we have bn plus 1. So the convergence faster, or the error goes to 0 faster. And because this is a new sequence which follows exactly the same model again, then we can do Aitken and Chance again on this new sequence. And from bn to the plus 1, we go to bn plus 2. And this sequence could, in fact, continue indefinitely. So you get arbitrarily fast convergence, right? The problem is that at some point, usually after 3 or 4 times of applying Aitken or Shanks consecutively, it becomes unstable for large n. So it is always advised to do only like 3 or 4 times of Aitken or Shanks, as we have done before, right? So we have never done anything more than like 3 or 4, and we saw that for this sequence, which has so this sequence was 4 minus 1 to the k 1 over 2k plus 1. So when k is large, the terms of this sequence are 1 over k, and the error of the series is integral of 1 over x, which is log of x, or log of n. So log of this is usually the worst that can happen, right? The slowest convergence, or the slowest error rate. And we saw that 3 Shanks or 3 Aitkens are more than enough. After 20 summations, 20 terms, we get 9-10 decimal places of accuracy. So this is more like the worst case. If I have 1 over k squared, obviously we need less terms to sum to get a good accuracy. So typically 3-4 times of Aitken or Shanks is more than enough, okay? Now the same thing with Richardson. So if and again, what we did here, we transformed the sequence by solving for L. Remember, the base idea was to try to model the error of the convergence, a simple model. And this behavior only applies when the model is in fact something like this, some number to the power of n, okay? And what this transformation does is it removes the b to the n, and the result of this transformation has a term of b to the n plus 1. So what we are doing is that we are eliminating poorly converging leading terms of the error. All right, so we heuristically model the error with something like this, b to the n, and find a transformation so that the transformation, when we plug this model, it ends up with b to the n plus 1. And then we say that, okay, now it has a faster convergence because the error goes to 0 faster, because the leading error term now has been eliminated, okay? Now what happens in the non-oscillatory behavior? Let's say we go monotonically to the limit from above or below. And typically this happens in physics, or again engineering problems. This kind of behavior has an error model of some constant over n to the b, where b is let's say greater than 1. And if you remember, we actually have seen this before when we discussed numerical integration, and we saw that for for rectangle approximation of numerical integration, for rectangle approximation, the error was proportional to 1 over n. And for trapezoid, it was 1 over n squared. For Simpson, it was also 1 over n squared, etc. So in those cases, we can model the error as 1 over n to some power, which is typically greater than 1, greater than or equal to 1. Okay? And then when that's the case, then the question is, obviously this behavior doesn't work, but we can again follow exactly the same rule, but in a different way. So the way it works is that we write an as L plus a over n to the b, Remember, the ultimate goal is that to try to come up with a transformation that has a better convergence. A better convergence means I want to come up with a transformation of an that when I plug this definition, this limit plus the leading error term, the leading error term goes away and I end up with some constant over n to the b plus 1. At least it's better to end up with n to the b plus 2 or etc. So if you have a uniform convergence, something like this, usually or typically in the engineering or physics problem, we do Richardson. And so the way we try to transform the sequence is that we write the n terms, L plus A over n to the b, and then we multiply it by n. And we also write n plus 1 term. N plus 1 times an plus 1 is n plus 1 L plus a to the n plus 1 to b, and then nan is also nl plus a over n to the b. And when you subtract this, both sides, we have n plus 1 an minus n plus 1 an plus 1 minus nan on the left side. On the right side we have n plus 1 l minus basically minus on the right side we have nl plus a over n plus 1 to the b, right? Then if when we subtract, we have n plus 1 L and NL, so we end up again with L. So n plus 1 times an plus 1 minus n times an also has a limit of L, right? It converges to the same limit as the original sequence. But then once you look at the order of the error, it actually is 1 over n to the b plus 1 instead of n to the b. And that's exactly why we define the first order Richardson as n plus 1 Sn plus 1 minus n Sn. This, if the error of convergence has a behavior of 1 over n to some power, this transformation makes the error some constant over n to the original power plus 1. Now the error goes to 0 faster, okay? Now with the same logic, we can eliminate 1 over n to the b and 1 over n to the b plus 1 if the error has also 1 over n to the b plus 1. We can eliminate these two, the first two leading terms of the error simultaneously by applying a second order Richardson instead of the first order Richardson. And if we want to eliminate simultaneously the three leading terms of the error, we use the third order Richardson, and etc. So you see the power is it's a very powerful concept, because if I have my error is 1 over n plus 1 over n squared plus 1 over n cubed, or some coefficients there, but the three leading terms are something like that, I can apply a third order Richardson and immediately get rid of those three first terms of the error. And now the transformed sequence has an error, leading term error of 1 over n to the fourth, which is a huge improvement. So that's how, for example, if for numerical integration, if we start from trapezoid method and then apply a third order Richardson, suddenly the convergence is very fast, and then we have a very fast convergence. And we discussed this at some point, and this is called Romberg integration. So the Romberg integration is exactly like this. It starts with trapezoid and then applies Richardson extrapolations, and it gives you a very beautiful and fast convergence with you don't need to have use many sub-intervals. So the number of sub-intervals could be in fact very small, maybe 10, 15 is enough. But you apply third order or fourth order Richardson, and then suddenly the error goes down very fast. So this is the idea behind this transformation. And again, not all sequences, not all problems we can model them like this, but if we have some intuition that the error eventually behaves some number to some power or the n to some power, we can use either Richardson or Aitken or chance. Okay. So this is the idea. And then another interesting thing about, now that we know about sequence transformations, another interesting thing is perturbation theory. And I'm going to talk about this in the next lecture. So stay tuned. Thank you, and I'll see you in the next one. Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on sequences and series. And so far, we have looked at sequence accelerators, but now I'm going to look at some useful sequence operations that we can implement in Java. To remind you, we implemented sequences as a functional interface in Java, and then we added some default methods that do some transformations on the sequence, but we kept the identity of the sequence as an functional interface. And we also implemented default methods. So here these are default methods. We implemented some default methods for operator overloading for sequence interface: addition, subtraction, multiplication, and division. Okay. Adding two sequences results in a new sequence which adds term by term. Subtracting two sequences just subtracts term by term and returns a new sequence. Multiplication, the same thing, multiply term by term. And division, you also divide term by term. And again, in order to keep the identity of the sequence as a functional interface, we add these as default methods. Okay. And then we can have some useful relations, and that are actually or particularly useful when we are dealing with perturbation theory using sequences. The first one is the definition of a sequence as the Kronecker delta. So delta of n, it's basically discrete signal or a sequence basically. So this kind of discrete signals occur, or we see them all the time when we are dealing with discrete systems. But here we looked at them as just sequences instead of a discrete signal. So a sequence delta, for n equals 0, it's 1. For n non-zero, for example, -1, +1, -2, +2, etc., delta is 0. And then because this is a sequence by itself, we can just add it as a static method to the sequence interface. Okay. And then what I mean by that is that if we go back to Eclipse and look at our sequence project, we have this sequence interface, and it already has one public abstract method, which is evaluate. That's our functional interface. And then we have other default methods for transforming the sequence: diff, Aitken, Shanks, Richardson, second order, third order, fourth order, and then operator overloading methods. Sequence add, subtract, adding a number to a sequence. We define that as adding it to each term, so adding term by term. And then subtraction, multiplication, division, and then negation. Okay, so let's just quickly look at one example of this operator overloading. So let's create a test class, test operator overloading for sequence. I think we already looked at this operator overloading, but let's do that one more time to just remind you. So I'm going to call a method public static void test1, and here I'm going to create a sequence sec1, which is k goes, or n goes to let's say 2n, 2 times n. Okay, and I need to import sequence. All right. And then sequence sec2, I can say that just sec1 times sec1 plus or minus 1. okay? And let's do a sysout sec1 evaluate at 1. So this should return 2 times 1, and then sec2, so sysout sec2 dot evaluate at 1. So this should return 2 times 2, which is 4 minus 1, 3. So we see that we do in fact get operator overloading, okay? And again, because this is an interface, we're adding them as default methods, and all of them are public methods because the interface is public. So unlike classes that even if you define them as public, the method could be defined as private. For interfaces, if interfaces only have 2 access modifiers, it's either default access modifier or public. Default means it's a package level access, and public means it's open to the world, okay? And then if you declare interface as public, all the methods are by default publics and you cannot change it. So you see all these methods have this field green circle. In Eclipse it means it's a public method. And adding something like public abstract modifier to this, for example, to this method is unnecessary because it's implicit in the definition, okay? So I cannot change any of these methods to private. It complains that illegal modifier for the interface method diff. Only public, abstract, default, static, and strict FP are permitted. So I cannot have a private method in a public interface, okay? All right, so let's add some of the, so we have these transformations. Let's add the sequences, some of the operations. So I'm going to add a static sequence delta. It's going to return n goes to basically evaluate at n. Now this is complaining because cannot make a static reference to the non-static method evaluate. So basically what we need to do is we're going to return a sequence. So we're going to basically create a sequence, or maybe just return n goes, I'm going to use a multi-line lambda expression, and here I'm going to say that basically, or a single line. So if n is 0, so I'm going to use a ternary operation. If n is equal to 0, we're going to return 1 double, else we're going to return 0 double, okay? And this is double, so remember, just note that I'm returning double. And let's go and test this. So let's create another test, public static void test2, and I'm going to invoke test2 to test the delta function. So sequence delta is sequence delta, and then sysout delta at 0, evaluate at 0, which is 1, evaluate at -2, which is 0, evaluate at 2, which is 0, so it's 0. So we have, now we have the so we have delta of n, right? The Dirac delta or the Kronecker delta of n. Now we can construct other sequences based on delta of n. For example, let's say I want to have a sequence an that is non-zero for n equals 0, 1, and 2, and it's 0 everywhere else. So I can say sequence a sec, for example, And I can use the power of operator overloading, which is an absolutely beautiful thing to have. So I'm going to say, let's say a0 is 1, so 1 times delta of n, plus a1 is, let's say, minus 2, so I'm going to say, okay, now minus 2 times delta of n minus 1. So we want to also be able to shift the sequence. So let's say I want to have a sequence an, and I want to create new sequence bn, which is a shifted version n minus 1, for example. So let's go and add also this capability as a default method. So delta is one thing, but the first operator is shifting. So default sequence shift and int n m, for example. This shifts by m orders, m terms. So return n goes to basically evaluate at n minus m. Okay, so this is the very basic operation or transformation. We're shifting. Now I can say that let's test shifting. So let's say I want to create delta n minus 1. So this should be sequence delta shifted is delta shift by 1 plus 1. Okay, and now sys out delta shifted at 0. It should return 0. Yes, it returns 0, and at minus 1 it should return 0. At plus 1 it should return 1, because now we have delta minus 1 n minus 1, and delta is only 1 when the argument is 0, so n equals to 1 exactly, and 2 it should go back to 0. Okay, so this is how we shift a sequence, and then, or we shifting or delaying a sequence. We can also call it delay. Maybe delay is a better terminology. Okay, so we have shifted delta, we tested this. Now I want to create a sequence just based on the delta. So delta takes care of the a0, and then delta shift by 1 takes care of a1 plus, let's say, a2 is 5.1 times delta shift by 2. Now using operator overloading and basically the shift functionality or delay functionality, I created a new sequence. Let's do the sys out. So I know that asec, if I evaluate it at minus 1 and then 0 and then 1 and then 2 and then 3. Okay, so I should only get at minus, the only non-zero values are 0, 1, 2. So I get 0 at negative 1, 1 at 0, because we defined it as 1 times delta n, and then at 1 I get minus 2, because it's minus 2 delta n minus 1. So basically the definition of an is delta n plus or minus 2 or plus minus 2 times delta n minus 1 plus 5.1 times delta n minus 2. So you can construct any sequence from just the delta function. All right, and this is a very basic fundamental concept in signals and systems when we are dealing with basically discrete systems. So 5.1 at 2 at 3 it's 0. Okay, all right. So now the next thing is So if I go back to our PowerPoint, so this is the Kronecker delta. We implement it as a static method, and using operator overloading and the shift functionality, we can do the construct any signal from delta. Okay, and the next one is unit step. Unit step defined at 0. A step at n equals 0 is 1 for n greater than or equal to 0. So we are including the equality in the 1. And then for negative 1, negative n, n minus 1, minus 2, etc., it's going to be 0. So, and you probably can guess that un is the partial sum of delta n from 0 to n, okay? So again, we're going to use a static method, sequence unit step, and this is going to return, and again, lambda expression. We're going to test with 0, plus 1, other than that 0, 1. So returning double value. Just note that we're returning double because the sequence basically returns double. So if n is greater than 0, we're returning 1, otherwise we're returning 0. And then if I want to have a step at, let's say, n equals 2, so I'm 0 until n equals 2 and then jump up, I use unit step and then transform it using this shift functionality or delay functionality. Yeah. Maybe let's also add another method, delay. Maybe someone is more comfortable with delay, but they're basically the same thing, delay or shift. Okay. A delay is more suited for a discrete system because then the argument n is representing time steps, and n minus m is like delaying a discrete signal by m time steps. Okay. So for now, I'm going to just delete it, but if you're more comfortable with the delay function instead of shift function or shift terminology, just use delay. Okay, let's do public static void test3, and here, and let's invoke test3, and here we're going to create a sequence, step 0. So this is going to be a sequence stepping right at 0. Okay, so unit step by default is at 0, and we can also have another one that directly jumps at int m, and the way we're going to do it is if n greater than or equal to m. But using this unit step with a delayed m and creating a unit step and 0 at 0 and then shifting by m is similar. Similarly, we can basically do the same thing, right? We can have a delta that gives us a delta at exactly m, right? So we don't need to use the shift functionality. So step 0, and then sysout step 0 evaluate at 2, for example. This should give us 1. At minus 1, this should give us 0. Yes, at 0, this should again give us 1 because we included 1 in the definition at 0. Okay. Now I'm going to basically create a new sequence, step 1, and take the step 0 and shift it by 3. Okay, and what happens here is that now this is basically a unit step at n minus 3. This was the originally it's a unit step at n. So at 1, the step 1 should be 0. Yes. And at 2, it's 0 still. Yes. At 3, it should be 1. Yeah. And let's also try plotting them. I guess visualization is a better way. So we're going to create an array of indices, new int maybe 100, and double step 0 vals, new double indices dot length, double step 1 vals, new double indices dot length, and then for int I equals 0, I less than indices dot length I plus plus, we're going to say that indices I is equal to I, and so what we are going to do, we are going to plot from, let's say, minus 50 to 50. Okay, so 101 minus 50 to length over 2 plus 1 I plus plus, and okay, and then step 0 vals at I. Okay, so no, so we have to stay with that length, but I'm going to just reduce the index. Step val at I equals to step 0 dot evaluate at indices I, and step 1 vals at I is step 1 dot evaluate at indices I. All right, and then the rest is just creating a MATLAB chart, fig new MATLAB chart, fig dot plot indices and step 0 vals. Now this complains because the plot is defined just for doubles, so let's just do double. There is no harm in that. Okay, this says that okay, we can do just so indices is double, so this integer is changed to double, and we can cast it to long, shouldn't matter, and then fig dot plot indices and step 1 vals. Let's plot this with blue color, this one with red color, and then fig dot render plot, fig dot marker on, fig dot show. Okay, it doesn't create the plot because I'm on Mac operating system, so I have to go to the VM arguments and remove this check mark. Okay, as you can see, we have the 0 to 1, and then at the unit step, which has been shifted by 3, gives us 1 at 3, and before 3 index 3 it's 0. Okay, and the unit step, the original one is 1 at 0 and after that, so this is the unit step. All right, let's go back to the PowerPoint and convolution sum. So the convolution sum is also a very interesting and a very useful thing to implement. So if we have two sequences an and bn, we can define a convolution sum. Now here the assumption obviously is that the sequences start from 0 or 1, so there is no negative index. So here the assumption is that no negative index, which means that for the negative indices we're going to assume that the sequence is 0. Okay, so we're going to just define the convolution from 0 to infinity or 1 to infinity, and then because we're assuming that there is no negative thing. So m, this is m is the variable of summation. So the convolution is am bn minus m, and m goes basically from 0 to infinity. And here, because b also is a sequence that is 0 for index less than 0, negative index, m is limited to the maximum of n. That's why this sigma is running from 0 or 1 to n. Okay? So we have to take two sequences. If I'm convolving one sequence with another, I have to create a partial sum and then sum them up from 0, 1 to n. Okay? Because again, the assumption here is that there is no negative index, which means that an is 0 for n less than 0, or less than or equal to 0, depends on how we define the sequence. And bn is also 0 for n less than 0. Okay? And then the way I'm going to implement it, very simple. This is just a partial sum, right? The sequence is the sum. So here I'm going to create a method called okay, let's maybe move this shift to the bottom here, and then we have another default sequence. Remember, convolution also should return a sequence, convolve. And in the convolve, I'm going to pass another sequence, bn, or b. So we're taking this sequence, which is a, and then convolving it with b. And what I'm going to do, I'm going to return a basically a new sequence using lambda expression called the series object, and the sum, the static method sum, it takes a sequence, all right, and then initial, let's say 0, and last it should be n. Okay, now what we need to do, we need to define this sequence. So sequence sec is this. Basically n or k goes to actually we should do it just here inside the lambda expression so that we have access to this n. So here m is the index of this sequence, inside sequence, which is this dot evaluate. Okay, we do not have access to that, so let's create a sequence a, which is this sequence, and then a dot evaluate. Okay, we still don't have access to this. We want to sum this up with a dot evaluate at n at m, all right, or just maybe okay, times b dot evaluate at n minus m. All right, so we make a copy of this sequence a, and then this returns a convolved by b, so returns a convolution by b. Okay, maybe a convolve a and b. So it takes the summation a evaluate at m, b evaluate at n minus m, and sums it up from 0 to n. All right, now let's go and test it. So let's create a new test, test 4, and public static void test 4. Now what the simple cases that we already know is that if I take a delta of n and convolve it by any sequence an, I should get an, right? So that's the basic thing. Convolution of any sequence with delta sequence is is the original sequence. So delta is the identity function or identity sequence for the convolution. So let's test that. Let's create a new sequence, delta, and sequence delta at 0, and then sequence A, or sequence A is basically n goes to, let's say an is just 2n, 2n, okay? And sequence conv A is basically sec A convolve with delta. And what we're going to do, we're going to just plot. So we're going to do sec A and conv A. So sec A is the blue curve and conv A is a red curve. And as you can see, so one thing is that my assumption here is that the A should not be so we define the convolve assuming that it's basically the sequences that we're dealing with are 0 for less than 0. So what I'm going to do, I actually have to multiply this by sequence dot unit step. Okay? Or basically I create this, so this lambda expression returns a sequence and then sequence dot unit step. Must be a functional interface. Okay, let's see. This is our sequence A, and then sec A we want to multiply it by sequence dot unit step. So we make sure that the A is 0 for negative index. Okay, now it's 0 and the convolution is basically the same thing. Let's see what happens if we set delta to delta n minus 2. So if I convolve a sequence by delta n minus 2, I should get an minus 2. So shifting delta and then putting into the convolution actually shifts the the original sequence. So delta by 2, and then the original sequence starts from 0, and then let's see what happens. Okay, as you can see, we're getting a delay of 2. All right, and maybe a fancier thing to say, let's say instead of having a linear thing, let's say we have a maybe quadratic thing. Plus 1. So at 0 we are 1, and then we get a delay of 2. So we are 0 until so the original sequence is 0 at negative 1 and is 1 at 0, and then we shift it by 2 indices, so it's 0 until 1 and then becomes 1 at 2. All right, so it's shifted exactly by 2 indices, 48 and 50. So the convolution seems to work, but let's try to do another test. So we know that, if you recall from our discussion on the polynomials, we said that if you take a polynomial x and multiply it by another polynomial, the coefficients, let's call this r of x equal. The coefficient Rn is basically the convolution of Pn and Qn. So if we take two polynomials and multiply them, basically what it means is that the coefficient of n index for the multiplication, the result is the convolution of the coefficients of the two polynomials. And we can test this using this approach, public static void test 5. So here what I'm going to do, so let's go and invoke test 5. And what we're going to do, I'm going to create a sequence. So let's say our polynomials p of x is just x plus 1, q of x is x2 minus 1, or just x2. So let's see, let's try the polynomial route first. So p is basically new polynomial, and then coefs are 1 and 1. So this gives us x 1 plus x. And then I have another polynomial, q, new polynomial. It's 0 plus 0x plus 1x squared. Okay? And then polynomial r is p times q. Note that the operator is already overloaded. So sys out p equals plus p, sys out q equals plus q, and then sys out r equals plus r. So 1 plus x, 1x plus 1, x2, it gives us x cubed plus x squared plus 0x plus 0. So we get x cubed plus x squared, okay? Which is what we expect. Now using sequences, let's see. So what we're going to do here is I'm going to create a sequence. Let's call this sec p, and this is going to be let's create the sequence delta first. Delta is sequence dot delta. I'm just going to create it using delta. So this is going to be, actually let's do this. Let's try to create a sequence by passing in an array. So let's say default sequence for array, and then we pass in a double array, a 1D array, okay? Then return n goes to basically double array. So we're going to int length is array dot length, okay? And then if n between 0 and length minus 1, so we're going to do this. We're going to say that if n basically n greater than or equal to 0 and n less than array dot length, if this happens basically return array at index n, else return 0, okay? Now this complains because n is supposed to be long, so we're just going to cast it to int. So this is a multi-line lambda expression. Okay, so we create a sequence for array, and here it is guaranteed that the index starts from 0 and goes up. So let's do that. So what I'm going to do is that and this has to be a static method. All right, so sequence for array, and we can do a vararg actually. One and one. So this is sec p, and then sec q for array 0, 0, 1. All right, and then sequence sec r is sec p convolved by sec q, and then we're going to basically sys out sec p dot basically evaluate at 0, evaluate at 1, at 2, and 1, at 2, at -1, and at 3. All right, so let's do this. So let's here do a sys out. Actually, okay, so let's put this here. So I'm evaluating p. So p is 1, 1. So at -1 is 0, at 1 is, at 0 is 1, at 1 is 1, at 2 is 0, at 3 is 0, exactly like the coefficients here. And now we're going to create we're going to print basically, let's say printing p, and now printing q, sec q. Okay, all right, so q at -1 is 0, at 0 is 0, at 1 is 0, at 2 is 1. So it's exactly like the coefficient of the x squared. All right, now finally what we're going to do, we're going to print the results of the convolution, printing convolution, or r. So sec r. And let's go up to 5. So what we expect to see for the convolution result is to have basically the third index and the second index. So all right, this is -1, 0, 1, 2, and 3. 2 and 3 are 1. 4 and 5 are 0. 2 and 3. So the coefficient of x squared is 1. The coefficient of x cubed is 1, right? So the convolution of the sequences is exactly the same as multiplying the polynomials. And we can approve it by changing the coefficients. For example, 2. So we have 2x plus 1 and x squared. So the result is 2x cubed plus x squared. Let's see, 2x cubed plus x squared, exactly like that. Okay, so the polynomial convolution is the polynomial multiplication is exactly the same as sequence convolution. All right, the thing is that for polynomials, the polynomials start from 0. It means when we represent the polynomial by sequence, that sequence is 0 for negative n. It only starts from 0, 1, 2, and etc. Okay. So that's the main thing. So the last thing here is the running average. So the running average is, sometimes we use this in discrete signal processing so this acts as a low pass filter. So it reduces very fast changes in the terms of the sequence. So in order to implement the running average, what I'm going to do, again, you can guess. It's a partial sum. So M is the order of the running average. And it returns a new sequence. So what I'm going to do, I'm going to go to sequence here, use a default access running, or maybe a static sequence running average, and we pass in a sequence, and then return n goes to we pass in a sequence and then int m, or order, and this goes to 1 over order times we call the series class, and the sum, we pass in our sequence, and we're going to sum it from n to n plus order minus 1. All right, and then we can have a non-static part for this, and this just takes the order, and this sequence becomes this. All right, so it takes this and applies the running average, and then returns the sequence. So let's test that too. So test 6 is going to be testing the running average, test 6, and in the test 6 I'm just going to create a public static void test 6. all right, so I'm going to create a sequence that I know is very sharp. So sequence 6 sec1 is n goes to basically unit step. Sequence dot, all right, just sequence unit step at 0. So this is a very sharp sequence, right? At 0 it suddenly jumps to 1. But let's say that now we try to apply a running sequence. So sec2 is sec1 dot running average with 10, with an order of 10. We're going to filter it. So let's see what happens if we plot it. Step 0, this refactor rename, this is going to be sec1 vals, and refactor rename, this is going to be sec2 vals. So sec1, sec2. All right, as you can see, what happens in the running average is that it adds a ramp. So it removes some of the sharpness, and it adds a ramp to the running to the original step. Okay, so instead of going sharp to like this up, we start smoothly. Now obviously this is the indices are apart, that's why you don't see the smooth transition, you see this ramp one. But as we can see, there is some removal of the sharp behavior of the function. So if I set to -10, it actually goes down. So let's say 220. You see the ramp gets larger and larger. That means it removes some of the it removes more and more of the sharp behavior of the original signal. This was an introduction to how to implement some of the useful sequence operations, and I believe at the moment we have all the tools that we need to really get into more interesting stuff with sequences. So we have looked at the sequence accelerators, we have very powerful operator overloadings, and some of these useful convolution and averaging of the sequences. So we should be able to really start doing or implementing any discrete signal processing system, any system based on discrete signals. And we will look at these concepts in the next lectures. So stay tuned. Thank you for watching, and I'll see you in the next one. Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue the discussion on sequences and series. And one example here is, or one use case of using one of the sequence transformers to accelerate the convergence is that related to the perturbation theory. So I'm not going to actually talk about the details of perturbation theory in this lecture, but I'm going to talk about one of the use cases. And in general, the perturbation theory is about turning a hard problem into an infinite number of easy problems. And then basically we calculate the result of each of these easy problems and try to combine them together infinitely to find the solution to the hard problem. And what we usually do is we introduce a free parameter. So it's an extra degree of freedom. Some people just call it degree of freedom, a free parameter or another degree of freedom to the system. Typically we call that epsilon. And then we introduce it in the original problem, which is the hard problem, such that when we set it to 0, when we set this epsilon to 0, the problem is solvable. We can find the exact solution. The solution is known. And then we write the solution of the hard problem with the new degree of freedom, epsilon, in terms of a power series of epsilon. So we end up with a sequence or a series, right? A(n) epsilon to the n. And assuming an analytic behavior is that this series is more like a power series or a Taylor series. Remember, Taylor series converge for analytic functions, okay? So we assume that the solution to the hard problem is well behaved, which is not. In fact, most of the times it's not well behaved, but if it's not well behaved, it just means that this series is not representing an analytic function, which means that this series is in fact a divergent series. But that's not a major issue. We can resolve that somehow in most cases. So we do this, and remember the first term here, this summation starts from 0. So a0 epsilon to the 0th power. It's just a0, right? And a0 is basically evaluating this series at epsilon equals 0. So when we set the epsilon to 0, the solution is in fact a0, right? So a0. So we start by setting epsilon to 0 and find a0, and then we write the general solution like this series, and then eventually what we want is to set the epsilon to 1, because epsilon to 1 means we get exactly the hard problem. And the hopes here are that the radius of convergence of these power series is greater than 1, so that this becomes, when we set epsilon to 1, this becomes a convergent series, right? In most cases it is not, but let's not worry about that at the moment. And then once we have this series, and let's assume that it's in fact a convergent series, then we can use any of the accelerating methods or accelerating transformations. So if the coefficients turn out to be oscillatory, we apply Aitken or Shanks. If the coefficients are monotonic, we apply Richardson, and we can get a much faster approximation or acceleration for a convergent, right? So we don't need to calculate maybe 20-30 terms. Maybe we can just calculate the first 10 terms and then apply twice the Aitken transform or Shanks transform, and then we get a much more accurate result for the original series, right? Now, one example that is very interesting to look at is this case. Let's say we have this equation, x to the 5th power plus x equals 1, and we want to find the real root of this equation. Now, this can only have exactly one real root, because if you look at this polynomial and look at the derivative, it's 5x squared plus 1, 5x to the 4 plus 1, and it's strictly increasing, right? This means that if the function goes up, it never comes down. So this polynomial must have exactly one root. And we kind of can guess that the roots should be between 0 and 1. Because if it's greater than 1, then x to the 5th is much greater than 1, and plus something greater than 1, it's just greater than 1. It's never equal to 1. If x is less than 0, then x is 0, negative. X to the 5th is also negative. Therefore, the whole left-hand side is negative. So x, the root must be between 0 and 1. And this equation has exactly one root because of the strictly increasing behavior of the function. Now, we have already discussed all of the common root finding methods, including bisection, trisection, Brent, Newton, Raphson, and other types of methods, okay? Secant, enhanced secant, false position. So we can use that. So let's try to do that first. So let's head to Eclipse. In our sequence, in the test package, let's create a class like test root finder, root perturbation. We want to have a main method. Let's call test1, and test1 is basically just using one of the root finding algorithm. Public static void test1. So let's we already have this roots project. In the roots project, we have the real root function and then the real root. So I'm going to give a dependency, go to the build path, give a dependency to roots, and now I call the real root function. Let's call this func, which is equal to t goes to, or x for example, goes to x times x times x times x times x 5 times plus x minus 1. All right, minus 1. So we are getting x to the 5th plus x minus 1 equals 0. Okay, and then we have real root object. Let's call it root finder equals new real root. So we pass in our function, okay, and then double result equals root finder dot bisection, and we already know that the root is between 0 and 1, and then sys out result. So this is the exact result, 0.75487766. So let's copy this, put it here as the exact value. So this is the exact value, okay? Now, let's try to solve this and find the root using perturbation theory. So the perturbation theory says introduce a new parameter epsilon in the system, in the equation. So I can put an epsilon here, epsilon times x to the 5th plus x equals 1, or introduce an epsilon here at x to the 5th plus epsilon x equals 1, and or introduce the epsilon here, so x to the 5th plus x equals epsilon, right? Now it turns out the best case here is the second one. So introduce the epsilon at x. So let's look at that case, x to the 5th plus epsilon x equals 1. All right, and then when we do that, so this is our general hard problem with the degree of freedom epsilon, and if I set epsilon to 1, I end up with this, right? So the solution to my hard problem happens when I set epsilon to 1. And then we write the general solution of this as a function of epsilon. So x of epsilon, which is going to be the root, is a summation from 0 to infinity of a n epsilon to the n, okay? Now if I set epsilon to 0, x of 0 is basically a0. So a0 is the solution when I set epsilon to 0. And I already know the solution, and that's the whole point. When we set the epsilon to 0, the hard problem is supposed to become a simple problem or easy problem. So x to the fifth equals 1, so the solution is 1. So a0 is 1. And then what we do, we put this sequence series into the into this problem, and then find the coefficients in a recursive way, right? So a1 turns out to be minus 1 over 5, a2 turns out to be minus 1 over 25, a3 turns out to be minus 1 over 125, a4 turns out to be 0, and after that the other coefficients become positive, and then 0, negative, 0, positive, etc. So a5 is 21 over 15, 625, a7 is 78, 78, 125. So as you can see, there is some sort of oscillation or alternating of the sign happens. But now what we want to do, we want to sum these up, right? a0 plus a, because when I set epsilon to 1, and it turns out that if you try to calculate the radius of convergence for this series, it's greater than 1. It's like 1.6 something. So setting epsilon to 1 causes basically gives us a converging sequence, so no problem there. All right, but let's try to actually numerically sum this sequence up and see what we get, and then try to, because the sign of the terms kind of alternate or oscillates, we apply Aitken or Shanks and see what happens then. All right, so let's go to Eclipse here. So in test 2, public static void test2, I'm going to create an array, let's say of double a equals so a0 is 1, a1 is minus 1 over 5, a2 is minus 1 over 25, a3 is minus 1 over 125, a4 is 0, and then a5 is 21 over 15, 625, 21 over 15, 625, and let's go back one more time. A6, it should be 78, 78, 125. 78 over 78, 125. All right. So I have A0, A1, A2, A3, A4, A5, A6. Okay. Now let's try to sum this up. So let's create a sequence. Just and let's import it. Okay, we don't. So let's call this a sequence. Okay. So basically n goes to series dot okay, we need to import it, and we also need to import series dot sum from okay, now we, in order to create the a sequence, n just returns an. All right, so I'm just returning the index of this array, and for the sequence, if you recall, we defined the variable as a long variable, so I just cast it to int because arrays are defined over int. And then let's call the partial sums a partial sum, and it's going to be a sequence. The partial sum is also a sequence, and basically n goes to series dot sum over a sequence. We're going to sum from 0 to n. All right, and then for int I equals 0, I less than a dot length, I plus plus, we're going to sys out A partial sum evaluate at I. So let's see what we get. Test 2. And maybe let's also do the exact here. Alright, so the exact was 0.754877, and then we see that when we sum these terms for the sequence that came out of the perturbation analysis, the first is 1, 0.8, 0.76, 0.752, 752, 753344. So as you can see, we're definitely getting closer to the exact result. And we expect that because this sequence turns out to be a convergent sequence. It doesn't diverge, it converges, because the radius of convergence for the original perturbation series is greater than 1. And the last term is 7543, 424. And the exact result is 754877. So we get about 3 decimal places of accuracy. Now let's say we want to get a better approximation. How do we do that? And that's where the power of the sequence transformations come into play. In most physics problems, let's say you have a Schrödinger equation, you try to solve it using perturbation theory, okay? You are very lucky if you are able to calculate up to the 5th or 6th term, okay? Here we get 0, 1, 2, 3, 4, 5, 6, right? So you would be very lucky. So let's say we got lucky in this problem and we got these coefficients, but after the A6, the rest is, let's say we are just unable to calculate them. The question is, how much information does just these 6, 7 have? Can we just somehow extract a very accurate result just using these 6, 7 terms? And the answer is yeah. Let's try sequence transformations. Why not? And because of the alternation in the sign, we're going to use Aitken or Shanks. Let's try Aitken. So I'm going to create a new sequence. Let's call this BSEG, which is taking the A, and we're going to, you remember we applied this on the partial sum. So let's call this Aitken sum, Aitken partial sum. And we're going to get the A partial sum and call the Aitken on this, alright? And it returns a sequence. And remember, Aitken uses basically the nth term, n plus 1 and n plus 2. And now we have up to A6. So for Aitken, we can use, if I have A6, I can use Aitken 0, Aitken 1, Aitken 2, Aitken 3, Aitken 4, and Aitken 4 up to here, because Aitken 4 uses A4, A5, and A6. So I cannot go beyond this because I don't have the rest of the terms. But now let's see what happens. So let's call this partial or A sequence. And then we're going to do Aitken partial sum. And obviously the length was 6. I have to go twice down that because Aitken uses at index n, it uses n plus 1, n plus 2. All right. All right, let's see what happens. Okay, the original A sequence turns out to be you see Aitken from the very start, from the very beginning, it's already 0.75, which is good because because it's already 2 decimal places of accuracy, unlike the original sequence that started from 1, went to 0.8, went to 0.76. all right, but then it kind of stays there, doesn't add much, and then eventually it becomes 0.7572. So eventually it ends up with 2 decimal places of accuracy, whereas the A sequence, it has at least 3 decimal places of accuracy. Let's try now let's try to go with Shanks. So Shanks partial sum, A partial sum, we're going to Shanks it, and then Shanks partial sum. And but remember, for Shanks we have to start from 1, because at n it uses so let's write the comment here. For Shanks, it uses n minus 1, n, and n plus 1. So if I have A0 to A6, I can have S1, S2, S3, S4, and S5. okay, so I can go from 1 to so the length of A is 7. Actually, I think we could for 8can we could go higher, so let's try it again. No, we end up with an array index out of bound. Okay, so for Shanks, we still end up with the same thing as 8can, so there is not much difference between Shanks and 8can. But let's try to do 8can again. So we try a new sequence 8can 2, and we get 8can partial sum and 8can it again. Now we have basically what are the indexes? Now we can go to 3, right? Because A0 uses 0, 1, 2, A1 uses A1, 2, 3, and A2 uses A2, 3, 4. So we can go to 2, and let's see what happens here. So we are using the second order 8can, so, or applying 8can twice, 8can 2, or 8can 8can 2. Array index out of bound. Okay, so we should go to 4, I believe. Or 3. No, so we should go to 4. So the original sequence is like this. 8can sequence is this, and then the second 8can is something like this, 7, 5, 2, and we have 7, 5, 48. So as you can see, we're pretty close. Not as close as the original sequence, but still just by applying 8can one time we get 0.75. And you probably can see that the problem here is that there is a 0 here, and that 0 causes the 8can. So but what happens if we use Richardson? So let's try Richardson. So we do Richardson, we get a partial sum, and then call, let's say, Richardson. And Richardson uses n plus 1. So Richardson, the first order Richardson uses n and n plus 1. So we go to a dot length minus 1. Richardson partial sum, evaluate. Okay, so Richardson starts from 0.8 and then 0.72, and let me see if I can put this here, for example. Let's minimize this, and also minimize this. All right. So Richardson starts from 0.8, 0.72, 0.736, 0.752 basically, 0.7587, 0.7593. So it kind of gets away from the exact root, the exact solution, which is 0.7548. So it just seems to increase more and more. But 8can and 8can 2, they remain around 752. Okay. And what you can see, it's what is very interesting here is that the first three terms of the sequence are 1, 0.8, 0.76, which has a relatively large error, right? But then the first 8can is about 0.75, which is much closer. And if I just use 4 terms of the sequence, I still end up with 0.75. Okay. So this shows that we can in fact use perturbation theory and combine it with the power of sequence transformation to be able to accelerate the result of the perturbation theory. And again, understanding sequences and series are very interesting and very important. So I hope you enjoyed this lecture, and stay tuned because I will have more lectures coming soon. And thank you for watching, and I'll see you in the next one. Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue the discussion on numerical integration, and one of the interesting topics is Romberg integration, which I like to call trapezoid integration on steroid, because what we are going to do is to use Richardson acceleration or extrapolation. Let's call this acceleration. To apply the Richardson acceleration to the trapezoid method. So if we choose n number of subintervals for trapezoid method, then we end up with a partial sum, and then we can apply a Richardson acceleration. Why? Because as we discussed before, the typically the sequences that we have for Richardson for numerical integration, they have the error has a format of some number over n to some power, and because of this behavior we can apply Richardson acceleration. And in our discussion on the Richardson transformation of sequences, we said that Richardson of the first order eliminates the first leading term. Richardson of the second order eliminates the first two leading terms of the errors, and the third order eliminates the first three leading terms of the error, and Richardson of the fourth order eliminates the first four leading terms of the error, and it becomes more and more accurate. So what we are going to do in the topic of Romberg integration here, we're going to write the trapezoid down with some specified number of subintervals, and then apply, for example, a Richardson, fourth order Richardson, to the summation, to the partial sum that is being produced by trapezoid, and that should hugely accelerate the convergence and the accuracy with just a very small number of subintervals. Okay, so in most cases Romberg integration is defined on the trapezoid method, but in fact any method for a numerical integration generates a partial sum, right? And the integral, the value of the integral is the limit of that partial sum or a series, right? And we can apply the Richardson acceleration to any of those methods, like rectangle method, trapezoid, or Simpson. Okay. Now, I mean, in general, Richardson extrapolation generates a recursive formula for n and m. M is basically the leading order of the error, and n is the number of subintervals, I believe. And then because this is recursion, we can use caching or memoization, right? And Rn and Nm is basically the zeroth term, which is applying one subinterval to the original function. Therefore, it's just the length of the interval b minus a times the average of the function values at both ends, fa plus fb over 2. This is a trapezoid formula for only one subinterval. And but again, I don't recommend doing recursions, because we have already implemented very powerful tools for creating sequences, working with sequences, and applying transformation to sequences. All right. This brief introduction is from Wikipedia. So it says, in numerical analysis, Romberg's method is used to estimate the definite integral by applying Richardson extrapolation repeatedly on the trapezium rule or the rectangle rule. So it's not just specific for trapezoid. It could be trapezoid rule or rectangle rule. And the estimates generate a triangular array. Romberg's method is a Newton-Cotes formula. If you recall, Newton-Cotes formula means it works on a uniform partitioning of the original interval, so it evaluates the integrand at equally spaced points, uniform partitioning. The integrand must have continuous derivatives, though fairly good results may be obtained if only a few derivatives exist. If it is possible to evaluate the integrand at unequally spaced points, non-uniform partitioning, then other methods such as Gauss quadrature, which we have already discussed, Gauss-Legendre quadrature, and Clenshaw-Curtis quadrature are generally more accurate. So if there is no reason to stick with uniform partitioning, it's better to use quadrature methods because they are generally more accurate. But just in terms of Romberg integration, typically I don't recommend doing recursion or recursive implementation if there is a straight implementation is possible. So what we are going to do here, we're going to create a method Romberg in our integral 1D class, which takes a start n value and the number of subintervals. And then what we are going to do first is creating a sequence, which is called trapezoid sequence. This is the partial sum for the trapezoid rule. So if you recall, this trapezoid method in integral 1D just sums up, adds n terms based on the number of subintervals. So if we have subintervals, it adds n terms of the trapezoid. And then what I'm going to do is create a new sequence, Romberg sequence, by taking the original trapezoid sequence and apply a fourth order Richardson acceleration. Okay, and then I'm going to return this and evaluate it at the number of subintervals, which is our n, right? We divide the original interval into some number of subintervals, and as the number increases, of course, the error becomes smaller and smaller. And then what I'm going to do, I'm going to also apply that to, for example, Simpson, and I'm going to plot the convergence as the function of subintervals. All right, so let's head to Eclipse and try to do that. In the integral class, in the integral project, I have integral 1D, and if you recall, we had the previously implemented the forward rectangle, backward rectangle, center rectangle method, trapezoid, which takes a start value, end value, and the number of terms or subintervals, and it uses uniform partitioning, if you recall. Simpson, the same thing, start, end, number of subintervals, it uses uniform partitioning. And then we had the Gauss-Legendre 3 points, Gauss-Legendre 5 points, and Gauss-Legendre that asks for the number of quadrature points, or Gauss-Legendre that by default uses a 5-point Gauss-Legendre but works with 100 subintervals. So what I'm going to do here, I'm going to create a method public double Romberg, double start, double end, and int num sub intervals. All right, and then in order to use the sequence class in the sequence project, sequence interface is an interface that we already have developed. It's an in functional interface, has only one public abstract method, and the rest, which are all the transformations that we defined on the sequence, are based on like default methods, so they don't change the status of the sequence of the interface as a functional interface, which is a great thing. So what I'm going to do here, I'm going to give a dependency on the sequence project, so build path, and in the projects I'm going to add a dependency on the sequence. All right, now I'm going to import the sequence and call this trapezoid seq. Is I just say n goes to trapezoid method, start, and n. This should be n. All right, and this argument, let's just call it subintervals. Now this trapezoid method takes an integer, but here for the sequence the parameter is long, so we just do a typecast to integer. All right, now I create a new sequence, let's call this Romberg sequence, and it's basically taking the trapezoid sequence and apply a Richardson fourth order, and then return Romberg sequence and evaluate it at subintervals. All right, so subintervals in integer is integer. This takes a long, so there is an implicit casting here, which Java, the compiler, automatically does that. So the compiler automatically does implicit casting, because there is no loss of information when you go from int to long, because long is a bigger number than integer. It has 64 bits, integer has 32 bits. So there is no loss of information, and Java compiler automatically does the implicit casting for us. All right, so this is the Romberg. So there is no recursion. We're doing purely summation and sequence stuff, and that's very completely straightforward. Now I can do, for example, apply Romberg on forward rectangle, and pretty much everything remains the same. Instead of a trapezoid sequence, we have forward rectangle, forward rect sequence, and this goes to, we call the forward rectangle method, start, and n. All right, and again the number of subintervals is n, and we have to cast it to int because the sequence is based on long. And then we calculate that, we apply a fourth order Richardson, and evaluate the number of subintervals. And again, you see how beautiful this is and how simple this is, using this concept of sequence interface, and then all these transformations are already defined in the sequence interface as a default method. So we're taking advantage of lambda expressions, the power of lambda expressions, and also the power of evolving an interface using default methods, so adding more capability to the interface. All right. Okay, great. So let's create a test class, test Romberg, and here in the I'm going to invoke test1, and test1 is going to compare the convergence of forward rectangle and the Romberg forward rectangle, which means we apply fourth order Richardson on the forward rectangle method. Public static void test1. So let me just note it that forward rectangle and Romberg on forward rectangle. Just note that we could define any order of Richardson as any order of Richardson transformation, the first order, second order, third order, fourth order on the original partial sum sequence. Here I'm basing the Romberg integration on the fourth order Richardson acceleration. All right, so maybe let's also write it down. So fourth order Richardson acceleration. Sometimes higher order Richardson accelerations cause instability, but I believe in most of the cases for well-behaved functions, when we are doing numerical integration, the fourth order Richardson should be pretty stable. So let's do this. So what I'm going to do first, I'm going to obviously create an integral function 1D func t goes to t times t, so we're just doing t squared, and then an integral 1D object, integral new integral 1D, we pass in the function, and then double result forward rectangle is integral forward rectangle from 0 to, let's say, 5, and then let's say 10 terms. Now we already know the exact, right? So let's create an int method. Int is num intervals, let's call it 10, and then from 0 to 5, so we already know the exact. Double exact is, so the antiderivative is t cubed over 3, and from 0 to 5 is 5 times 5 times 5 over 3. All right, so sysout exact plus exact plus exact, and then sysout forward rectangle equals result forward rectangle. And finally we're going to do Romberg. So double result Romberg is basically integral Romberg on forward rectangle from 0 to 5 and 10 subintervals, and then sysout Romberg and result Romberg, and we're going to set this to num intervals. So the exact value is 41.66666. The forward rectangle with 10 number of subintervals gives us a very poor accuracy, 35.625. But when we apply the fourth order Richardson acceleration on the forward rectangle, we pretty much end up with a very good accuracy, at least 8 decimal places of accuracy. 3, 4, 5, 6, 7, actually 10 decimal places of accuracy. So this is unbelievable. Such a powerful Richardson acceleration, such a very simple concept, but extremely powerful. So we are only using 10 sub-intervals, and we're getting like crazy accuracy. So if I increase the size of the interval, we know that smaller sub-intervals will result in a larger error. So let's see. Okay, so double start, double end 50. So let's just parameterize this. Start, end, start, end. Again, you probably can see that we're doing only 10 sub-intervals. The exact value is end times end times end divided by 3. Actually, let's write it at minus start times start times start divided by 3. So the exact value is 41,666.6666. Okay, the forward rectangle has a very poor accuracy with only 10 sub-intervals. The Romberg, basically fourth order Richardson acceleration on the forward rectangle, basically gives us the exact result. So 3, 6, 7 decimal places of accuracy, which is extremely good. And so let's set this to 5 again. And what I'm going to do, I'm going to plot. So let's try to plot the so what I'm going, let's call, okay, let's create another method. Actually, let's go full screen. Let's create another method, test2, and invoke test2. All right, and in test2, what I'm going to do, I'm going to vary the number of sub-intervals, and then we don't care about, okay, we do care about exact, because I'm going to plot the error, and then result forward, result Romberg, and then let's set and start and end, and then we create an array of double indices is new double, let's say 100 or maybe 50. We're going to sum from 1 sub-interval to 50 sub-intervals, and then for int I equals 0, I less than indices dot length I plus plus, we're going to say that indices I is basically I plus 1. All right, so the 0th index is 1 sub-interval, etc. And then we're going to create a new double, which is forward rect new double indices dot length, and double Romberg new double indices dot length. All right, and then for int I equals 0, I less than indices dot length I plus plus, what we are going to do here, number of sub intervals is I plus 1, and then all right, we do have this exact thing here. So we're going to say that, okay, forward rect I equals that, and then Romberg I equals that. All right, and then of course we create a MATLAB chart, fig new MATLAB chart, fig.plot indices forward rect and blue, fig.plot indices Romberg and red, and then fig.render plot, fig.marker on, and fig. So what I want to do actually, I want to plot the error math.abs integral this minus exact, and the same thing here, math.abs integral minus exact. So that's my plan. Log set x-axis to set y-axis to log, and then fig.show with a true flag. All right, so what I'm going to do here, I'm going to run this, and then all right, let's not do the log, and it doesn't show because I'm on Mac, so I have to go and uncheck this flag in the VM arguments. All right, so as you can see, the blue one is the error of the, it's fascinating that the Romberg's is basically the exact, and it should be exact because we know that the for the polynomial the polynomial only has 1 over t squared has only 1 over, if we calculate the error, it has only 1 over, most likely from 1 over n error and 1 over n squared. It doesn't have n cubed or n fourth. All right, and we know that a fourth order Richardson acceleration removes 4 leading terms, and for t squared we only have at maximum 2 leading term error. So the Romberg, even from the beginning, it gives us the exact result, and that's a very good thing. So let me just add some labels here. Fig dot x label number of sub intervals, fig dot y label and error. So Romberg, okay, error. So maybe t squared is not a good function. Maybe let's try something more interesting like sine. All right, so as you can see, so the blue one is the forward rectangular approximation. Let's also increase the font. Fig dot font size, let's say 15. So the blue one is the forward rectangular approximation based on the number of subintervals. You see that the error is relatively large, but then the Romberg, basically fourth order Richardson, after 4 or 5 terms, it's just it's unbelievably fast converging to the result, right? So it's great. So let's copy this, put this here. Okay, so the red one is going to be Richardson on forward rect. Okay, and the green one and the blue one is going to be forward rect. Forward rectangle. Okay, now let's try to use Romberg on the basically on the trapezoid. So clearly we're going to create a new test. Here we'll call it test 3, and we're going to do trapezoid and Romberg on trapezoid, which is the original definition of Romberg. So we're going to have refactor rename trapezoid and Romberg. Okay, we're going to call trapezoid method, and then we're going to call the original Romberg method. And let's run test 3. Alright, as you can see, trapezoid has a basically faster convergence than forward rectangle. So after 10 terms it's pretty close, but again the Romberg or the Richardson acceleration is much faster, right? After 5 terms it's pretty much there, whereas the original trapezoid is after like 20-25 iterations it's getting there. So we are definitely accelerating the numerical integration by a lot. Okay, so here we have so the red one is still Richardson on trapezoid method, and then the blue one is just the original trapezoid method. Okay, and we can clearly see that using the Richardson acceleration can enhance the rate of convergence by a lot, and that's a very good thing, because then we don't need to divide the interval into many sub-intervals, and that helps a lot in terms of computation. Of course, we're paying some computation penalty on doing the basically the transformation, because it involves a few multiplications, divisions, basically just multiplication, right? And we have to take 4 terms and then multiply them. But at the end of the day, the fact that we are eliminating the leading terms of the error, 4 leading terms, causes a huge improvement in terms of actually why is the error okay, so we made a mistake. So the exact is actually minus cos, so it's the is this cosine of a start minus math dot cosine of end. So I made this mistake also in test 2. We use sine, so the exact, because remember we were plotting the absolute error. So yeah, now the error goes to 0. Let's plot it on the log scale. Test 3. Okay, so this is a much better way of seeing it. Let's copy this. This was for trapezoid, the absolute error. Okay. Send it to back. So the blue curve here is the original trapezoid estimation, and you see that after 50 terms it only gives us almost 2 decimal places of accuracy, but then we apply fourth order Richardson and we end up with a huge number of decimal places of accuracy. As I mentioned, for fourth order Richardson, we do get some instability in terms of some small oscillations happen, but the error is pretty good. After 35 terms, we get about 3, 4, 5, 6, 7, 8. We get more than 8 decimal places of accuracy. And let's do the same thing with test 2, which compares the forward rectangle and the Romberg on forward rectangle. Alright, so let's run test 2. And again, you see the forward rectangle is painfully slow. After 50 terms, we don't even get 1 decimal place of accuracy. But using fourth order Richardson acceleration, we get more than 1, 2, 3, 4, 5, 6, 7, 8, more than 8 decimal places of accuracy. And we're not doing much, we're just doing a very simple sequence transformation. You see, I want you to really understand and observe the power of sequence transformation. That's incredible. And for numerical integration, Richardson is the transformation to go with. Alright, so this red one is Richardson, fourth order Richardson on the forward rectangle, and this blue one is just the forward rectangle, which is painfully slow. All right, so I hope you enjoyed this lecture on numerical integrations using sequence accelerators. Please stay tuned. I have more lectures that will come soon, and I hope to see you in the next one. Thank you. Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on sequences and series. And I'm going to discuss the ideas of rate and order of convergence. So for example, let's start with a sequence that has this monotonous behavior, and it's more like a non-oscillatory behavior as n grows. And we saw that such sequences are suitable for Richardson acceleration, and the error model or the asymptotic behavior of the sequence as n goes to infinity is the limit plus some constant over n to the b, and b should be greater than or equal to 1, otherwise the sequence might diverge. And then if a is positive, then the error is always remains positive, so we are always above the actual limit, so the sequence approaches the limit from above. And if a is negative, and then we are approaching the limit from below. All right, so in general we can write this asymptotic behavior for our sequence as n goes to infinity, similar to a limit plus some number over n to the b plus some other number n to the b plus 1 plus some other number n to the b plus 2, etc. So n to the b is the lowest term in terms of the power or degree that defines the behavior of the error, right? That's the dominant term for the error. And we say that 1 over n to the b or a over n to the b is the leading term of the error, which is typically what is actually defining the behavior of the error. And then b is the order of convergence or the strength of convergence. Obviously, the higher the b, the larger the b, the faster the error goes to 0. And if we also discussed that when we apply a Richardson, first order Richardson acceleration, what happens is that we kind of get rid of this first leading term, and then the next term, n to the b plus 1, becomes the leading term of the error. So the order of convergence increases, which means that now the error has a faster reduction, or the error goes to 0 faster, or the new sequence goes to the same limit faster. That's why we say that the Richardson transformation actually accelerates the convergence. But then there is another idea of rate of convergence, and that gives us a fundamental thing about the behavior of the sequence. If we already know the limit of a sequence, and then we take the limit as k goes to infinity, ak plus 1 minus l, this is error for the term k plus 1, and then ak minus l, so this is the error for the kth term. All right, so error at k plus 1 divided by error at k, and that's a new sequence, so we can take its limit, and let's say this limit exists and it's a number, it's a real number mu. All right, and it's typically between 0 and 1, and the reason is that for a series to converge to the limit, we know that eventually the error must go to 0. That means that at some point for a very large k, ak plus 1, the error at k plus 1 must be less than error at k. All right, so this sequence decreases, so it converges to a number between 0 and 1. And if this number exists, this limit exists, we say that we have a linear convergence. Okay, and then if this number mu is equal to 1, we call it a sublinear convergence. So in general, mu, anything between 0 and 1 is a linear convergence. Exactly equal to 1 is sublinear convergence, and if mu turns out to be 0, which is what we really like, is called superlinear. That shows that the error of the convergence is not linear, it's actually going down by power more than 1, which means ek plus 1 over ek to, let's say, to the power of 2 or 3 or etc. That's a very much faster convergence. So linear convergence, a number between 0 and 1, sublinear exactly equal to 1, and superlinear exactly equal to 0. And one special case of sublinear, which is the worst of worst, is the logarithmic convergence, and that's when not only this limit is 1, but also when we take the ak plus 2 minus ak plus 1 over ak plus 1 minus ak. So this is the relative error, right? This is equal also to 1. That means not only the acceleration, the convergence is not fast, but also it's less fast, or it's slower than we anticipated because of how these terms behave relative to each other. Okay, so linear, sublinear, superlinear. And unfortunately, when we talk about calculus or numerical analysis, numerical differentiation and integration have sublinear convergence, and this is a problem because most of the time using these numerical tools on sequences and series, we want to solve differential equations, and in order to do that we have to either do numerical differentiation or numerical integration, and a sublinear convergence is a pretty slow convergence, so we have to increase n, or we have to increase the number of steps that we take. And we don't need to worry about that because we have already very powerful tools for accelerating the convergence, which is the Richardson extrapolation, because as we mentioned before, the behavior of the sequences that we end up with in numerical differentiation and integration typically follow this error behavior, 1 over n to some power, and then these are suitable for Richardson acceleration. Okay, so we said that Richardson acceleration or Richardson transformation is suited for sequences that have this kind of behavior, 1 over n to the b. And if you start with this behavior, L plus a over 1 to the n to the b, and then put it here, we see that this limit, this fraction is basically n to the b over n plus 1 to the b as n goes to infinity, which is basically 1, right? Regardless of what this a number is. Therefore, sequences with this behavior are always sublinear, and again, that's why I'm saying that the numerical differentiation and integration have sublinear convergence, because they typically follow this error model. and this error model is always sublinear. So if we have this sequence L plus A n to the b plus a1 n to the b plus 1, which is the error model, and we take the leading term here and put it in this limit, in this definition, it's always 1. So Richardson suited sequences typically have sublinear convergence, and we definitely don't like sublinear convergence because it's a very slow convergence. That's why we apply Richardson transformation. And then the problem here is that sequence accelerators do not change the rate of convergence. They only change the order of convergence. And what I mean by that is that we know that this original sequence with this error model has a sublinear convergence. And then if I apply the Richardson acceleration, let's say we get rid of this term, the limit is still the same. So we end up with a new sequence that is L plus some number n to the b plus 1, etc. And the order of convergence has increased, which means the error goes to 0 faster, but the rate of convergence with this definition is still 1, so the sequence is still sublinear. Similarly, for the sequences that have an oscillatory behavior or oscillatory error model, we said that those are suitable for Aitken or Shanks transforms, and then if we put it here, we see that this error model, some number to the nth power, has a limit of magnitude absolute value of b, and in order for this sequence to converge or the error term goes to 0, b must be less than 1, all right, the magnitude of b. And this is a linear behavior, not sublinear, because b is not exactly 1, but still it's not a superlinear, it's sublinear, and we know that the smaller is the better. So the smaller the b is, we are getting closer and closer to a superlinear behavior. So this error model b to the n has a faster convergence compared to the 1 over n to the b, for example, because the rate of convergence here is b, which is less than 1. The rate of convergence here is exactly 1. All right? And this is also another reason why if a sequence is suited for Richardson, Aitken or Shanks don't really work on the acceleration for those sequences because the rate of convergence are different here, b and 1. And even if we apply Aitken or Shanks on this oscillatory behavior, the rate of convergence remains the same. And because the rate of convergence of these two types of error models, these two types of sequences are fundamentally incompatible, 1 versus magnitude of b, we cannot, if we apply one transform on the other one, there is no gain, because in order for these transforms to work, the rate of convergence must be compatible. All right, so here I'm just showing the Richardson and Shanks, for example, or Aitken. Richardson takes an and transforms it into bn, and if we go through with the transformation and the definition, we see that basically what happens is that bn has an error model whose leading term is n to the b plus 1 instead of n to the b. And if we take the limit or try to find the rate of convergence for bn sequence, which is the Richardson transformation of an, we end up with 1. Again, Richardson transformation does not change the rate of convergence. It changes the order of convergence. Similarly, for the Shanks or Aitken, if an is a sequence with this error model, bn is also a sequence after applying Shanks whose error model starts with b to the n plus 1. And if we take the limit, find the rate of convergence for bn, it's still absolute value magnitude of b or absolute value of b, which is less than 1. So Shanks transform, all these transformations, they don't change the rate of convergence, they change the order of convergence. Shanks transformation does not change the rate of convergence. And that's the fundamental thing that we need to know why these are not compatible. If I apply Richardson to an error model with this behavior, I'm not getting a good result because Richardson is suited for sublinear sequences, and Shanks work on the oscillatory sublinear sequences. Okay. Now we can formally define the order of convergence as this limit when we take ak plus 1 minus L divided by ak minus L to some power p as k goes to infinity. If this limit exists, it's a finite number, and we just call this mu, so it's greater than or equal to 0 and less than infinity. That means that the order of convergence is p, that's the formal definition, and p is typically greater than or equal to 1. And basically the best behavior or the ideal case is that p is very large and mu is very small, ideally 0, okay? So higher the larger the p and smaller the mu, we say that the sequence has a faster convergence because the error goes to 0 faster and faster. If p is 1, which is what we have so far, and mu is 1, it's a sublinear sequence or sublinear convergence. If p is 1 but mu is between 0 and 1, it's a linear convergence. If p is 1 and mu is exactly 0, it's a superlinear convergence. If p ends up to be 2, so for p1 mu is 0, but for p2 mu is something non-zero, is not exactly 0, we call this a quadratic convergence. If p is 3, so for p1 and 2 mu turns out to be 0, but for p3 mu turns out to be something non-zero, we say that it's a cubic convergence. And you probably can guess that quadratic convergence is much better in terms of speed of convergence compared to the linear convergence, and cubic is faster than quadratic, of course. And again, because in calculus we're dealing with differentiation and integration, we are mostly dealing with linear and sublinear convergence. Now, one interesting thing that we discussed when we talked about root finding algorithms was that the Newton-Raphson iteration, root finding iterations, are in fact quadratic convergence. That's why we always say that the Newton-Raphson or the Newton's method for finding roots is relatively fast method or algorithm, because you can mathematically prove that it's the errors of iteration go to 0 quadratically. So they follow this pattern of e to the ak plus 1 minus l over ek minus l to the power of 2. Okay, for power of 1 it's always 0, for power of 2 it becomes non-zero, so it has a quadratic conversion. So Newton-Raphson root finding iterations is quadratic, has a quadratic convergence, which is pretty good. For example, bisection and the other method like bisection, trisection, or secant method even, they have so bisection, trisection have linear convergence or sublinear convergence. Secant is superlinear but not quadratic. So when you write this limit for secant, p ends up to be something like 1.2, 1.5, something like that. It's not exactly 2. So here's one example. Let's say our error term is 1 over 2 to the n, therefore en plus 1 over en to the p when we take this limit. And it's something, if p is less than 1, we're definitely getting 0. If p is equal 1, we're getting 0.5, and if p greater than 1, the limit diverges, we get infinity, okay? And therefore this is a sublinear behavior, because for p equals 1, we get a non-zero number. So it's sublinear. And it's linear because p equals 1, and it's sublinear because the value of the limit, this mu term, is not 1. It's something between 0 and 1. And if we have, for example, 1 over 2 to the 2 to the nth power for the error, then en plus 1 over en to the p. For p less than 2, we get 0. For p equals 2, we get 1. And for p greater than 2, we get infinity, which means which means we have a quadratic convergence, right? Quadratic means for p less than 2, this limit should be 0, which is true, so it's definitely superlinear. And then for p exactly 2, we get some number, some positive number. Doesn't matter if it's 1, less than 1, or greater than 1. It's a quadratic, so this has a faster convergence than this one, all right? Now, how to estimate order of convergence, this p term? And one practical way of estimating p is take for large k, you can construct this sequence. Log of delta, delta is the forward difference, delta of ak divided by delta of ak minus 1. All of this divided by log of ak minus 1 divided by ak minus 2. This is the delta, right? We're calculating the this new sequence. This is basically a transformation on the sequence ak, right? And we're getting a new sequence, and as k goes to infinity, this ratio converges to the p. So this is one practical case. We just make k very large and see where it converges to, and that's p. How to find rate of convergence mu? The problem with the rate of convergence mu is that we don't know exactly the limit, because the original definition of mu is having the L, the actual limit. But then there are ways to look at the approximate error. So the exact error or the actual error or convergence is an minus the exact limit. But if we don't know it, we can define a new sequence, e tilde, which is an plus 1 minus an. Okay? This is basically delta an, right? This is the forward difference. And we already know that if the sequence, the original sequence goes to L, which means this en, the original error sequence, goes to 0, this approximate error also goes to 0. And you can prove that if the sequence is a superlinear, it has a superlinear convergence, then the limit of the en over en tilde is 1. That means that these two errors are equivalent to each other. So you can use this in the original definition and try to find mu. If you just search on Google for the rate of convergence and how to practically find it, you can find articles about this kind of approximations. All right. So for superlinear sequences, we can say that en is asymptotic to en tilde. That means that if we start with the forward difference sequence, it actually a good it's actually approaches to the original error sequence. All right. So let's go to Eclipse and try to apply this definition for the order of convergence for some of our sequences. So here in Eclipse, let's go to our sequence, and we have the sequence interface with all the methods and the transformation and the operator overloading. We have the series class that sums up the sequence. We have the Taylor expansion here that generates a sequence, a polynomial. And now let's say in the tests we try to create a new class, the test order of convergence, and we want to have a main method. And here I'm going to create a method, public static void test1, and here I'm going to invoke test1. Let's define a sequence and import it. Sequence sec1 is, for example, n goes to let's define a sequence 1 over n times 1 over n. So we're looking at 1 over n squared. Let's import this. Okay. And we know that if we create a sequence sec2, which is n goes to series dot sum over this sequence, and sequence from 1 to n, right? So we're creating a partial sum. And let's first look at the order of convergence for sequence 1. And we already know that this sequence converges to 0, so the L, the limit is 0. and then we know that basically this sequence 1 an is 0 plus 1 over n squared. So b should be 2 here, right? This is exact, and this kind of sequence is very suitable for Richardson acceleration, for example. And the rate of convergence is an plus 1 minus 0 over an minus 0, which is n over n plus 1 to the power of 2, which is 1. So it's a sublinear convergence, which is a sublinear convergence. And let's try to find the order of convergence. So in order to find the order of convergence, what I'm going to do, I'm going to create a new sequence, let's say Pn, and n goes to what we are going to do, math.log of sec1.diff, and we're going to shift it by 1. Okay, and if you look at the shift, it shifts forward, so we want to have shift by minus 1. So this is delta an, and we can shift it, or we can basically evaluate it at n plus 1. All right, let's go back to the PowerPoint. Actually, we want to evaluate it at n minus, okay, so we want to evaluate this at n, and then divide sec1 dot diff, we want to evaluate it at n minus 1, and then divide the whole thing by math.log n minus 1 and n minus 2, right? So we take the forward difference of the sequence, the original one, an, and evaluate it at n, delta evaluated at n minus 1, and then n minus 1, and then evaluated at n minus 2. Okay, and now let's try to plot this, plot Pn. So let's call this int, or maybe long, because these are long numbers. Okay, let's call this int. Indices new int, let's say 100, and then double p-vals is new double indices dot length, and then we're going to write a for loop, int I equals 0, I less than indices dot length, I plus plus. Here we're going to set indices I to I plus 1, and then p-vals I equals to pn dot evaluate at I plus 1. Okay, now the problem here is that this goes to okay, so let's start from 10, for example, and then we're going to evaluate at 10. All right, and then MATLAB chart, fig new MATLAB chart, fig dot plot indices and p-vals, fig dot actually this should be double, fig dot render plot, fig dot show, let's add it a boolean flag here, and this should be double. All right, let's see. Now I'm on Mac, so I have to go to the run configurations, VM arguments, and remove this check mark. All right, so as you can see at term 10, We are at 0.9 for Pn sequence, and we know that this sequence should converge to 1 because we already know that the rate of convergence is, the order of convergence is basically the order. So this sequence clearly converges to 1, and what we see that the rate of convergence is also 1. So this sequence can basically so in order for the rate, let's go back to the definition. So here we know that the sequence 1 over n squared is a sublinear has a sublinear convergence, right? In order for the sublinear, it means that the p must be 1 and mu is 1 too, right? So p must be 1, and the sequence that we are making, this log sequence, has to converge to 1, and that's exactly what we see here, right? So let me go to 500, for example. And let's run this. Yeah, it approaches 1 as we expect, right? And so the definition of order of convergence, and then this b here in the error model is not exactly the same. So it depends how you define this. Some people define this b as the order of convergence, but that's more like the order of error, how fast the error goes to 0. But in terms of the rate of convergence, this p here is also formally defined as the order of convergence. And what we see here is that for our 1 over n squared sequence, p goes to 1 as we expect, because that's a sublinear sequence. And the good thing here is that we can in fact accelerate p, because now pn is a sequence by itself, right? So let's say p, let's define a new sequence, pn Richardson, and we're going to apply basically take pn and apply a Richardson fourth order, and then p vals Richardson, new double indices dot length. Okay, and now here we are going to basically say p vals Richardson at I is pn Richardson, evaluate at 10. So let's give the first one a color of blue, and the second one a color of red. Let's also turn the markers on here. All right. As you can see, the Richardson pretty much converges super rapidly. Let me just add some titles. So X label index, and the fig Y label sequence pn. And as you can see, with the Richardson, we are pretty much there at 1 after just 10 terms. You apply your fourth order Richardson, calculate at 10, and we've discussed this before that for Richardson fourth order, as you increase the order of Richardson, there is a chance of oscillation or instability, which is very small here, but that still happens. So up to, for example, 50, 60, we don't really see this oscillation up to 40, but after that we see. But as we can see, Richardson acceleration is definitely suitable for 1 over n squared, for example, or even this log, even if this log sequence pn, and that gives us the order of convergence based on the definition of rate of convergence. Okay, so this sequence 1 over n squared is sublinear, so we should definitely have a p equal to 1. and p is the limit of this sequence, and it's definitely 1, right? Similarly, for this sequence sec2, for the partial sum, I'm going to change it back to sec1 and maybe remove this. Yeah, we cannot do that. What I want to set sec2 here, and then define the rate of convergence, the order of convergence for that. So here we define it based on sec2. Alright, so sec2 is just summing up 1 over n squared, and we know that this converges to pi squared over 6, and then the error model, if we estimate the error by integrating from n to infinity of 1 over x squared, the error model ends up to be 1 over n. Okay, so we still have a sublinear behavior. So let's see if that actually works. So we have indices Pn now defined for sec2, which is the partial sum of sec1, and then Pn recharge. Okay. Yeah, we are still getting 1. So even if we create a partial sum of 1 over n squared, we're getting 1. So that means that we are still at a linear or sublinear convergence, one of these two. And what is obvious here is that the fourth order Richardson transformation becomes unstable, and at very large n, as we expect, typically that happens. So, but as you can see, for a small index, it pretty much gives you the exact result right away. Okay, so definitely use these transformations. This also confirms that the partial sum of 1 over n squared from 1 to n has an order of convergence equals to 1, which means that it's either a linear or sublinear behavior. There is no other way. Okay. Now, if you recall, we had this sequence, let's say sec1, and we had this sequence that has an error of 1 over 2 to the 2 to the n. Okay, and we saw that it works for p equals 2. So let's test that too. So let's create a sequence, for example, 1 plus so n goes to 1 plus 1 over math.pav 2, actually 2 to the, so we take 2 math.pav 2 to the n. Okay, so our sequence has a limit of 1. The error is 1 over 2 to the n, and let's call it sec2, and let's see if this sequence in fact converges to 2. Alright, we're not getting anything because I assume that let's see, 1 over, let's try 10 terms. Let's just okay, so we're plotting p sequence, and let's see, 1 over 2 to the n, right? And maybe let's n minus 1, n minus 2, everything looks the same. Let's go like plus 20, for example. Let's remove this Richardson, see if we can calculate Pn correctly. No, it still doesn't give us anything. I assume that's because something becomes negative here. N minus 1 divided by, if we take the diff, n plus 1, that's definitely negative, n minus 1 over n minus 2. We can add an ABS of this and try to see if that works. No, it still doesn't work. But eventually this should give us a factor of 2. Okay, so this was the introduction or more general discussions on the rate of convergence and the order of convergence. And then we also said that if we know the error model, we can also define order B for the error as well, the convergence of the error. And we said that in particular we don't like sublinear convergence or even linear convergence, but then most of the time we're just stuck with this kind of behavior because of how differentiation and integration behave. Okay, thank you for watching. I'll have more lectures coming soon, so please stay tuned and I'll see you in the next one. Hello and welcome to another Java tutorial. In this tutorial I'm going to continue our discussion on Taylor series and Taylor polynomials. So far we have discussed that Taylor series are basically a polynomial series representing a smooth function, right? A function that doesn't have singularity at a given point. And then this is basically, Taylor expansion is basically a polynomial expansion at a given point, and the coefficients are, the terms are like 1 over n factorial times the nth derivative of the function at the point x0 times x minus x0 to the nth power. All right, and then and this polynomial to some order locally approximates the function, and it has a uniform convergence. It means that if the function doesn't have singularity, the series, the limit when we have infinite terms, it has to exactly match the function. Not only that, because it's a uniform convergence, we can term by term differentiate. So if I want to know the Taylor series of f prime, I calculate the Taylor series of f and take the term by term derivative. All right, and one example was the exponential function e to the x, and at x equals 0, e to the x is sigma n from 0 to infinity x to the n over n factorial, which is 1 plus x to the 2 over 2 factorial plus x to the 3 over 3 factorial, etc. And this has a uniform convergence for any x, right? So even though we're expanding at x equals 0, we can see that if I put, for example, x 100, this series should converge to e to the 100. Furthermore, if I take the derivative from left and right, so the derivative of left, e to the x, d dx is just itself e to the x. And then I can differentiate term by term from the series. So 1 becomes 0, x becomes 1, x squared over 2 is x cubed over 6 is x squared over 2. So eventually I get the same series, right? So it shows that the derivative of e to the x is e to the x, and the derivative of the series is again the same series. And we looked at one way to implementing the Taylor series in or the Taylor expansion in Java, which was the symbolic math library. And then we used the diff method for our symbolic math library that had some basic functions. And then let's go to Eclipse and try to recap on that. So in the sequence project, I have the Taylor expansion class, and here we had a function from our symbolic math project. A function is basically an abstract class that represents the an abstract function, right? And we have different types of function, cosine, cotangent, etc. All of them extend this abstract function. And we implemented operator overloading for this function, like add, subtract, multiply, and divide, and negate. So we can use operator overloading for this function. And in the Taylor expansion, we have a method called getSeries, and here we are just creating the result. So basically, we're calculating the Taylor expansion at x equals x0, and for n terms, or the degree of the Taylor polynomial is n, okay? And we start with a zero polynomial, and for the zeroth term, it's just the value of the function at x0, okay? There is no derivative. And for higher order terms, we create a copy of the original function, and then the overall polynomial for this ith term, we start with 1, and then we calculate the 1 over n factorial, right? For k equals 0, k less than I, k plus plus. We take the diff recursively, so this calculates the derivative of function I times, and then we also increase the power of x minus x0 by multiplying by itself, and then the factorial is just multiplies by k plus 1, all right? And then we have 1 over factorial times func copy. Func copy holds the value of the nth derivative or ith derivative, right? Remember, we have a for loop that runs over I, and times the polynomial x minus x0 to the power of I, okay? And then we return the result, and we can quickly test it. So here, let's just maybe create a test class, test Taylor series, and let's have a main method, and I'm going to invoke test1 here, and we're going to have a public static void test1, and here I'm going to define a function. Let's call this func is and I'm going to I'm going to do a static import, basically symbolic math from if you recall, in the function space we defined methods that return this function. So from function space, I'm going to import all the functions we have already defined. Let's also import the function, all right, the symbolic function, and let's call this let's say sine of x, all right, plus cosine of x, or maybe something more fancy like sine of x times sine of x. And then we're going to plot this first. Double x vals is mathutils dot line space from minus math.py to math.py, and let's say 1000, and then double func vals is array func dot apply the real function. T goes to func dot evaluate get value at t, and then apply to the x vals array. And then we're going to have a MATLAB chart, fig new MATLAB chart from mathlib project, and then fig dot plot x vals and func vals, okay, and then fig dot render plot fig done show with a true flag. And then I'm going to run this, and it doesn't show the figure because I need to go to the run configuration, and in the VM arguments I'm going to remove this check. All right, so this is x-axis and this is the function. We're plotting sine squared, and all right, now let's try to get the Taylor series around x equals 0. So in order to do that, I'm going to create a Taylor expansion object, Taylor expansion, new Taylor expansion. I'm going to pass our function here, and then I'm going to create a polynomial and Taylor series or series Taylor polynomials, and we're going to call the Taylor expansion get series, and around 0 we're going to have 5 terms, and sys out Taylor series. Okay, so let's run this. We get x5 0, x4, x3 0 again, x2, x0. So as you can see, we only get the even orders, and that makes perfect sense because it acts like a even order root around 0, right? Quadratic or fourth order, so it doesn't have fifth order or third order or first order. And we can also plot this. So double Taylor vals, we're going to apply array function, apply t goes to Taylor series dot evaluate at t, apply it to x vals. All right, and so I'm going to plot the function with color blue, fig dot plot x vals, and then Taylor vals with color red. Yeah, as you can see, the blue one is the function and the red one is Taylor expansion, fifth order, and as you can see, it can approximate the function better. Now if we go to, let's say, 10 terms, and we see that it probably gets so it covers a wider range. And we already know that this sign function is analytic function and it doesn't have any singularity, but so the Taylor series must converge to the entire function at any given point, even though we're expanding it around 0 as we add more and more terms. All right, that's the whole idea of Taylor. But now there's another question about if I expand the function f of x around x0, so I get x minus x0 terms, right? The question is, if I cut it at some point, let's say n terms. Now basically the idea is that if my function has singularities and I expand the function at around some point, how far from this point the series actually converges to the exact value of function, and that defines something called the radius of convergence for Taylor series, or in more general sense for power series. We said that Taylor series has a uniform convergence, which means you can apply term by term algebra. So if I have two functions, f of x and g of x, and both of them at x0 have Taylor series, all right? The coefficients are fn for f of x and the coefficients are gn for gx. Now we can add and subtract Taylor series. So if the Taylor series of f plus g is exactly the same series, the coefficients are fn plus gn. The same thing for subtraction, fx minus gx, the coefficients are fn minus gn. We can multiply or divide by a number. So if I multiply the function by some constant number, the coefficients of the Taylor series get multiplied by the same number, term by term. We can differentiate term by term. So if I know the Taylor series of f of x, the Taylor series of f prime is just differentiating by term for this series, the term. So the coefficients are n fn x minus x0 to the n minus 1, all right? And n starts here from 1. So if I shift it to 0, and then I get n plus 1 fn plus 1 x minus x0 to the n, right? So I can find the coefficients of f prime. But then in the discussion of convergence of the series, we said that if I have a series of sigma n from 0 to infinity of some sequence, because as soon as I plug in some number for x, this becomes a sequence, right? The terms are fn x minus x0 to the n. All right? The necessary condition is that as n goes to infinity, the generating sequence, which is fn or an here, x minus x0 to the n, this sequence must go to 0. The limit of this sequence must go to 0. Okay, and this is very important. And if that's the case, then we can find how far from x0 we can go such that this limit goes to 0. And because this is a power series, if this goes to 0, we are guaranteed that the Taylor series converges. Okay, so we can define a radius convergence, which has the meaning of how far from x0 can we go so that the limit of the generating sequence still goes to 0, so that the series still converges. And we can take the square root of an, nth root of an times x minus x0, all of it to the power of n. Okay, and that should remain less than 1 as n goes to 0. So the radius of convergence is 1 over the limit of n goes to 0 square root the nth root of an, and an is basically 1 over n factorial times the nth derivative of f, right? Here an represents fn or gn, and fn, the coefficients of Taylor series are 1 over n factorial times the nth derivative of the function at the point x0. all right, this tells us how far from x0 can we go so that the power series, the Taylor series, still converges to the value of the function. And typically this is not and this is called Cauchy-Hadamard theorem, that tells us the radius of convergence for a power series of the form fn or an x minus x0 to the power of n. If an's have the same sign as n goes to infinity, they don't oscillate or change sign, then r is equal to limit of an over an plus 1, the ratio of two consecutive terms. We take that limit. If n's have alternating sign as n goes to infinity, we can define a new sequence bn, which is the square root of an minus 2 minus an minus 1 squared, right? And then r becomes the limit of bn over bn plus 1 when n goes to infinity. All right, so let's try. And the other thing, one of the important things is that r, the radius convergence, can be infinite. All right, that means this limit can go to 0. So typically people evaluate 1 over r, which is this limit of square root of n an. All right, so we can also do that and then invert it. And the meaning of the infinite radius of convergence is that no matter how far we are from, if we write the Taylor expansion for x0, no matter how far from x0 we go, this Taylor series eventually converges to f of x, no matter how far. That's the meaning of the radius of convergence. The problem is that Taylor series have, as we get farther and farther away from x0, the convergence becomes slower and slower, which means we have to add many more terms in order to get a good accuracy or get a good estimation of the function. All right, so let's try to go ahead to Eclipse here, and in our Taylor series class, Taylor expansion class, what we want to do, we want to find the radius of convergence, radius of convergence. So what I'm going to do first, I'm going to create a public sequence. I'm going to create a sequence that basically represents the nth term, the terms of the coefficients of the Taylor series. So we're going to basically get term at double x0 and or maybe let's call this Taylor coefs and int n. All right, so what happens here is basically we want to do the same thing here. So let's look at this for loop, and we are going to evaluate basically at So I here is the n, we're looking only at the nth term, and then we're going to return n goes to so this so n here is the nth degree. We want to what do we want to calculate? We want to calculate the nth term of the sequence, right, at x0. So we don't need to know the n, right? So basically we're calculating an, the coefficients, or fn. The term is x minus x0 to the nth power, right? So let's call this Taylor coef, and then what we need to do here is we're going to say that return n goes to something. And what is that thing? If n is equal to 0, we're going to return the function at 0, right? And then else we're going to say that, okay, we're going to create a copy of the function, and then basically we're going to eventually return something like this. So let's see, we're going to create a copy of the function, and we're going to calculate the factorial, and then we're going to for k from 0, k less than n, k plus plus, we're going to take the derivative, calculate the factorial, and then we're going to return 1 over factorial, the nth derivative. So we're going to return 1 over n factorial times, alright. Okay, this is how we create the Taylor a sequence that represents the Taylor series, the Taylor coefficients, alright. So let's go back here, look at the sequence, So here we calculate the Taylor series of this function, and let's create a sequence Taylor coefs, and or let's just call it Taylor is Taylor expansion dot Taylor coef at x0, which is 0, all right. And let's just sys out Taylor evaluate at 0, and then sys out Taylor evaluate at 1. Let's say we want to see the first 5 terms, 2, 3, 4, 5, 1, 2, 3, 4, and 5. All right, so let's run this. So also let's make the Taylor expansion 5. So we have so this is the plot. So the 0th term is 0, and then 0, and then 1, and then 0, and then minus 0.333, correct, and then 0. So now we have a sequence that represents the Taylor coefficients, all right. And now what we want to do is find the radius of convergence. So finding the radius of convergence, and the way we're going to do it, we're going to create a new sequence, and then so let's do this here. So I'm going to create a new sequence, bn or b, which, or the rn, radius, this represents the radius, which is n goes to basically math dot pav of Taylor sequence evaluate at n, and raise it to the power of 1 over n. And let's make sure that the n is cast as double, all right. And always be careful. So if I write this as 1 over n, because n is a long and one integer, the result is always 0. So Java compiler interprets it as 0, which is incorrect. So we want to make sure that whenever we write something here, it's 1.0, which already doubles. Or if we write just 1, which will be interpreted as int, we have to make sure that we cast double for n, right? Just make sure that you do that, otherwise you get a wrong answer. Always be careful about how the Java compiler handles integers and longs when we in fact want to have a double value. So this is radius of convergence, radius of convergence sequence. And then let's plot this. So what we're going to do here, I'm going to basically create, so let's put this MATLAB thing here, the previous figure, and now I'm going to create a new MATLAB chart, fig new MATLAB chart, and then what I'm going to do, I'm going to create double indices, mass utils, linear space. I'm going to give it a step size. So I'm going to start from 1. Okay, now so I'm going to create new double 100 points, and then double radius vals, new double indices dot length. Alright, and then for int I equals 0, I less than indices dot length, I plus plus, we're going to have indices I equals I plus I, because we want to start from 0, okay? And or I plus 1, doesn't really matter. So and then radius vals at I is basically, note that indices of is double, but this sequence evaluate, it has to take a long, so we're going to pass in I plus 1. all right, and then now here I'm going to fig dot plot indices and then radius vals, fig dot render plot fig dot show with a true flag. Okay, it's taking time. All right, so maybe let's just look at the 10 terms first. So as you can see, all the odd terms are 0, which we expect. So we have only even zeros, right? And then we are calculating the basically what we are calculating here, this is actually the reciprocal. What we are calculating here is 1 over Rn, because this is equal to limit of an to the power of 1 over n. all right, so what we need to do, we have to basically invert this, and the problem here is that we have zeros, so if we invert this we end up with infinities, right? Yes, so let's stick to, that's one reason that we always prefer to calculate 1 over r instead of 1 over this limit. And then what we want eventually is to have the limit of this sequence. Okay, so if I put 20 here, we see that it takes time to run and does the calculation, because it just have to make more and more take more and more differentiation here. Okay, so it takes time. and it's still taking time. So okay, this is probably not the best approach, but if we look at, for example, the Taylor series 20 terms, what we see, let's run this. Now obviously it's still struggling, so this takes time for the Taylor series to evaluate. But the idea here is that we can find the inverse of the radius of convergence by looking at the square root of the nth root of an, okay? Now we know that for the sine function, all the coefficient, basically, if we look at the, for example, the terms, let's put this back here one more time. What we do know here is that, for example, if I calculate for the nth term, and I actually have to take the absolute value here, absolute value of the Taylor, okay, and all the coefficients are positive for the sine squared. So what we can do, and it is obvious that this sequence is converging to 0, and when it converges to 0, and remember this is 1 over radius of convergence, it means that radius of convergence is infinite. So we can, if we are expanding around x equals 0, we can be infinitely away from 0, and the Taylor series still should converge to the original function. But we just, but then it has a slow convergence, so we have to add many terms, all right? However, so here we have the we have a sequence an which basically doesn't change sign. So what we need to do is that we can use this definition, an over an plus 1. So so instead of doing this, I'm going to create a new sequence. Let's call this radius, n goes to Taylor evaluate at n divided by Taylor evaluate at n plus 1, all right? And now let's look at this sequence. So the problem here is that we have alternating every other term coefficient of the sequence is 0, so this is basically not a good way of calculating the radius of convergence, okay? Because if n is even, n plus 1 is odd, and all the odd terms are 0. But let's say we look at the x equal 1 instead of x equals 0. And then we try to evaluate this sequence. And as you can see, it's oscillating. So we don't have actually a positive sequence, it's oscillating. So we need to do the sequence B, which is n goes to math dot square root of math dot abs Taylor evaluate at n minus 2 times Taylor evaluate at n minus 1 n minus 2, so n minus 2 times n minus Taylor dot evaluate at n minus 1 times Taylor evaluate at n minus 1, okay? So we end up with this sequence. b, and then we try to calculate bn over bn plus 1. So let's say it's radius again. Let's comment this. N goes to b, evaluate at n, divided b dot evaluate at n plus 1. And let's see what happens now. Okay, so as we see, this is going to infinity, growing. That means the radius of convergence is going to infinity, which means the radius of convergence of the sequence is basically infinity. Okay, but if I add something like sine squared over x minus 2, for example, then we have a singularity at x equals 2. Then the question is, we should be able to get a radius of convergence when we expand around 1 of just 1, right? We can only go from 1 to 2 until we hit the singularity. So let's see what happens in this case. Now, calculating the radius of convergence takes the Taylor coefficients takes time, because we're using our symbolic function, so we're taking a lot of derivatives. But let's just wait. And but again, the idea here is that if we are expanding the Taylor series around a given point, the radius of convergence is the distance from the point to the closest singularity of the function. Here we have x equals 2. So the radius of convergence is 1, going from 1 to a maximum of 2. All right? As soon as we hit the singularity, the Taylor series starts to diverge. So it doesn't converge to the function again. So this one is still calculating, so it takes time, even for 10 terms. Okay, it's still calculating. Alright, I'm going to stop this because this is taking too long, but this was the whole idea of the radius of convergence for Taylor series. I hope you enjoyed this lecture. Please stay tuned. I have more lectures to come, and I hope you enjoyed this video, and thank you, and I'll see you in the next one. Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on sequences and series. And basically, I want to do a recap on what we have discussed so far, and then go and introduce new concepts. So a sequence is basically a discrete version of a dense function, all right? So a dense function means its variable is a continuous or real number and can be anything. So it's a continuous variable, and then we have a continuous function. But a discrete sequence or discrete function means we only evaluate the function at integer, plus integers, negative integers, or 0. And then we said that most of the time we don't use the notation of f of n. If n is integer for sequences, we use a sub n or b sub n. And then we said that one of the main things about sequences is their limit. We want to see if a sequence converges to a specific limit or not. And for example, 1 over n squared, as n goes to infinity, basically as n grows larger and larger, approaches 0. So we said that the limit of this sequence 1 over n squared is 0. This one is Euler's sequence, and the limit is Euler's number, so 1 plus 1 over n to the power of n. So the base approaches 1 from the above, which means the base is always greater than 1, but it's decreasing and decreasing to 1. But then the power gets larger and larger, and any number greater than 1, when it's raised to some power, it grows. So the base tries to, the power or the exponent tries to increase this value or growing it, but the base is decreasing. So, and the pace of these two cancel each other out perfectly, and this sequence eventually ends up converging to a finite number, which is called Euler's number. All right. And we implemented sequences as a functional interface in Java, and we said that that's a very convenient way, because then we can easily define them anywhere in our code using lambda expressions. And we said that one particular type of sequences are recursive sequences, where we define a new term based on prior terms. And then we said that in order to resolve and be able to find, explicitly find the values of each term, we need to have initial conditions, all right? And the initial conditions, the number of initial conditions we need depend on how many terms we use, how many recursions or recursive terms we have. For example, in Fibonacci, we have we are using two of the previous terms to define the new term. So we need to have two initial numbers or initial conditions. And then we said that one of the very, very important sequences are called series or partial sums, and then the series and the partial sum of another sequence. So the partial, if we start with the sequence a sub k or a sub I, and we sum its term from some index k, which is usually 0 or 1, to some variable n. So n is variable here. We call this a partial sum for this original sequence an, and we typically denote it by s sub n. And then if this sequence, the new sequence s sub n, or the sequence of partial sums, converges, we say that this series exists, and the value of the series is just equal to the value of the limit, okay? And one of the very important concepts here is that the necessary condition for the series to exist, or for the series to converge, or the sequence of the partial sums to converge to the value of the series or the limit, is that the original sequence or the generating sequence of the series a sub n or a sub k, which is the difference between s sub n minus s sub n minus 1, the difference between two consecutive terms of the partial sum. It is basically a sub n. This sequence a sub n must go to 0. The limit should be 0. Anything other than 0, the series does not converge. The partial sum, the sequence of the partial sums, does not converge, okay? And then we said that numerically we can test for convergence by by looking at the absolute error, which is the value of the sequence minus the exact limit, if there is an exact limit. But first of all, we don't know if there is a limit. The series might diverge. So we look at the growth of the series, or the change in the series, by defining this absolute error in terms of the error sequence. So Sn plus 1 minus Sn. And the relative error is the same thing. Again, we look at how the basically the absolute error divided by what current term grows, okay? However, there are some well-established tests for convergence, specifically for series. So if you have a partial sum sequence from, let's say, 0 to n of some sequence ak, and then we want to know if k from 0 to infinity, basically it's the limit of s sub n, whether it's a finite number or it's an infinity, for example. So whether it converges or diverges, all right? So if this k from 0 to infinity ak exists and it's not infinite, it's a finite number, we call this the value of the series, all right? So we want to test this by just looking at the generating sequence a sub n. And the test is going to tell us whether or not the partial sum sequence converges, or basically the series converges. Here I have put 3 of the most famous tests. The first one is ratio test, or the Lambert's criterion, and it says that take the generating sequence a sub n and find the ratio of a n plus 1 over a n, all right, absolute value, and look at the limit. If this ratio sequence, right, so basically we're generating a new sequence which is the ratio of a sub n plus 1 over a sub n. If this new sequence, the ratio sequence, converges and or maybe diverges, so let's call the limit r. So there are 3 cases. One is r, let's say r exists, so r is less than infinity. So first of all, r could be greater than or equal to 0, right? R cannot be negative because we are taking the absolute value. So if r is less than 1 and it's obviously greater than or equal to 0, automatically it means that r is a finite number, it's not infinity. And this guarantees convergent. All right, so this, if r is less than 1, we are guaranteed that this sequence, partial sum sequence, converges, or the series converges to a finite number. If r is greater than 1, which can very well include infinity, all right, if this limit is in fact infinity, then we are guaranteed to have a divergent series. The partial sum sequence doesn't converge. If r is exactly equal to 1, then this test is inconclusive. We cannot say anything with confidence or with accuracy about whether or not the partial sum sequence converges. All right, and we have to use, for example, another test. The next test is root test. So root test is important in a few ways, and because when we're dealing with Taylor series or power series, this root test is directly related to the radius of convergence for power series, and that's a very important concept. All right, so again, we take the absolute value of an, this generating sequence for the partial sum, and then take the nth root, so nth root of a sub n. And this is a new sequence, of course, so we can look at its limit. N goes to infinity, and let's call it r. So if r is less than 0 and greater than is less than 1 and greater than or equal to 0, then we are guaranteed that this partial sum sequence converges. If r is greater than 1, which could also include infinity, then this partial sum sequence diverges. We are guaranteed to have a divergent series, and the divergent series means that the result of k0 to summing from 0 to infinity ak is either plus infinity or negative infinity. And if r is equal to 1, then we have inconclusive. The test is inconclusive, and we have to use other tests. The third one is Leibniz criterion, which is typically applied to an alternating series, which means this generating sequence AK, or AN basically, has an alternating sign, which is typically means we have a -1 to the nth power or something like that in the sequence. All right. So in this case, first of all, obviously we know that an must go to 0, so the limit of the generating sequence must go to 0, otherwise the series is guaranteed to diverge. And the next one is that, okay, so we know that an goes to 0 and an is alternating between negative sign and positive sign. So if for every n is an plus 1 is less than or equal to an, basically an is here we are assuming the generating sequence is -1 to the n, or -1 to the n plus 1 an. So we're assuming that an is basically positive. So you can think of this an here in the conditions as the absolute value of this generating sequence. So here we are assuming that an is basically always positive. We're taking the absolute value. So if an is positive, goes to 0, and it's a decreasing sequence by our definition here. So if it's a decreasing sequence, which means it never goes up, it either stays the same or goes down for every n, then a sequence, a partial sum, which has an alternating sequence -1 to the n an or -1 to the n plus 1 an. These two are guaranteed to converge. Obviously the difference here is just a minus sign, so it doesn't really matter if we have -1 to the n or -1 to the n plus 1. If the magnitude of the generating sequence is decreasing, and then it's in fact it has an alternating sign, then it's guaranteed to converge. All right. So for a full list of tests for sequences, you can go to this page on Wikipedia, en.wikipedia.org/wiki/convergence tests. All right. And we also said that one of the most important series that are related to functions are Taylor series, and they typically represent smooth functions that don't have singularities, and they are based on an expansion of the function into polynomials around a given point x0, and the terms are 1 over n factorial times the nth derivative of the f calculated at x0. And then as we add more and more terms, this series approximates the function better and better. And then one example here, e to the x is summing from 0 to infinity x to the n over n factorial, and this basically has an infinite radius of curvature, it has an infinite radius of convergence, which means as here we are expanding about x equals 0, okay? But then if we plug any x here, x 100, 200 or something, as we add up this series with more and more terms, it actually converges to the value of e to the 100, for example, all right? That's the definition of the radius of convergence. And when we say that the radius of convergence is infinite, we mean that you can plug any x here. No matter what, this series always converges. And then one of the very, very important concepts that we talked about, it's very important, is the acceleration of the convergence of sequences or series. And we said that if we are starting with the sequence an, which has a relatively slow convergence, first of all, we know that it converges. And then we look at its trend as we increase n, and then we see that it's converging to some number, but it's a very slow convergence. And then we said that if somehow we could start from an and build another sequence bn that also converges to the same number, to the same limit, but then it also satisfies this limit, so limit of bn minus a over an minus a as n goes to infinity. If this is 0, we say that we have transformed a sequence into b sequence such that b has a faster convergence than a, all right? Remember, b and a are not the same, but they have the same limit. And if bn has a faster, because we are trying to find the limits, and we want to find it by not going to a very large number of n, because as we increase n, it adds more and more computation cost, which we want to avoid, all right? And we discussed 4 of the most important transformation of the sequence. One of the things that always pops up in this transformation is the notion of delta or difference, discrete difference. So delta of an is an plus 1 minus an, which is also sometimes called the forward difference. And we can also define a reverse difference, which we typically denote by delta bar, which takes an and subtract an minus 1 from it, all right? But whenever we say delta an, we mean forward difference. And we said that binomial transformation, so it takes the sequence A and converts it into a series S, a partial sum from 0 to n minus 1 to the k, k from n, ak. And then we said that Euler transform, if we have a sequence that has an alternating sign, minus 1 to the n, Euler transform transforms an to minus 1 to the n, an to minus 1 to the n, sn, where sn is basically nth difference of a calculated at index 0 divided by 2 to the n plus 1. And the thing about Euler transform is that it is guaranteed that if minus 1 to the n an converges, the series converges, then the minus 1 to the n sn, also the series over this sequence, also converges to the same number. So these two series have the same value, the same limit when we look at the partial sum sequence and let n goes to infinity. All right? So these two sequences, when we calculate the series from them, the series are guaranteed to have the same value. They converge to the same number. But the Sn sequence, delta n a0 to over to the n plus 1, this definitely dies off faster than an. Therefore, this series on the right has a faster convergence rate, right? Because one of the things that determines how fast a series converges is how fast the generating sequence an actually dies off. Because an must go to 0, otherwise the series is guaranteed to diverge. And the faster an goes to 0, the faster the series converges. All right. And then we looked at these two very important transformations, which are essentially the same in some sense. And we look at Aitken's delta squared process, which takes the sequence xn and applies a transformation. We typically call it AX sequence, and at index n, it takes the xn minus 2 minus delta xn plus 1 squared over delta squared of xn. And delta squared means apply delta on delta. So because when we apply delta on xn, it gives us a new sequence, and now we can apply delta on the new sequence again. All right. And we said that Shanks is also the same thing, but Shanks at over an is basically Aitken over xn minus 1. All right. And we said that the idea here is that if we have a sequence, we're summing over am from 0 to infinity. First, we define a partial sum, this capital An, from 0 to n of the original sequence am. And then now we want to see whether or not this partial sum sequence converges. And in order to accelerate the convergence, we apply the Aitken transform or Shanks transform, S of an, which is basically this term. All right. And then we said that the good news is that because the S of an converges to the same number but faster, we can apply Shanks transform multiple times. So we apply S, we get a new sequence. We apply S to the new sequence, we get S squared or S of S. And then this is a new sequence, so we can apply Shanks one more time, get S of S or S cubed. We typically don't go beyond 3 times Shanks because there's a chance that the convergence becomes unstable. So if we apply too many times these Shanks or Aitken transforms, the sequence that we end up with might very well become unstable. And we said that one of the very famous examples are this series that approximates pi, 4 times minus 1 to the k over 1 to the 2k plus 1. This is an alternating series, okay? And we can test it in different ways and confirm that it actually converges. For example, with the ratio test, let's see, if we take the ratio test, we end up with 1 over basically 2 times n plus 1 over 2 times n plus 1. And the limit is 1. So the ratio test is inconclusive. And then, but the Leibniz criterion, which we can always use for alternating series, says that, okay, this sequence is alternating and its absolute value is proportional to 1 over 2n plus 1. And then this sequence is always decreasing monotonically, okay? So we have a sequence, we have a series whose sequence is alternating sign and its absolute value is monotonically decreasing. So it's guaranteed to converge. There is no doubt about that. And then we said that we can approximate the error by converting the error into, error is from n to infinity, and we can approximate it by an integral from some n to infinity, and the integral of 1 over x is basically log of x. So the error of this series behaves like log of n, which is very, very slow in terms of dying off and going to 0, okay? And then we said that, okay, if we look at, for example, sum of 20 terms of this sequence, we see that after summing 20 terms of this sequence, we have an error which has about 1 decimal place of accuracy, which is very bad. As soon as we apply the Shanks transform and look at the new sequence, after 20 terms, 20 summations, it has at least 3 decimal places of accuracy. The second Shanks transform brings it up to 7 decimal places of accuracy, and then the third Shanks transform basically gives us an almost exact result. It has more than 9-10 digits of accuracy, decimal places. So we see how the acceleration, all these transforms help. And we said that because we defined the sequence as a functional interface in Java, it means that it can only have one public abstract method, so the rest of the methods should either be static or default. So we added all these transforms as default methods which return new sequences, new sequence objects. The next one of transformations, which accelerates the convergence, is also the very important one, because this transformation, we typically use it all the time when we're dealing with integration, do numerical integration, or numerically solving differential equations. And it is called Richardson transformation. So Shanks and Aitken are good for oscillating sequences, the sequences that have an alternating sign, but they do not work well for non-oscillatory sequences. For example, 1 over n squared, if you look at the series, that is sigma of 1 over n squared, no matter how many Shanks or Aitkens you apply, it doesn't really accelerate the convergence that much. But Richardson transform works very well for non-oscillatory sequences. And then we said that we can define different orders of Richardson. The Richardson of the first order is just n plus 1 times Sn plus 1 minus n times Sn. Remember, we applied these transformations on the partial sum sequence. You can apply it to any sequence, but here we're looking at the series in particular. So we're applying these transformations on the partial sum. Richardson's second order is n plus 2 squared, Sn plus 2 minus 2 n plus 1 squared, Sn plus 1 plus n squared, Sn over 2 factorial, and etc. And here's a Java code that we wrote that implements the first order Richardson. Basically, it's a default method in our sequence interface. And the Richardson, first order Richardson, returns a sequence in object, and we define this very easily using a lambda expression, because when we apply this Richardson on a sequence, the result is a new sequence. So n goes to n plus 1, evaluate the original sequence at n plus 1 minus n times evaluate the original sequence at n. All right. And then we did a very nice example of how Richardson can in fact accelerate the convergence, whereas Aitken or Shanks, they fail miserably at accelerating the sequence. And the example that we used was the series for 1 over k squared. We already know the exact result, exact limit, which is pi squared over 6. And this is a non-oscillatory series, right? The sequence 1 over k squared is non-oscillatory. It doesn't change sign for different k's. And we said that we can estimate the error by converting the error summation into an integral 1 over x squared from n to infinity, which is 1 over n. So the error for this summing up this partial sum of this series behaves like some constant over n plus some constant over n squared, etc. And as we see here, the Aitken after 50 terms, if we apply Aitken 3 times, after 50 terms, we only have 2 decimal places of accuracy, less than 2 decimal places of accuracy. But if you apply, for example, third order Richardson, after 50 terms, we have more than 10 decimal places of accuracy. And then another example to signify the behavior or the use of Shanks and Aitken versus Richardson is when we take this exact same sequence, which is 1 over k squared, and we're summing over that. And we apply an oscillatory terms, minus 1 to the k plus 1 over k squared. So this is 1 minus 1 over 2 squared plus 1 over 3 squared, etc. And once we apply Richardson, we see that not only Richardson doesn't help the convergence, but in fact it causes the series to diverge. So if we apply Richardson, the result is a divergence. But as soon as we apply a Shanks or Aitken, we see that this blue one is the original sequence, and the Aitken, the double Aitken, and the triple Aitken, they pretty much converge super rapidly to the limit, which is 0.822 something 5. Okay, so when we are dealing with the series of an oscillatory sequence, we definitely use Aitken or Shanks. When we are dealing with a series of a non-oscillatory sequence, we use Richardson. And then we also discussed about where the idea of the Aitken and Richardson in general come from. And the idea was that we can model the behavior of the error as these sequences or the partial sums approach the limit. And we said that for oscillatories, we can model it with the error is basically some number to power of n, right? So it's more like a power model, which is some number to the power. And then for non-oscillatory behavior, which is suitable for Richardson, it's more like 1 over n to some power. Okay? And then we said that, for example, if we have such a model for the error, some number b, and then another number to the power of n, so n is in the power, then we can say that if for large n, an is asymptotic to L, which is our limit, plus a minus b to the n, we can also write the same thing for n plus 1, n minus 1. And then we can solve for L by eliminating a and b. L becomes an squared minus something. So we get this term, which is exactly Shanks. And in order to get this, basically we bring L to the other side, and then we realize that if we eliminate b, basically minus b is an minus L, an minus 1 minus L, an plus 1 minus L, an minus L, and then now we can solve for L. And it's not a quadratic equation, it's a first degree equation. And this is Shanks. Similarly, for the Richardson, we see that we can do the same thing. So if we go back and use this model and apply the definition of the, for example, first order Richardson, here we see that n plus 1, Sn plus 1 minus n Sn causes the error to go from 1 over n to the b to the 1 over n to the b plus 1. So now the order of error goes from b to b plus 1. Similarly for Shanks and Aitken, so if you take this error model, a minus b to the n, and put it into this sequence, which we already know that it converges to L, all right? Then you end up with L plus a some number times another number to the n plus 1. So the order, and this b should definitely be less than 1 for the error to go to 0, okay? And one of the very famous use cases of these accelerations, specifically the Richardson acceleration, is Romberg integration. So we can start with any slow numerical integration method like forward rectangle or trapezoid or Simpson, and then apply, create a partial sum, define a sequence which is equal to the partial sum of the integration for this method. Here I'm defining a sequence which is the partial sum based on the trapezoid method, partial sum for the integration. And then I apply a fourth order Richardson to this partial sum of the trapezoid and call it the Romberg sequence. And then evaluate the Romberg sequence at the number of sub-intervals that I have, okay? And then here's an example. So we looked at f of x equals sine of x, and we integrated this over 0 to pi, and we saw that the forward rectangle has a painfully slow convergence after, even if we divide the 0 to pi interval into 50 sub-intervals, the error has a hard time going down. So the accuracy of the forward rectangle has about 1 decimal place of accuracy. Trapezoid obviously has a faster convergence from faster than forward rectangle. So after dividing the interval by 50 subintervals, we get at least 2 decimal places of accuracy. But then as soon as we apply a Richardson on the forward rectangle or a trapezoid, we end up with a much better accuracy. And we also mentioned that here, as you can see, after some number, for example more than 35 subintervals, the Richardson kind of becomes unstable. And that makes sense, because the higher the order of the Richardson, the higher the chance that it becomes unstable for larger n. So typically if we increase the order of the Richardson transform, we want to stay to the lower terms, a smaller index, 20, 10, 20, okay? We also discussed some useful sequence operations. For example, canonical delta is just a sequence that we can define as a static method in our sequence interface. It's 1 only for n equals 0, and for any other n it's 0. Unit step, basically it's 1 for any n 0 or greater than 0, and 0 for any n less than 0. And then we said that the convolution sum of the sequences is defined based on am bn minus m, and we're summing over m. So n is fixed here, is the index of the cn sequence, and m is changing. And we can assume that an and bn sequences are 0 for n less than 0. So here the index runs from 0 to infinity. But then bn minus m, so m also is limited, has an upper limit of n, because as soon as we go b minus 1, b minus 2, b becomes 0. So convolution sum, we define it from 0 to n, okay? We also defined a running average sequence, bn, 1 over the number of terms. We start from an and then add na plus 1 all the way to n a sub n plus m minus 1. Alright, this is some sort of averaging from one point, and it's more like a sequence transformation, okay? We also discussed the perturbation theory. We said that perturbation theory is a use case of power series, and if we have a hard problem, we can break it down into an infinite number of easy problems by introducing a free parameter, which we typically call it epsilon. And the assumption here is that when we set epsilon to 0, i.e. we end up with an unperturbed problem, we should be able to easily solve it, okay? Ideally we should be able to find a closed form solution. And then once epsilon is not 0, what we do is we write the solution in terms of a power series of epsilon, and then eventually we set epsilon to 1 after finding all the coefficients for this power series, okay? And one example that I showed here, which is a nice example, is let's say we have this equation x cubed plus x equals 1, and we are asked to find the real root. We already know that the real root should be between 0 and 1, right? Because if it's negative, x5 plus x is always negative. If x is greater than 1, then x5 plus x is definitely greater than 1. And then we said that let's add an epsilon as a coefficient to x term. So x5 plus epsilon x equals 1. And when we set epsilon to 0, we end up with a0 term here, a0 coefficient, which is the solution of x5 equals 1, which is 1. And then we said that, okay, the general solution of this x5 plus epsilon x equals 1, we can write it as a power series of epsilon, and then we found the first few terms, a0, a1, a2, a3, a4, a5, a6, all right? And then in the Java code, we actually run the bisection method on this equation, and then we found the exact solution, which is 0.754877, etc. And then we sum these first terms, the first 7 terms of the perturbation theory, and we ended up with 0.7543. The exact one is 0.7548. So up to 3 decimal places of accuracy, which is a very good thing, okay? Finally, we also have some useful things to remember when we're dealing with power series and applying the perturbation theory. One is if we add a constant number, capital A, to a series an x to the n, which is a power series, we can represent it with a new power series, and Bn is an plus capital A times delta of n and 0. This is the Kronecker delta. All right. So if n is 0, Bn is B0 is A0 plus A. If n is non-zero, this term is 0, so Bn is An. Similarly, instead of having a constant term, if we have A times x to the p power and add it to a power series, we end up with a new power series, and Bn is An plus capital A delta of n and p. So if n is not equal to p, Bn is An. If n is equal to p, Bn is An plus A. And then the multiplication, exactly the same thing. When we multiply, we end up with a new power series, and the coefficients are the convolution of the original coefficient. All right. And then raising to some power, let's say integer power, it's just multiplying by m times by itself, so it's just the convolution, right? So raising a power series to some integer sequence is just multiplying by itself, so we end up with a convolution. So we can actually raise the sequence to a power that is not integer, let's say 1.2 or -2 or something. Then we can use the Taylor expansion of these basically the 1 plus something 1 plus f to power of m. All right, the Taylor expansion of that. Okay, this was a brief summary so far of all the discussions that we've had on sequences and series. In the next lecture, we look into more of the properties of the sequences and series. So please stay tuned. Thank you for watching, and I'll see you in the next one.